Hi, Anna, are you there?
Yes, I am. Oh, hi, Tracy. I thought it was Amy. You have very similar voices.
That's funny. Um,
Yeah,
I wondered if I could, well, let's see. Oh, hey, good. My
nice.
camera works for a change.
Oh, this is the virtual background. I thought that you have this really cool poster behind
I
you.
do. It's like, 20 feet that way.
Oh,
And then you see like the foosball table between me and it, and maybe
I get
kids playing on it. So I thought, I'll just move it closer.
it.
Um, yeah, it was kind of nice. The gift shop finally opened, so I could
Yeah,
purchase the VLA, the VLBA, the NGVLA, and the ALMA posters.
I didn't buy Alma.
I decided I had a wall of, exoplanets, so I added it on the next wall of
Fair enough.
instruments. I was wondering if I could give a try at my
Please
talk.
do. Sure.
Let's see. My computer sometimes behaves, sometimes not. How is that?
Perfect.
Oh,
As in, I can see the talk in the presentation mode.
okay. Now,
Mhm.
is anything blocked by the Zoom window, or that's just on
Doesn't
my?
look like it.
Okay, good.
Unless you want to flip to the other pages, maybe it will be more. No, it all
Seems
seems
good.
fine. Hmm.
Right. All right.
Let me check. You're in the second session
I
today?
know I'm the third talk, I think.
Oh, third
Unless,
talk. Yeah, sorry. I'm
unless it's moved.
losing memory of everything at this stage.
How could you with this many talks?
I was not an SOC. I would say Amy and Frank as the chairs of SOC, but the fact that they could fit in so many, I was actually quite impressed.
Yeah,
But it's packed program.
it sure is. Right.
Cool.
All right. Well, I'm glad it works. Thanks.
Hey, Joe.
Hey, Greg, you can hear me?
I can hear you, yes.
Most excellent.
Yep, I'm not sure. I don't have co-hosting ability yet, so I'm not sure if it's on for sharing, but oops. Anna, you're muted.
Yeah, I know, right? I'm here in charge of unmuting and muting everyone, and I'm just tired. Anyway,
enough.
who is I'll make you a host, co-host, just as I'm setting up everything.
No
It'd
worries.
be actually super helpful.
Yep. Do
You
you
are.
need help setting up the Slack channels?
Oh, I still haven't done it. Sure.
I
Or I
can-
can do it in a sec. I'm still sending an email because we have different streaming one today. And I forgot about, I mean, I probably couldn't do it anyway yesterday. I need to take a lot of photos of the conference. Probably will do it in like 4 takes or something. So I'll email about this. I don't know whether you want to mention it or something. I think the first one I'll try to do will be straight after those 2 sessions at the beginning of the break.
Anna,
Alright.
I'm here now.
I say, hello,
Alright,
Rick.
excellent, Rick.
I guess we
So-
should. Sorry, go ahead.
I was just say, yeah, I'll be the chair for the morning before the break. And the question I have is if people are happy to just quickly make sure that their slides are sharing the way they want them to, that'd be great if you're in the morning session.
Well, I'm the
Tracy-
first. I'm the first in the morning, so I'm ready to try.
I'm
And-
second and I'm on for the same reason.
Okay, and Tracy already checked. Hers is all working.
Oh, excellent. All right, Rick, why don't you go ahead?
All right, I'm going to push this green button and see what happens.
As long as it's not a red one, you're okay.
Yeah, okay. All right, you see anything?
Yeah.
We see your screen. It's not in presenter mode yet.
Yeah, just a minute. View.
Sorry.
Oh, slideshow, sorry. It's from the beginning. How's that?
Perfect.
Amazing.
From the beginning, Rick. Wow.
Yeah, right. Well, believe me, it's a long story. I'm not even going to get into it because it'll put me in a bad mood.
Uh-oh.
All right.
All right,
Excellent.
so, okay, let me stop share and hope that we can do this when the time comes. Anna, this has changed a bit. I'm going to try and send you the
It's
PDF of
okay.
this.
You don't need to
Okay.
do it now. I mean, as long as
Okay.
they're presented, I don't need them.
Okay,
At this
good.
very moment.
I'll send you the final copy after all the dust is settled.
All right, Joe, do you want to try?
Yep. Okay, now you're seeing the slide.
Yep.
And are you seeing presenter view or
We're seeing the swap presenter view. So you'll want to swap your displays.
like so?
Perfect.
Okay.
All right. Excellent. And for all the speakers that are on so far, I will try to give you guys a 2-minute verbal warning. I apologize, but there's no way on Zoom to do it without interrupting your talk.
Yeah, it's all right. I have my watch next to me, so I don't run over. Yeah, 15 or something.
You have, sorry, I'm juggling several different screens.
Yeah, it's all
You
right.
have 25 minutes, and I've got to go double check my notes for how long that actually means you have.
20.
20, that's fine. We'll go for 20. I can do it. I hope.
Sorry, 20 for the talk and 5 minutes for the questions.
Yeah.
And the rest is 12 plus 3, I believe.
Yes.
I really need to not be doing this on my laptop. I need 4 screens.
Yes, same.
Uh,
Oh my- Oh yeah, we still have 10 minutes. I was wondering. No, that's good. That's good. I mean, I still can do a couple of things.
It's all good. Anna, you're doing a great job. Just these are insane. These are always insane to organize, so don't worry.
I know. I
So,
know.
so after all this is over, Anna is going to need a good stiff drink.
Well, I have to drive later on, so maybe just one. But
But,
yes,
but we can help with that.
I know. Well, you have, I'm sorry, I know I just got this as a private message, but I just going to mention, Rick, that if you run over time, one of your neighbors is going to stop you.
Well,
Oh,
that's okay. I have my watch and a clock.
There was a-
I will do my best. I'll just faster than I already do.
That's fine. It was kidding.
Yeah, I know.
Whether it's next door.
Yeah.
Okay, I have to set up streaming here.
supposed to be co-host, so why is that not showing up?
I'm gonna try sharing mine for just a second to see if I can get my presenter view running so I can keep track of time.
Go right ahead. I will be a vicious host anyway, so you guys start going over. The wonderful thing is I can mute everyone.
Why do I hit 2?
You'll swap displays.
Ah, I don't have a swap display button. Okay. I saw Joe magically do it, but it doesn't show up. I'll just do without it.
How do you not have that swap display button?
I don't know. I don't. It shows up sometimes, but it's really not here. Fascinating. It's probably because I'm running through a hub to another display. I don't know. Whatever.
Okay.
It's fine.
Like I said, I will give a 2-minute verbal warning.
Sounds good.
Rick, how are you?
Luis, hey, have you got a date when you're going to be able to come here yet?
Not yet, but I'll arrange that soon. It will be great to see you in person.
Yeah, we have the deck all ready for you.
Hi, Rick from Bologna. I am Gabriele.
Yeah, Gabriele, how are you?
Fine, thank you.
How are the plans for your delayed celebration in October?
No plans, not yet.
Yeah, we're still hoping,
Waiting.
but we don't know. You seem to be at home.
Yes. Yeah, at home.
Yeah,
And we'll see what happens.
yeah.
Gabriella, it's Miller. Hello from me
Hello,
and Libby.
ciao. Ah,
We're missing both of you very much.
yes, we would like to meet, but it is not possible.
Yes.
Amy, do you want to quickly try your slides? All right. Not hearing anything back from Amy. So, good morning, everyone. Welcome to day 2 of the VLA at 40 Years conference. Today, we're going to be starting off with 3 sessions during the morning session, 3 different topics during the morning session. So, low radio frequencies, new developments, and radio surveys. Just as a note, Anna noted that she needs to take pictures of the conference, which these days mean, I guess, screenshots of all of us on the video at Zoom. She was hoping to do that after, I think she said after the first break. Is that right, Anna?
At the beginning of the next break, before everyone disappears for a break.
Right. At the beginning of the next break. So please don't bug out too early when we have the break. I know we only have 30 minutes, but it's nice to get some recording of these videos that are actually good for screenshots at least. So just as a note to all the speakers, I will be giving you all 2-minute warnings. I do apologize in advance that they will be interrupting your talk. Anna, is there anything else we should say before we go on?
I think it's all good. Oh, a moment. I'll have to record it.
Yes. So the other, so welcome to VLA at 40 in the morning sessions. Today, we're going to be starting with a discussion on low radio frequencies, new developments, and radio surveys. I will ask that if you have any questions, please either, during the question session, please either raise your hand or put it in the chat, and I'll do my best to get to you. So today we're going to first start with a talk from Rick Perley on some reminiscences from the early days of the VLA. So take it away, Rick.
Okay, let's see. And, okay, are we seeing it?
We're good.
All right, thanks. All right, well, first, thanks to the organizers for asking me to do this. This is not a science talk, but neither is it a total trip down memory lane talk as well. I still think I'm too young for that sort of stuff. But what I'm hoping to do here is to give some flavor, especially to the younger crowd, about what it was like to be on the very early end of developing and using the VLA. So, this thing is not advancing. Oh, there's a problem. I can't seem to move my slides ahead.
Rick, I often find you may have to click on your screen first, and then it will be able to advance.
Ah, perfect. Thank you. All right. So everybody has a first time at the VLA story. I actually have 2. The first one was a near miss. The second one we'll get to in a moment. So during the 1970s, from 71 to 77, I was a graduate student at the University of Maryland, and I was working with Bill Erickson's Clark Lake Radio Observatory thing called TPT. There's a little picture of it down on the right. This was a 48 banks of low frequency antennas working from 20 to 120 megahertz, and I was developing a novel form of aperture synthesis using the east to west arm alone. But what's important to the story here is that my thesis advisor, Bill Erickson, was a pilot. And every winter when he came out to the observatory to work during the session break, he would fly in and then fly back. And I twice flew back with him across the country from California to Maryland. On one of these, and I don't remember if it was 75 or 76, he announced that we were going to make slight deviations. The first deviation was to fly up the Grand Canyon, and I do mean in the Grand Canyon. And that was kind of exciting since it was really cool, but we ran into some fog banks and we had to get out fast. And relevant to this story is he said, there's a new array being built in central West New Mexico, and we should try to go find it. So off we went, and unfortunately it was cloudy. There were snow showers everywhere. I was the navigator holding a map, which didn't show the ground very well. We could only see little bits and pieces, and we failed to find the VLA. So that was my first glancing interaction with the VLA. At that time, I'll have to confess, I don't think I even knew what it was. Anyway, so upon completing my thesis in '77, I had the considerable good fortune to be hired as an astronomy postdoc, the first postdoc to be in Socorro, arriving in October of that year. So when we arrived in October, well, let me just back up and say this was an absolutely fabulous opportunity for me. The timing was absolutely perfect. I knew a little bit about synthesis. I had ideas for using high resolution observations of quasars, radio galaxies, et cetera, et cetera. When we arrived in the middle of October, there were 9 antennas that worked, more or less, all around the west arm. And in the bottom right is the little picture that I got from one of the monthly reports showing what the array looked like in 1977. At that time, by the time that we arrived, it had become the largest and most sensitive telescope in the world. It just passed the 5-kilometer array in England. And it was just a great time to arrive. There were 13 antennas visible here, but only 9 were actually outfitted, and it was very, by today's standards, very limited bandwidth. So the commissioning schedule, Ron didn't point too much of this out yesterday, but I thought it would briefly point out that the VLA was built, quite rapidly. Construction began in '73. First signals from one antenna 74, second antenna 75, first fringes early 76. 5 antennas became available in 77, and early observing started about then. 10 antennas in January 78. Fraser noted to me that his first published paper with VLA data was from data taken, looks like I can't spell, in January 1977. I joined a young, and I'm going to really emphasize this point, nobody, I think almost nobody on the staff when I got here was over the age of 40. It was a highly talented, ambitious, and filled with enthusiasm group. I'm going to do a lot of name dropping in this talk, but I won't read them all out, but you can see that the individuals in that first line, Barry, Ken, Gareth, Peter, they all were here by middle of 1975. Bob Jelming, the offline group, and others listed there, all were added on within a year. It was a very vigorous, active group of people. Barry has told me in the previous version of this talk given at the SK meeting in China that, quote, we didn't know what we were doing when it came to commissioning the telescope. But I know that's not true, but it does illustrate the kind of we can do it attitude at that time. Now, as a brand new postdoc here, a question that immediately came to my mind is what was I going to be asked to do? And quite surprisingly, I really wasn't asked to do very much. There's only 2 things I can remember, and I think they both came from Dick Thompson, is the first suggestion that perhaps I should look at some sort of graduated flagging scheme. The idea was to assign flagging weights to data based on their quality. This turned out very quickly to be not a good idea. I quickly found out that data were either good or bad, and there really wasn't anything in between. So we kind of ditched that one. And the other suggestion that Dick had made to me was a very important one. And this is almost a quote. He said, we were building this gigantic new array and we don't know how to calibrate it. Why don't you go think about that? And this is what started my long running and continuing efforts to improve array performance. I should also emphasize that this was not done because we were told to make things work. All of us here, all of the young scientists who were here at the time and those associated that distance in Charlottesville, we were out to make things work better because we could see opportunity moving ahead. And it wasn't that we were told to do this, is that we had to figure out how to make this work. So basically, all of the young new staff that came here, we were just basically let loose to play in this fabulous new sandbox filled with wonderful new toys, get science done. feedback to the engineers and programmers what didn't work, and support incoming users. So job number one was to write science proposals. Now, before I get onto that, I'd like to make another point about the social structures. Nearly all VLA-related activities took place at the VLA site. So we had to take a daily bus leaving at Socorro at 7:30, traveled up in 2 buses to the site, and then returned home at 4:30 in the afternoon. For those who couldn't make that stiff schedule, there were many vans available. That could be you could get on at 9, 10, whatever, all kinds of times. It was all done by personal agreement with the other people. But I want to point out that there was a lot of useful work done on these buses. So you were sort of in a captive audience. There were other people around you, and discussions invariably turned to problems of the day, fundamentals of interferometry, et cetera, et cetera. It was really good. One other thing is on the way back, a very special thing happened. There were 2 tables arranged in these buses and sets of seats rotated, and active bridge was played on these 2 tables on the way back. And getting a seat at the bridge table was quite competitive, so that the keeners who played bridge, I wasn't really one of them, but quite a few well-known people were. But this was only done on the way home. For reasons unclear to me, nobody played bridge on the way up. It just wasn't one. We ate lunch at the site in a cafeteria, and there were a bunch of visitors' quarters, initially 4, but ramped up to 10 as the observing pressure ramped up. In this arrangement, buses and overnight stays and eating at the facility continued until 1988 when the AOC here in Socorro was built. That changed everything. Now, returning to how things were in those days, writing observing proposals was considerably simpler in those days. You just wrote a letter to Dave Heasham. And in the upper right is a rather poor copy of my very first proposal dated January 4th, 1978. And I will say that as a, quote, insider in a brand new growing array, there was no problem in finding things to look at because everything we looked at was original and new. And you had never any trouble finding co-authors. Everybody wanted to get involved. And another little note that the number of proposers per proposal in those days was typically 2 or 3, quite different than things are now. This free format, just writing a letter to Dave Heasham, continued until fall '81 when a cover sheet was required. And I have a picture of an early cover sheet on the right that Ron Eakers and I put in. And as you can see, free form handwritten cover sheets were considered perfectly okay. All right, let's see. Okay, scheduling was done by hand. And here is Barry Clark would go around, would make up the schedule a couple weeks in advance. You would get a paper sheet, test time, which is in the purple there, was assigned by Barry simply by walking around and asking you what you wanted to do next month. So there was one advantage to this rather simple system is that you could actually organize your life at least 1 month in advance. Co-authors could be present. Very simple, but the obvious disadvantage is it's a fixed schedule, no changes could be possible, and an awful lot of high frequency observing was wasted due to weather. So the new system is considerably better, even if you can't organize your life much in advance. Observing. All observing was done in person at the site in those early days. In fact, before 1980, the observing scripts were on punch cards and had to be fed into a card reader. Probably most people listening here don't even know what that means, but it was certainly an advantage when we got away from the punch cards. All data calibration imaging was on the site. Visitors all had to be present. And as the number of the observing ramped up, more quarters were needed. 10 apartments eventually installed on the site, and mostly they were full all the time with all the visiting people coming through, all living at the VLA site. This resulted in a very lively social scene with regular trips to Daddle and Magdalena for dinner. As I mentioned before, lunch was in the cafeteria. And not until the rise of apes in the early 1980s could people make their images at their own institutions. The picture on the right shows the observing rooms, the same room we have now, with the observer's room in the glass cage in the left side, and the line printer, the famous line printer, which, as it turned out, if it ran out of paper, observing stopped. And I don't know the reasons for that, but that's the way it was. Data processing. During the 1977-1980 time frame, all processing was done on a DEC 10. This Ken Zawinski informs me that the processing power of this machine is about 0.1% of a modern PC. And it was shared between everybody who was there, competing for the uses, for these resources, including the developers. And we use a very special purpose software developed by Barry Clark and encoded by the various people working with him. No exportable software, everything was done on site. Data volumes were small, megabytes, but the resources were very limited and the competition was pretty stiff. I have a few comments on this later. Impact of self-calibration and snapshot imaging was huge, and I have a few comments to extend a little bit what Ron mentioned yesterday. There's a couple of pictures there showing you what the old DEC 10 looked like. I was unable to identify the individuals. The lower one shows Jim Thorson, who was one of our developers in the late 1970s working on the image processing system. Snapshots. Now, the original plans for the VLA, as Ron mentioned yesterday, presumed 8-hour observations and little to no deconvolution and a pipeline that he discussed, but automatically produce maps. In my own mind, that sort of meant every 8 hours, a piece of paper would flutter out of some printer and it would be mailed to the user. That wasn't what it was, but that's sort of the impression I always had. But as Bob Gemling pointed out to me shortly after I arrived here, the VLA's two-dimensional structure would enable snapshot imaging. First time I'd heard of this idea, and it was completely obvious that for objects that were compact and small, you didn't need to spend 8 hours staring at it. Very short observations would be useful. But of course, short snapshots have high side lobes, and high side lobes require deconvolution, much more computing needed. The early deconvolution programs were slow. Barry Clark's Clark Clean was one of the many innovations that were brought in response to these issues. But the thing, in my opinion, which really impacted the VLA's early scientific capabilities was the development of self-calibration. And this is not a computing talk, and I don't think I have any time to go through it, but it was a magical thing. But because it required iterated imaging and deconvolution, it required even more computing standards. And as Ron showed yesterday, he and I put together this little 3-element montage showing the remarkable, spectacular improvement in imaging quality caused by first deconvolution and then self-calibration. Well, the growth of these self-calibration deconvolution hugely increased scientific productivity, required more people to support, more staff were hired. I've got a bunch of names. Almost all of these people have been very kind to write to me with some of their memories, which I've tried to include in this. But from the late 1970s through the middle 1980s, a fabulous succession of postdocs, young staff arrived in Socorro and took up work at the VLA. We needed more space, so an extension to the control building was needed. So on the bottom left is the picture of the site in 1978 with the single VSQ in the lower right. And then the Science Library Office building specifically built to house all the new scientific staff was built just to the left side of the control building. And there's a picture of it on the right. And of course, we called it the slot. Computing was, as I've already mentioned, quite slow. The implementation of VAXes in 1980 was a huge improvement, but at the same time, the computing requirements were spectacularly rising. So there was always this tension, as already noted by some, removable. Oh yes, my disclaimer, all statements about me being a major factor in the computing crisis are maybe not true, but have been overstated. In the 1980s, we had removable disk packs holding 250 megabytes. Individuals signed up for 2-hour blocks. It was an amazing social scene. Poor Anna Nicole was assigned the job of putting up the sign-up sheets daily. She had to walk into the ape's cage. There was a mob waiting with pens at the ready. It was like a pack of wolves trying to get their 2 hours. And I'm really not overemphasizing. This was an amazing scene. Anyway, this is not a computing talk. There's a picture of somebody, I don't know if it was me or not, putting in a disk back of 250 megabytes on the lower right. But the VAX arrived in Charlottesville in late 1979. We came to VLA in 1980. This was a big improvement. We got a second VAX, moved on to a convex Unix operating system in the mid-late 1980s. But the whole problem wasn't really solved until ever more powerful PCs, laptops became available in the 1990s. Two miscellaneous items before I close. The crush of observers combined with unfamiliarity with calibration, scarcity of computing resources led to a difficult situation. The scientific staff, we were quite overwhelmed with assisting our visitors on ever slower computing. But calibration is in fact a relatively routine operation. And with the rise of APES and allowing imaging but not calibration at home, a new program started in 1981 to offer calibration for observers. They would not have to come to the VLA to set up their files and do their calibration. Peggy was a key element in this. Dave Wunker, Ina Cole were also involved in this effort. Eventually, the DAs moved to VLBA support once APES started including calibration and people could do all their things at home. And the second and last topic, it was very clear from the beginning that the crush of new users and the rapidly developing imaging techniques, our users needed help in learning these new things. And in 1982, the initial synthesis imaging summer school was held, but this was focused mainly on discussing new techniques. But it was immediately clear from the people who showed up for that meeting that they were not really interested in debating with Larry D'Addario and others about how to do calibration better. They wanted to know how to do calibration at all. And so the second summer school, 1985, in which I was an important player on, was refashioned to focus on training our users. And we've had very successful workshops every 3 years since then. And literally thousands of people have gone through the NRA summer school. So here's a summary. Getting on board the VLA early in 1977 was, for me personally, an amazing piece of good fortune. The array had just passed all others. It was an absolutely exciting project to be involved in. We were all given a tremendous amount of leeway to try to figure out how to use this machine, with observers coming around from the globe daily, new staff being added monthly. It was a really exhilarating and exciting time. The computing issues that others have mentioned and Ron discussed yesterday were indeed difficult, annoying, troublesome, irksome, all kinds of words like that. But these were overcome and the pain has long subsided, thanks to implementation of APES and the rise of personal computers. The bottom line is this machine, which I had nothing to do in design or building, was superbly designed. As Ron pointed out yesterday, did far more than was ever originally conceived. And it was just the greatest excitement to be here. So I said it's not a science talk, but I thought I would just leave with two of my favorite images, 3C449 on the left, nature cover, and of course the iconic Cygnus A on the right. And with that, I'm done.
All right. Well, thank you very much, Rick. We'll open up to questions. As a reminder, either raise your hands or put a question in chat. I've already seen two comments in chat. So Miller, would you like to make your comment about the pipeline?
Yes. The pipeline was very difficult to use. It was partially a failure. Calibration in the pipeline never worked, but imaging did work in a few cases. And in the early 80s, when I was around, we were able to do some successful imaging, especially in H1 observations where you had many channels to do, and you could at least make the images in the pipeline, but it required an incredible amount of hand-holding. And myself and others would sit there and try to moderate the use of the pipeline, and it was a limited success, but it was a great relief when the pipeline did disappear, because it was a very high maintenance operation.
Yeah, Ron pointed out Bob Duquette's summary of the problems with the pipeline. And for anybody here who wants to become a project manager and manage software projects, I really really recommend reading Bob's review. It's not a hostile review. It's a fabulous discussion of why it failed to work as planned.
That's correct, Rick. And I remember Ron Eakers, Bob Jalming, and maybe you were around. We had major discussions, and the day we decided we would never be able to calibrate in the pipeline was very revealing.
Mm-hmm. Yeah, I had actually nothing to do with it. I'm not an H1 person, so I had nothing to do with the pipeline except to be aware that it was in trouble. We probably go to another question, I guess.
Yeah, let's move on. There was a question from Josh Tobin that's been partially answered in the chat about how calibration was done prior to calibration routines being included in APES.
Sorry, what was done?
Calibration.
Oh, calibration. Oh, well, the DEC 10 program, ANSOL, was the same thing as Calib in APES. Basically, I mean, it initially worked in a slightly different way, but the idea was still the same. There's really, this was the thing that Barry brought. It did have a UV range in it, and I didn't have time to talk about this, but my early attempt at self-calibration utilized this capability to limit the UV range of the data used in the solution to allow a primitive form of self-cal, which had spectacular results. Yeah, but no, there's not really any difference there. The real innovation was the development of self-cal, where the concept of dividing the model by an estimate, dividing the data by an estimate of the model led to this antenna-based calibration scheme that we now all take for granted today.
Well, thank you very much, Rick. We do need to move on. If people would like to continue the discussion, there are Slack channels open to continue discussion, as well as there's some discussion going on in chat. So thank you very much.
Okay, I'll stop the share.
Excellent. Our next speaker is Joe Lazio, talking about the 74 megahertz system on the VLA, breaking the ionospheric barrier.
Okay, and sound check, you can hear me and see the correct view?
Yes and yes.
Excellent. Yes, it's a pleasure and a privilege to be able to give this. Actually, this talk really should be given by Namir Kasim, but he could not be here, so I will do my best to convey some of the continuing excitement from the VLA, this time moving downward in frequencies. Okay, low frequency radio astronomy. We heard yesterday Ron Eakers talk about the many discoveries, actually unanticipated discoveries from radio astronomy. But if you look at many of them, they were not at the original VLA frequencies that Rick just described. Indeed, the entire idea of celestial radio emission was down at 20 megahertz. For instance, pulsars were at 80. There was this great string of discoveries, many of them not really at VLA frequencies. And this is another picture, maybe the same picture of Bill Erickson's Clark Lake TPT. There were some really fantastic arrays of substantial collecting area built, but you can see that there was almost as if there was something that happened about the 70s and radio astronomy moved to higher frequencies. Some of the move to higher frequencies was driven by scientific motivations. We heard yesterday about, for instance, molecular emission and atomic physics. Molecular physics drives you to centimeter and millimeter wavelengths. But one of the other aspects is that the early low frequency arrays were often limited to baselines of order a few kilometers. And that had a couple of, well, it had one potentially very important impact, which was that confusion, classical confusion was an issue. It's perhaps best demonstrated by the image on the right, which is an image from the Westerbork telescope in the Netherlands. And what you can see is that the density of sources is becoming so high that it's approaching, say, one source per beam. So there's this noise floor, if you will, that results from all of the faint sources, unresolved faint sources, contributing to a noise floor. And that noise floor can be well above what you would estimate based on thermal analysis. If you go to higher frequencies, well, angular resolution already just helps you, as well as spectral indices tend to help you. So at higher frequencies, you can mitigate this classical confusion. Why were the early low frequency arrays so limited in baseline? Well, here's an illustration actually from the 74 megahertz VLA. The movie that is playing on the left shows it's one field of view from a VLA image. I've tried to indicate these, you're seeing 9 sources, they're spread across the field of view. You can imagine that typical sources are perhaps a degree apart or so. And if you watch the movie for a while, sometimes you'll see that the sources all move in the same direction. That's ionospheric effects over the array. Sometimes, however, they move in different directions. In fact, you can sometimes see the shape of the array appearing up, indicating even higher order phase effects. So the early arrays were kept relatively compact so that the array would be in the regime in which the ionosphere could be considered to be essentially coherent above the array. The consequence of this was, the VLA, it was very easy, or relatively easy, to get to, say, even in the early days, Millijansky sensitivity, arc-second resolution. The original VLA was designed to have arc-second resolution. Whereas by contrast, Clark Lake would have perhaps an arc-minute resolution. Okay, so here's another picture. Pay attention to the one on the upper left. What you can see there is, here's some illustrative array. And if the antennas are closer than about 5 kilometers, the ionospheric structure is more or less coherent over the array. And as it becomes larger, then you get larger phase shifts because of the electrons in the ionosphere. Now, today we look at that and we say, well, that's obviously a job for self-cal. You can, at least it seems plausible that you could decompose the ionospheric phase contribution into an antenna-based contribution, and therefore solve, and today we would say CALIB or the CASA equivalent. Of course, at low frequencies, the phase difference as you move to longer baselines can be substantial. You can see here Namir wrote something like, it's very easy to get pi radians over very short distances. And so as Rick was noting, as self-cal was coming into the fore in, say, the 80s, perhaps early 80s, the obvious question came up of, well, if it works great at, say, 1 gigahertz or at 5 gigahertz, could it also work good at, say, 100 megahertz or something like that? And that led 2 gentlemen to make a modest proposal, which is perhaps we could essentially piggyback on the VLA site and build a large low frequency array. At the time, the concept was that instead of big dishes, it would now have a bunch of dipoles or a set of dipoles I believe it was like at each VLA pad or off to the side of each VLA pad. So it would utilize the same infrastructure, but then there'd be additional dipoles. My sense is that this was perhaps a bridge too far at the time. And therefore, there was this idea of, let's test it out using the VLA dishes. And in the early 90s, 8 of the dishes were outfitted with 74 megahertz dipoles. So you can see a picture here of Namir holding at least one iteration of the dipole. And in the upper, I guess, sort of upper left, you see one of the dipoles it's kind of difficult to see, but you can see it circled there. It was suspended. I'm sorry, is there a question? Okay, it was suspended below the subreflector, and in fact, Bill Erickson was a sailor, so the entire mounting or deploying of this dipole had something to do with the way you also hoist a sail on a boat. This turned out to be this pilot system turned out to be wildly successful, and by the late 90s, as I understand it, largely through the efforts at Namir at the Naval Research Lab, all 27 of those antennas had been outfitted with 74 megahertz, and that 74 megahertz system continued essentially through the 2000s until the start of the EBLA project. And you can see the rather simple radio receiver that was used in the lower, I guess, lower left or lower middle. In fact, what's almost hidden in the upper, the middle up picture is that there are also 330 megahertz dipoles, and the signal transport system could actually handle both. So you could do both 74 and 330 megahertz at the same time. Well, so what was the impact of this system? The impact was that a number of sources suddenly turned into, you could have multiple beams across the source. And so here you see a number of very famous sources. In some sense, it was returning to the roots of radio astronomy, because you could see that these sources, Cas A, right? How did Cas A get its name? It was the brightest radio source, A, in the constellation Cassiopeia. Virgo A, same thing. So a lot of the very famous sources were re-imaged, this time with multiple beams across the source. I won't get into a lot of the astrophysics, but it really showed the power of being able to go to these low frequencies now at extended baselines. In fact, I don't have a picture in here. For a while, we tied in the PyTown link. So there were some actually few arc-second images of Cygnus A made down at 74 megahertz. There was, not only pretty pictures, but here's an example of actually stimulating the entire across the entire field of astrophysics. There was a cooling controversy, how much, and actually it continues today to some extent, how much feedback do AGN provide into clusters? And here you see a combination of a radio image in contours and an X-ray image in the grayscale. And you can see that the radio image appears to fill in where the X-rays are dark, otherwise known as excavated, as if there's an intimate connection. And then some of the other physics, we made images of the galactic plane. So here you see some work that I believe ended up in Michael Nord's thesis. And again, there were a number of students who were trained on this, showing the galactic center at low frequencies. Notable here are the absorption regions in the along the galactic plane or in the galaxy toward the galactic center that are starting to become absorbing. And it's notable, even though we were working down at low frequencies, so the astronomical journal cover that you see here is mapping out, or it's an illustration of how one could map out the cosmic ray electron density through the galaxy. So even though we're working at, say, low radio frequencies, the photons have low energies. It's worth keeping in mind that the electrons generating this, and in fact, in many of, say, centimeter wavelengths, the relativistic electrons have GeV energy. So we're in some sense doing low frequency or high energy astrophysics, even though we're looking at low radio frequencies.
2 minutes, Joe.
Okay, I am closing up. So if you think back to that movie that I showed, self-calibration was a remarkable breakthrough. It worked really well for the bright sources. And what we would say today is that self-calibration is a measure of direction-independent calibration. And some of the early work actually moved toward direction-dependent calibration. There was something that was implemented within Bill Cotton's package OBIT that used Zernike polynomials. And really efforts such as Aaron Cohen and Wendy Peters led to the VLA low frequency sky survey. So here you see a montage of sources, a survey at low frequencies, which remains a very substantial a piece of work and a calibration grid across the sky at low frequencies. I think LOFAR's 2 meter survey is starting to catch up, but it remains a very substantial piece of work with a number of contributions across the field of astrophysics, and it spawned a number of different follow-on projects. Beyond the 74 megahertz, so at the time, there was also this concept from the Netherlands for something called a low frequency array. And there was a consortium gathered together. A lot of the work actually was foundational from the 74 megahertz VLA. So what I'm showing here, the Murchison Wide Field Array, LOFAR, LWA1, which is actually at the VLA site, all of these have in some sense genetic heritage back to the 74 megahertz VLA. We were proving out things that could then go on to be applied or extended in many of these arrays. And then of course there are subsequent iterations even on into the SKA. So the 74 megahertz VLA, it both opened new grounds and then it laid foundations. And I will leave with the final slide. So we had a number of innovations out of the 74 megahertz array, VLA. There were novel discoveries. It was a whole new way of looking at the sky. You can see this 74 megahertz system paper that we published. I think we laid a foundation that then helped the next generation, but we were doing so ourselves standing on the shoulders of giants. So Rick has already alluded to Bill Erickson, had he touched many aspects of it, and Kurt Weiler, while his science was actually more interested in radio supernovae at higher frequencies, his guidance at the Naval Research Lab really helped along the way in many respects too. So with that, I'll close and happy to take questions on any of it, and kudos to the entire team that helped make this possible.
All right. So reminder, put any questions in the chat or raise your hand. I see a hand from Brian Butler.
Yeah, hey, Joe, maybe you or Rick can answer this. You say hardware costs less than 50K. Is that really right? It seems, I mean, maybe it is, but it seems given all the mechanical and electrical bits that it would have added up to more than that.
This is where it might be helpful. I would suspect that well, first off, it's hardware cost, right? Yeah, it's a good question. I suspect that's kind of the scale of maybe one of the proposals that Namir wrote, but I am speculating a bit as to and how much of it was perhaps bought through other funds. So yeah.
Yeah, I'll have to say, I have no idea what the original system cost. As I put into the chat room, Bill and I our first idea was to put a bunch of TV Yagis around each thing outwards. That didn't fly well with management, and probably a good idea we never did it. But that just shows you how we're, groping forward with trying to do this.
Are there any other questions? Brian, your hand's still up.
Sorry, I just didn't put it down.
No
But I
worries.
was going to say, you would never get away with that kind of a plan for a system nowadays. You would have to budget everything out the wazoo, as we all know now.
All right. Any last comments? Well, if not, let's, oh, sorry, Ron, go on.
So I'd be interested in whether you think the current system is a better way of doing it, or are we missing opportunities by having innovative, simple solutions which avoid all the process?
I think for big projects, the new way has a lot of benefits. It avoids a lot of pitfalls. For small projects like what this was, I think it's overkill and it makes it hard for staff and outside people to do creative things. That's just my humble opinion.
Yeah, well, I certainly agree, except that trying to draw the line between large and small is hard. And structures, like once they're given control of large projects, like to include everything.
Well, let's continue that discussion on the Slack channel. Thank you very much, Joe, and everyone who contributed. We're now going to be moving on to Tracy Clark, talking more on commensal low frequencies on the VLA with the VLA low band ionosphere and transient experiment, VLIGHT.
Okay, thank you. I hope you can see my slides and hear me okay. Great. So thanks to Rick and Joe for really starting out and setting a lot of the groundwork here. I'm going to stick to the low frequencies, talking about our VLIGHT system, where we use it for remote sensing from the ionosphere to deep space. And this is really a talk given on behalf of a much larger group of people at NRL and NRAO who've worked within the new infrastructure for building systems on the VLA and prove that even small teams can do this. Let me just, there we go. So you've already seen one of these, but poking through the archive yesterday of scientific memos, I was wondering when low frequencies were first written up for the VLA. So the memo on the left is from Peter Napier from 1982, proposing the 330 megahertz feeds. And on the right is the 1984 memo from Rick and Bill Erickson talking about that 74 megahertz system. So it didn't start in the very early days, and they're not quite 40 years there, but we can celebrate 40 years of low frequencies in a couple of years. Looking at the VLA archive yesterday, actually, I found what is recorded there, at least as the first low frequency, so sub-gigahertz observations. And you can see them here from the 1980s. And in fact, if you look at the project codes, I tracked down AK076 was actually Phil Kronberg, my PhD thesis advisor from Toronto, and Pearl is, of course, Rick Purley. So low frequencies were on and running, and we already heard a little bit about this from Joe Lazio. And in fact, that successful 4P system that Joe talked about operating until 2009 is what was the foundation for building the VLIGHT system. So after the VLA upgraded to the JVLA, we designed at NRL with NRAO a new broadband, low band receiver that came operational in 2012 and is in use for WIDAR. But that presented a very interesting opportunity as well that we took advantage of. Because the P-band system let me see if I can get my laser pointer going here. The dipoles that Joe pointed out for 330 megahertz are up here near the prime focus by the subreflector. That's a separate optical path from the gigahertz receivers that are down here in the Cassegrain focus. So we were able to actually develop a parallel system, we call it Commensal, that records data with these 330 megahertz feeds while the higher frequency observations are going on. So this V-Lite system operates between 320 and 384 megahertz, and it's been operational now 6.5 years, being upgraded along the way from an initial 10 antenna system to our current 18 antennas. We run with a custom real-time defect software correlator. And this system collects roughly 6,000 hours of data per year from the VLA. Not all of it's calibratable, but that's a huge amount of data. And in fact, we have a second system designed on top of this that I won't have time to talk much about, that is a GPU-based fast transient buffer that grabs the data before it goes into the correlator and search for fast radio bursts. So our resolution depends on the configuration the VLA is in, but up to 5 arc seconds. And sensitivities between a few hundred microjanskis to above the millijansky level. So over the past 6.5 years, we've recorded roughly 2.3 million scans, so 40,500 hours of data. These numbers are out of date a little bit. And that has given us 466,000 images, so about 25,500 hours that we've actually imaged. The image that I'm showing here is meant to display the data that we have accumulated. So 90% of the sky that is visible from the VLA has been observed for more than 20 minutes. We saturate this at 24 hours, but in a lot of these red spots, we have not just tens, but hundreds of hours of observing time in individual areas of the sky. So processing of this, as you can guess, requires pipelines. And in fact, the pipeline is very non-standard for a system like this. We have no control over the telescope. So it needs to be functional over a wide range of operational cases. The calibrators, for instance, are chosen by the higher frequency observers without any input from V-Lite. And in fact, it's even more complicated. So going into this, we knew it would be difficult because the P-band dipoles that come through the middle of the subreflector are actually off axis during observations. They're 0.1 degrees pushed off so that the main observer can pick their receiver of interest around the feed circle. What that means for V-Lite is our primary beam not only was unknown because it's not the same as the VLA at P-band, it changes with the receiver that's selected, it's offset from the phase center, and it rotates with parallactic angle. So no one would ever build a telescope like this. It has been kind of complicated to handle that, but I'll show you in a minute what we've done. Our data are flagged, calibrated, and imaged and self-calibrated within a custom OBIT pipeline that we've written at NRL. With the help of Bill Cotton as well from the OBIT package. So in order to really solve our data problems, though, to get our fluxes, we need to map our primary beam. And we had to accumulate significant data, particularly with the upgraded V-Lite system with 16 antennas, in order to compare that data to the Westerbork Sky Survey as a function of distance from phase center. And we found that we're able to map out our own beams in a set of 4 different receiver settings, the LS separate, C plus X, and then the higher frequency together. Note that V-Lite, we're not able to map our own beam at P-band because we don't record while the VLA is doing P-band observations. So we found that the beam has significant asymmetries, and we show a 2-dimensional map here compared to the symmetric beam that the VLA has, mapping out to 3 degrees. So the plot on the right might be more clear. As you go from the phase center, you can see the 4 different sets of beams shown in colors here, and the range of colors are showing us the range of asymmetries in angle here. So we have these now implemented within our system. This is fairly new, March of this year. We've just managed to run through these beam corrections. And that allows us to not only create our database of fluxes, but it's very important for commensal sky survey work as well. So you'll hear in a little while Amy's talk about the VLA sky survey at 3 gigahertz. VLIGHT was designed with being a parallel sky survey to that in mind, which we call VIX, or the VLIGHT Commensal Sky Survey. So on the left here, the snapshot figure, I show our VLIGHT sky coverage. It's a crater map, as I call it. It's about 15 arcsecond resolution, 10 millijansky per beam over most of the sky with craters around bright sources because we're just doing snapshot imaging. By applying this elongated offset primary beam, we're able to take these highly overlapping snapshots and combine them into 3 degree by 3 degree mosaics. As you see here on the right, we have roughly 3 millijansky noise within most of the sky, although there are regions that, particularly around Cygnus A, that are much higher. So all of these VLIGHT images that we have, the regular VLIGHT, the snapshots, and the mosaic images are passed into our SQL database, which maintains basically all the metadata from the observations. It runs source finding. PyBDSF is our version that puts all of those positions of those sources back in the database. And then in our third stage, we run source association, where all of the sources that have been cataloged are matched against those that are already in the catalog for associations. And finally, we cross-match against everything in sky surveys that we've also loaded within our database. So that allows us for really easy light curves, transient searches, as well as external catalog matching. And in fact, we're now running that data again, recataloging everything in VLIGHT and VIX with our new beam corrections to get this accurate flux that we need. So here's where we are now. Thank you. We've got about 10.7 million sources. These are not unique and they're not all real. This shows the sky density of those sources. And I just have a few representative images that I had sitting on my desktop where you can see there's extended structure. The ones on the left are from the regular VLIGHT observations, and the ones over here are from the Commensal Sky Survey observations. So I just want to very briefly touch a few pieces of science that we do. So going back to Bill Erickson, keeping an eye on the ionosphere, that's what one of the main drivers that NRL is interested in for VLIGHT. And back in the 1990s, in fact, Jacobson and Erickson discovered co-rotating plasmaspheric irregularities with the VLA, where they saw these wave-like structures running across the field. And in fact, this is due to the magnetic field sweeping across the line of sight to any radio source that's being observed. And it was discovered that actually the perturbations in the plasmasphere are driven by perturbations in the ionosphere that travel up the magnetic fields that act like equipotentials. So for instance, here, the jet stream is driving those ionospheric perturbations. So using the data from VLIGHT, Joe Helmbolt was able to look at data from 2015 through 2019 and show that these CPIs are primarily driven by nighttime traveling ionospheric disturbances going up into the plasmasphere. The VLIGHT system also gives us the power to go very deep. And so one of the things that the VLA observes a lot is 3C84. It's a high frequency calibrator. Playing with some of that data, we just took a few images we had from multiple configurations and put those together to see what we could get for a nice image. It's a very difficult region. It's an A-team source. It's extremely bright and has extended emission around it. But we were able to make a very nice map of the area of the sky showing many different radio sources in it. And in fact, one of those sources went into a paper by Marie-Lou Gendron-Massalet on the IC310 source. And the final thing I want to mention are the transients. The transient universe is one of the other key focuses of VLIGHT, fast and slow. I very briefly mentioned the GPU-based VLIGHT fast system. We put out a paper earlier this year on the detection of our first fast radio burst. We were not able to localize it yet, but as you heard from Shami Chatterjee's talk, that is one of the main goals of this. And we have a system that now recognizes a fast radio burst and will dump the voltages for localization. We're also able to look at folded light curves for things like this eclipsing binary on a longer time scale with a 26-day period, or even much longer time scale looking at late time emission from supernova and these two galaxies as are shown here. So since my time is running out, I just want to summarize that we've recorded a wealth of data. Our primary beam models are now moving us to the era of accurate fluxes. And we're working towards the quality assurance as well as the processing Epoch 2. Based on all this long foundation of low frequencies, I think the future is really bright for commensal science as well at the VLA. With VLight operating through VLAS, the talks coming up by Casey on real fast and Cherry on cosmic are also going to be very important going forward. The gumballs on the right just show the images covering the sky for our arrays, a bit out of date. And finally, I just want to mention that with the VLight system, we're very interested in working with new students and collaborators. Thanks.
Thank you very much. We have time for one, maybe two questions. And Brian, since you've already asked a question, I'm just going to see quickly if there's anyone else who has a question. I'm not seeing chat or hands going up. So Brian, go ahead.
Yeah, Tracy, remind me, do you make an image per scheduling block, exec block, or is it per scan?
So what we do actually is we load 24 hours of data. We pass over midnight if a project continues, so we don't cut projects off. And then we separate the observations by primary observing band, whatever that receiver is people are using. And so any source within that data block will be combined together into a single image. We do have software as well that allows us to go ahead and go in and make small images in time of that for sources that vary, but our normal observing combines it over the day.
Thanks.
All right. Are there any other questions? Well, not seeing anything in either chat or in hands. I'm going to ask a question in the Slack channel. So we'll continue the conversation there. Thank you very much, Tracy. And we'll now move on to our next speaker. Hari Krishnan will be talking about real-time imaging with large N compact arrays.
Can you hear me? Hello?
We can hear you.
Yeah, thanks.
Perfect.
Okay. So, hello everyone. I'm Hari. I'm a postdoc at the Arizona State University. So I'd like to first thank the organizers for giving me an opportunity to present our work here. So I'll be talking about a real-time imaging correlator that we've been developing that is specifically efficient for large and compact radio telescopes. So it's a collaborative effort, and we have many active members in the team. Jay Stowell from the University of New Mexico, and Matt Kalapnis, who's a postdoc at the Arizona State University, Adam Beardsley, Judd Bowman, who's the PI of this project, Greg Taylor, who's the PI of the LWA project, and Nithya, who conceptualized the imaging correlator, who's now at CSIRO. So here's a broad outline of my talk. So I'll first stick to the basics, starting from the radio interferometry, and then walk you through the direct imager concept and discuss the GPU architecture of this imaging algorithm, and show you some commissioning observations, and talk about the future goals that we have for this imaging correlator, and finish up with a summary. So the motivation for this particular project is both driven by the recent discoveries in particularly the transient space phase at low frequencies, the meteor radio afterglow, the discovery of fast radio bursts, and cosmic ray shower measurements, and so on, which is only driving the already upward trend in radio astronomy, radio interferometers that are driven by the needs for sensitivity, wide field of view, high angular resolution, and wideband coverage. Then, as you know, transient science requires high temporal resolution imaging observations at wide frequency bands, as highlighted by the VLight and real fast systems. So, and the advancement in digital technology has only facilitated this, and we try to leverage this to come up with a new correlator concept that can be potentially be used for upcoming radio telescopes. So coming to the radio interferometry concept, so what you see here is a two-element interferometer, which is the fundamental unit of any radio telescope today that performs aperture synthesis. So here we have two antennas, which are the basic receiving elements that that captures the electromagnetic radiation from the celestial sources, that records the voltages, and these voltage patterns are then correlated to estimate the visibility function, which is basically a sampling function of the sky at the spatial scale corresponding to the baseline of the antenna. So the functional unit, as you can see here, is the correlator, which is conventionally implemented as either an XF or an FX correlator. So in an FX correlator, the voltage series from individual antennas are first Fourier transformed, and we take them to the frequency channels. And for each of these frequency channels, we perform the correlation to estimate the visibility function for every frequency channel and for every equation time. So the correlator itself has evolved through time, starting from analog correlators that were implemented using adders, multipliers, and so on, and then to one-bit shift-based correlators, and then to ASICs, and now implemented on FPGAs and GPUs. And this has been a useful concept that has been able to handle a few tens of antennas in an array. And even through this evolution from the analog to the latest GPU-based correlators, it is increased in computational complexity, but able to handle large operating bandwidths and so on. But as I mentioned in the motivation slide, so we are now looking at radio telescopes or radio interferometers that can have hundreds or even thousands of elements, like the SCA or even the NVLA and so on. So this is only going to increase the complexity of the correlator itself, and that scales as a square of the number of antennas. So in view of that, we have come up with a correlator solution, which we call the E-field parallel imaging correlator, which is a generic correlator concept that is highly efficient for large and compact configuration arrays like the Hera, SCA, EDA, HIRAX, and so on. So it is based on the mathematical formalism called modular optimal frequency Fourier, that is for Fourier imaging. So here what we try to do is use the grid voltages. So we are trying to use the grid the electric fields that are measured by the individual antennas and directly perform a Fourier transform to synthesize the aperture on the fly. So here's a flow diagram that describes how the EPIC works. So we record the voltage signals, digitized voltage signals from the antennas across Fourier transform taken to the frequency domain, and then calibrated for using a feedback correlation algorithm that is not yet implemented, but yeah, that's a concept at this point. So the Fourier domain voltage signals are then gridded on a regular grid, and we take an inverse Fourier transform and square that, and then accumulate to get the final image. So you can see that we are trying to do away with the cross correlation operation that gives you the intermediate visibility products. So without forming the visibilities, we are trying to take the electric fields to directly the image plane. So we've been testing this algorithm on one of the long wavelength array stations that's located at Sevialta National Refuge. So LWA is a compact array of 256 dual polarized active dipole antennas that are arranged in a pseudo-random pattern within an aperture of about 100 meters. The LWA operates in the frequency range between 10 to 88 megahertz. And here's a picture of the LWA Sevialta station. So at the LWA Sevialta, we have a number of commensal systems. So what you see here is a network topology of what we call the advanced digital processor subsystem. So this delivers various products like the raw F-engine data from, which is a Fourier transformed data from the digitized voltages, and beamform data, and then transient buffer node data, which is raw voltages recorded for a very short band with like a few hundred kilohertz over a period of time. And each of these products are delivered to different subsystems that perform various operations like beamforming and even imaging based on the FX correlator and so on. So for the EPIC, we use the raw F-engine data that consists of 12 subbands, with each subbands consisting of 3.3 megahertz of band, which are independent streams. And each of these bands consists of about 132 frequency channels at a frequency resolution of 25 kilohertz. And we get one spectra every 40 microseconds. And this data is delivered to a single node server that consists of two GPUs on which EPIC is implemented. So here's a block diagram of that shows what EPIC does. So the F-engine data are transferred using UDP packets, which are then decimated in frequency. So EPIC is implemented on Python and C++ based high-performance streaming framework called Bifrost. So Bifrost uses a high-level Python language to implement front-end packages that which are then which wrap the backend code which performs the core signal processing operations, which is written in C and CUDA. So inside of EPIC, once the decimated frequency gets into the EPIC, and we perform delay calibration, these delay calibrated voltages are then gridded onto a regular UV grid, and these gridded voltage patterns are then inverse Fourier transformed in 2D. Inverse Fourier transformed in 2D to get two gridded patterns of both the polarizations, and these are then cross multiplied to get the correlation products of the polarization products, and then we perform an autocorrelation removal, which post that we square the images and then accumulate to get the final image. So the raw image frames at the cross correlation, the cross multiplication step is at a cadence of about 40 microseconds. So the first deployment of EPIC this is described in Kent et al. 2019. So for more details on how that's done, you can refer to the paper. And so considering the current computation limitations on the GPU hardware, we further accumulate this 40 microsecond images to about 81.92 milliseconds. So this optimization and subsequent imaging is described in the paper that we are writing right now. So with this architecture, we are able to image the full sky with EPIC at millisecond time scales. So what you see here is a comparison between an image obtained with EPIC and an image obtained with an FX-based imaging, real-time imager called LW All-Sky Imager that runs conventionally. The right panel that shows the Lassie image is at 37.9 megahertz, which integrates about a couple of megahertz of band at a few tenths of seconds. And what you see here on the left is the EPIC image, which is basically a bandwidth integrated image of 1 megahertz at 31 megahertz frequency with 1 second integration. This is only to show the nice correspondence that we get and to show the operational efficiency of EPIC. So what you see here is the galactic center, the 18 sources, Cassie and Cygnus A, and so on. So we are also able to, sorry?
2 minutes.
Yes, thanks. So we are also able to extract light curves or dynamic spectra from specific regions in the sky. So what you see here is the dynamic spectra that is extracted from the images for the source location corresponding to the sun. So the sun was active on this day, and the bright features that you see in the dynamic spectra are basically the radio bursts. So this is an all-sky image, basically a snapshot at 250 milliseconds with a bandwidth of 250 kilohertz at 41 megahertz. So just to show you that we are the bright features are not artifacts. So here's a dynamic spectrum that we extract from an empty region of the sky where there are no sources. So we also perform, for the commissioning observations, we perform simultaneous beamformed observations along with EPIC all-sky imaging. So what you see here on the top right panel is the soft X-ray light curve of the sun, which shows a nice solar flare. And the bottom right panel shows you the type 2 radio burst recorded with the beamformed observation on the sun. And what you see here on the left is two images of EPIC, snapshot images at 80 milliseconds, just before the radio burst and during the radio burst. So this is only to demonstrate the commensality of EPIC. So we also made a comparison of EPIC with WSClean. So we performed the processing on the TBN data, which is the raw voltage data, which is first correlated offline and then processed with WSClean, which is, and that image is shown on the left panel. And we send the raw voltage stream as input to the EPIC, and we get the EPIC images on the right panel. So this shows you clearly how well EPIC is able to perform. And just to note that EPIC images are still raw, dirty images. We have not convolved out the beam and so on. So WSClean involves the cleaning and also probably the white field correction. We don't yet have white field correction in EPIC. So as an upgrade to EPIC, we are planning to add additional features like source tracking and trigger processing, probably from RealFast or even Chime, and to have white field correction effects incorporated into it, and to have a mass filtering and transient detection pipeline. So this is what we call as the Aperture Array Radio Transient Imaging System, or ARTIST, and we've recently submitted an NSF ATI proposal for this. So, so with that, I come to the summary slide. So we have recently come EPIC as a fast imaging pipeline that can image the all sky at microsecond to millisecond timescales. So at this point, the EPIC, as is implemented on the LWSA VLTA, it can process about 3 or 1.8 megahertz of band, depending on the grid size. So the maximum grid size that we are imaging for a single polarization on a single GPU is about 64 cross 64. And we also have plans to upgrade the EPIC to ARTIST for transient detection and give it as a whole package for the community. And the ultimate goal for EPIC on the LWA is to increase the bandwidth performance to about 20 megahertz and at a higher time resolution than 80 milliseconds, probably achieve the 40 microsecond itself, and at a larger grid size of 128 cross 128 for to cover the entire band. So EPIC is available at this GitHub site. So anyone who wants to use it, or you can actually visit that. There's documentation on that, and we have a lot of memos and on the development and so on. So I'll take questions or comments, and thanks.
Thank you very much. Let's thank Hari. There's a question from Shami, and I think it's the only one we'll have time to do live. The ARTIST flowchart showed RFI mitigation after dedispersion. Why was that choice made rather than going the other way around?
Okay. So this was just to show what we wanted to have on ARTIST. So there's no specific route that was defined for this purpose. And I think dedispersion itself sort of takes care of part of the RFI problem, because you expected RFI, most of the RFI to be a 0 DM, right? So.
All right. Is there any other quick question we can have? It seems like Shami wants to have a longer discussion with you in Slack about this, because he says that the 0 DM thing compounds the problem. So I think that's something worth having a Slack discussion, and I'll also pose a question to you in Slack as well. So let's thank Hari again, and we'll move on to our next talk. So our next talk is continuing to go in the fast regime, finding fast transients with VLA real fast by Casey Long.
Okay, how does that look, everyone?
You're good.
Thanks, Greg. Okay, well, it's a real pleasure to be here and to speak at the VLA 40th. A lot of great talks, and it's really an honor to have a chance to present something that we've done to sort of work commensurately and enhance what the VLA can do. So if there's one sentiment that I appreciated from earlier comments, it's that we really don't know what we're doing, and somehow that makes all things possible. So I think that's also true for what we're doing with the real fast system at the VLA. So I'll try to share a bit of that story and some of the science that we're excited about doing real fast. So before I dive into that, I just want to highlight that this is a project that was done with major contributions from the NRAO directly, and I've listed their names here. Other collaborating institutions include West Virginia University, Asia A, and JPL. But I want to particularly highlight Brian Butler and Paul Demarest, who were there from the beginning and have contributed continually to the operations and the management and the planning for this instrument. So just special call out for them. So let me go forward here and let's see here. There we go. So what is real fast? So real fast is essentially a transient search backend at the VLA, specifically focusing on fast transients, so millisecond timescales. The features that make it novel and we think it make it particularly scientifically impactful are its ability to perform real-time processing of data. And in particular, we're talking about millisecond imaging of the VLA. So we have a pipeline which performs dedispersion to include searches over a wide range of dispersion measures, including fast radio bursts, as I'll describe. And then after dispersion, there's an imaging step where we look for sources in these millisecond images. And another important aspect of the operation is that it's commensal. So it works with a fast timescale search, but also allows the primary slow cadence visibility data to be recorded. And then fourth point is that we have integrated this because it's a real-time system. We can also integrate it with automatic alert systems and data quality classifiers based on machine learning algorithms that allows us to do very rapid triggering of other facilities. So responding to things that are detected at the VLA, which is definitely a burgeoning and active area of technical development in many astronomical facilities. So a little more detail about where we are as a project. So RealFast there's a system diagram here. It's essentially a GPU cluster that is shown on on the bottom. Let's see if you can see my cursor here. Oh, I can't see my cursor, but the bottom tier here shows the transient detection system, which is a cluster of GPUs, which taps off post-correlated data from the CVE. So visibilities are generated at a millisecond cadence. Within the CVE, we have an access to that memory space, and that can be distributed to the dedicated GPU cluster that's in the west chamber of the correlator, west chamber correlator room. Whereas within the CVE, there's a second time integration, which produces the slow visibilities that go out to the archive for standard data product in the archive. Within that parallel system, we have our own web system, web server that serves out candidate plots and lets us do our data management. That is then eventually integrated into the standard archive also, which is still in development. The hardware is all installed. The basic software is working as expected and has been for more than a year now, actually. We are regularly searching 10 millisecond cadenced visibilities in the L through X bands. When the correlator is configured in continuum mode, it is essentially standard to produce this fast cadence visibility that's distributed to the GPU cluster. All of that is producing these candidate plots that we have an automatic classification system for based on this fetch classifier, which is a convolutional neural network that allows us to have a rapid data quality check and integration with alert systems. All of that can be produced within minutes of the observation. The bottom plot gives you a sense of how much observing time has been accumulated. This is a somewhat old plot, so these bars are continually going up as the system observes commensally with these bands. So I'm going to dive in a bit on fast radio bursts. You heard a bit about this yesterday from Shami's talk, but I'll just recap it because it's a critical aspect of what RealFast is interested in doing. It's the physical let's see. So phenomenologically, it has often been defined as a highly dispersed millisecond transient. Because it's highly dispersed, we infer that it comes from outside of the galaxy. Because there's too much electron column density to be associated with our own galaxy. It must be a significant column from outside of our galaxy. That definition is becoming a little harder to work with because we now know that there are FRB-like emission that can come from magnetars in our own galaxy. And also we actually have localized so many FRBs outside of the galaxy that we can actually define specific luminosity limits that define what what makes the process special. So another definition is that it has a radioluminosity, spectral luminosity of 10 to the 29 ergs per hertz. They occur at that energy level. They occur at a rate of about 10 to the 5 per cubic gigaparsec per year. So that's a volumetric event rate. We know that some of them repeat, maybe all of them repeat. We don't know that for sure. And we know that there are, of course, hundreds of events that have been published, including about 500 recently published from the CHIME FRB telescope in Western Canada. So physically, what's exciting about FRBs? We don't have to dive into this in too much detail, but the big questions which were raised initially and remain open is, what are they and how can we use them? So what are they? There are still many viable models for what produces the FRB emission. And in fact, instead of converging on a single model recently, I would say there's been more of a divergence because We have examples. There's one FRB that's been associated with a globular cluster, which implies it has a very old stellar environment. And then there are some that are associated with active star formation regions, which implies they have a very young stellar environment and formation process. So we don't really know what makes FRBs, and that is a very active field of research. Second point is, how can we use them? So we know that as this radio signal propagates through space, it's modified through dispersion, but also scattering and other processes. And that gives us incredible power to infer what's happening in those media. And so that is potentially the long-term goal of the field, is to apply FRBs to research of the CGM, IGM, ICM, and that potentially cosmology. So we'd like to see that grow in time. I see lots of chats. Please let me know if I'm need to do anything for those chats, but I can't see the chats.
You're good, Casey. You're good.
Okay, thank you, Greg. As a quote, maybe, in this audience, I could float this by and see if it's correct, but I believe Jim Condon made the point that there's nothing less interesting than a radio source. I think that's I think it's a true statement. I think I agree with that. And of course, his point was that when you associate radio sources with some other counterpart, you can do so much more, right? So if you know a distance, its luminosity. If you know that it lives in a particular kind of galaxy, you know that it's potentially associated with, say, star formation or an AGN. That's also true for FRBs. And in fact, some FRBs are associated with persistent radio sources, which we're trying to understand. Potentially, those could be a unique vantage on the FRB phenomenon. And it may be totally different from what we traditionally think of as the standard population of radio sources that are out there in the universe. Maybe not an AGN, not a star-forming galaxy, but in fact, a whole different kind of source, such as a baryonic emission, but extremely luminous. So associations are critical, and that's why VLA and the real fast system are an important aspect of understanding this phenomenon. So to demonstrate that, again, this is something that we heard a bit about yesterday, but just want to highlight the point that the VLA made one of the earliest big breakthroughs in interferometric localization of FRBs. So this is the FRB 121102 discovery, and it was made with VLA and then a prototype version of the real fast system. So the search was conducted through dedispersed visibilities. The burst was localized to arc-second precision, and then it finally was associated with both a persistent radio source, which we can now characterize its spectrum, and also a host galaxy, which we can measure its optical spectrum and get a redshift. So all of the sort of phenomena that we think of as brightness, or as we think of as flux densities, can now be made into luminosities and energies and much more physically constraining things.
Is he a little bit 1.5?
Sorry?
1.5 minutes.
Oh boy, okay. So we're continuing to push forward, and I will just highlight the fact that the real fast system continues to operate commensally and has made many new FRB discoveries and detections. So in some cases, we're the first ones to see it. Some cases, we're finding ones that have already been found. But here's a sort of a slide, little postage stamps of all the FRB discoveries. And the point here is that the associations are varied, so again, there's not a convergence into a single model, but there's a divergence, and that means that there's great scope for future discoveries. And a couple examples are not shown here is FRB 2011-24A, which is a paper that's on the archive just recently, and also there's one more that is in prep, which is not yet complete, but will be soon. And so I'll use my last minute to highlight some of the other aspects of the science we're doing with real fast. So one is this rapid triggering system. So we've teamed up with a group that's running a system called Guano, which is a rapid triggered swift observing system, where we just send them these VO event triggers that define a pointing location, and they can rapidly slew the telescope, or they can dump data for analysis. And that's been demonstrated in this paper by Aaron Tovavo. We got Swift to repoint within 32 minutes of an FRB candidate event. Turned out to be not a very good event, but it was actually a terrific demonstration of what can be done with VLA as a triggering system. And we have also a few sort of non-commensal discoveries where we control the telescope. We can do primary science, which is like deep imaging at the same time as we search for FRBs. And that's something that has been published in a couple of papers, and some are in prep. And then my last slide is just, I'll note that there are some commensal galactic science applications, including we found the galactic center magnetar, which is well known, but nonetheless kind of exciting that someone was observing for their own purposes the galactic center, and we found impulses from the magnetar. Great demonstration of the completeness and efficiency of the search engine. There's also an unidentified Fermi source in which we found pulsations, and we're trying to understand exactly what those correspond to, what the nature of the source is. And that's a paper in prep. And finally, this is a map of all the pulsars we found during VLAS. They're shown in red, and the pointing locations of VLAS for this particular epoch are shown in blue. And as you can see, we're also finding lots of known pulsars. And that again demonstrates that things are working as expected, and that there's potentially interesting things we can say about the spectral energy distribution of pulsars through this commensal application. So I'll leave my title slide up and just highlight the fact that FRB science is growing rapidly. There's lots to do. Commensal data analysis is really valuable, as Tracy highlighted. VLight is doing great stuff here too. And I want to just applaud and thank the NRAO for taking on high-risk project like this. It really, I think, helps keep the VLA active in new fields of research, and I hope to see that continue in the future. Thank you.
All right, let's thank Casey, and then I'll open it up to questions. We actually already have one question from Joan Roble. What are your running costs? I'm guessing operating costs.
I actually don't know. Maybe Brian Butler can comment on that. I think there's power for the GPUs. We don't operate 24/7 because it's commensal, and only some modes are passing data through the system. So we're probably operating maybe a quarter to a third of the day on average. But I don't know the power budget. That's probably the biggest operating cost at this point. The archiving group is also working with us to store data, and there probably is some running costs for that.
Yeah, and at some, well, Emmanuel could speak to this better probably now, but at some point NRAO will take over the operations of RealFast, and that will be some person power. But currently most of the operation is done by Casey and his collaborators. So it's pretty low. It's pretty low operational cost really for what is coming out of it.
Excellent. Are there other questions? Time for one more. All right. Again, in the interest of time, I will ask my questions on Slack.
Thanks.
All right. So we are now technically moving from session 5 to session 6, even though there's no break between them and no change of chairs. So we're going to be starting with for the radio surveys, we're going to be talking starting with commensal interferometric SETI search with the VLA using Cosmic by Cherry Young.
Hi, can you hear me okay?
You're coming in loud and clear.
Okay, nice. I'm just sharing my screen. It is working?
Perfect.
Great. Thanks for the introduction, and thanks for the opportunity of being here today. Happy birthday, VLA. So today I would like to talk about the opportunity, a new opportunity, in fact, to conduct commensal interferometric SETI search with the VLA using the COSMIC system. So in the last few years, the Kepler mission has discovered thousands of exoplanets. It is now estimated that 1 in 5 stars has an exoplanet orbiting the so-called habitable zone, where water exists in liquid form. So that means overall there are likely billions of Earth-like worlds in just our galaxy alone. With the advancement in technology on our own Earth, there has been no better time than now to conduct a large-scale search to find life elsewhere in the universe. This is what the talk is about, specifically the search for extraterrestrial intelligence, a field of research also known as SETI. The goal here is to look for technosignatures, which are signatures emitted by other advanced civilizations. Technosignature is analogous to a complementary research field in the search that search for biosignature, which are things like molecular lines like water. So what does technosignature look like? In the plot on the left, I've shown an example of the Voyager signal, the Voyager spacecraft detected by the Green Bank telescope. So what we can see here is that a very narrow band signal and is drifting in time and frequency as a result of the differential acceleration between the transmitter and the receiver on Earth. So it is generally believed that this could be a good example of what SETI signal could look like from Earth. Narrow band and drifting in time. So here we are proposing a SETI search with the VLA, and our project is named COSMIC, which stands for the Commensal Open Source Multi-Mode Interferometer Cluster. We've designed this project with the main goal of SETI search in mind, but you will see that COSMIC also has the flexibility to support other types of research. The COSMIC team is shown here, and it's grown a lot in the last year or so. Researchers, including 3 postdocs and a number of students, undergrads, PhDs. They are in Toronto, Alabama, Penn State, and Manchester, UK. In addition, we collaborate closely with scientists from the NRAO. Our main liaisons are Paul Demers and John Cooper. But also a number of other technical staffs join our weekly meeting from time to time. So we have a great support from the NRAO. Now, the idea of SETI search with the VLA has already been popularized in the movie Contact. So why is it such a good idea, and why are we doing it now? There are 2 main reasons. One is the large instantaneous field of view of the VLA being an interferometer compared to a single dish radio telescope. So this cartoon is just showing how a primary observer of the VLA might be looking at a pulsar, for example, but because of the small antenna, the VLA has sensitivity to a wider instantaneous field of view represented by the green cone. So what we can do, in fact, is to form some additional coherent beams represented by the blue cones that are pointed to other stars in the background at the same time to monitor those. And effectively, it's like having multiple telescopes observing at the same time. The second novel aspect of our project is the ability to conduct commensal observations 24/7, piggybacking on all VLA observations. So we have already heard from Casey and Tracy about how good commensal observations could be. In this VLA data flowchart, I've highlighted the actually, move this box here. I've highlighted the COSMIC related new components in green. So we can see that digitized data from the VLA antenna will first be amplified, and then the fibers will be split before sending to WIDER. And now a duplicated data stream will be sent to a dedicated COSMIC digital transmission system and converted to Ethernet. So as I said, the main goal of COSMIC is to conduct SETI search, and we'll have our own GPU cluster for that. But the nature of multicast Ethernet technology means that COSMIC also has the flexibility to support other potential commensal users. And we've been in touch with the RealFast and the VLight teams already. But I want to say, if you have interest in collaborating with COSMIC, we'll be very happy to start a discussion about that. Okay, so I already mentioned the commensal observing capability, and this is really a game changer in terms of SETI search sky mapping speed. So to better illustrate this point, I've made a plot to show the sky projections of the stars observed already by Breakthrough Listen so far with the Green Bank telescope, the green points, and the Parkes telescope, the red points. And the corresponding plot on the right shows the unique number of stars observed as a function of time. So you might have heard of the Breakthrough Listen Initiative program, and it has really been a key driver for SETI research in recent years. And so far, Breakthrough Listen has observed of the order of 1,000 stars with Green Bank and Parkes, as shown in this plot here. And that is really a big step up from previous research, but 1,000 is still a small fraction compared to the total number of stars in our Milky Way galaxy. So here we're actually commissioning a sister interferometer SETI survey with Meerkat, very similar to what we are proposing for the VLA. Our plan with Meerkat is to form 64 coherent beams at any given time, and our simulation shows that with Meerkat, we will achieve 1 million stars in about 2 years time frame. Now, COSMIC at VLA will have an even higher sky mapping speed, mostly thanks to the VLA Sky Survey, particularly the third epoch, which is expected to take place in 2023. So using observation log from our VLite colleagues, special thanks to Tracy, we created this map, which shows what COSMIC would have been able to observe if we were operating during the second epoch of VLAS, actually just half of it, I think. And so if we scale that to the same time frame, we can see that with the VLA, we can observe almost 100 million stars in roughly the same time frame, which is really a lot. Although I have to mention that the sky scanning mode of VLAS also mean that the VLA effectively spend less time on any given position. So it comes out to be a bit less sensitive than Meerkat. This is a plot made by one of my students, Leo Risked, with which he compared the figure of merit of previously conducted SETI searches. And so he looked into the sky coverage and the observing frequency for any given SETI search project. And he has color coded them with 3 levels of sensitivity, the red being the highest sensitivity, those that can detect an Arecibo-like transmitter out to 75 parsec, yellow is medium sensitivity, those that can detect Arecibo out to 25 parsec, and blue is lower sensitivity, Arecibo out to 5 parsec. We can see this highlighted here are some of the earliest SETI searches, and those began in the 70s, the 80s, and they tend to have lower sensitivity, although they were state of the art back in the days. And they only span a very narrow observing frequency band, and actually looks like just a line here, but just very narrow. Now, the Breakthrough Listen program with Greenbank and Parks, they have those projects, they have really improved on the sky coverage and the frequency coverage, as well as sensitivity. But with Meerkat and the VLA, they are really both on top of the plots. They have the best sky coverage. The VLA project in particular will open up frequency ranges that nobody has ever looked for SETI signals. Meerkat, as I mentioned, will have better sensitivity, allowing us to reach to large distances. Last year, we've deployed a test system for COSMIC in Socorro. As you can see in the photo on the left, the system is designed to interface with an eVLA test rack that effectively emulates the VLA digital fiber optic interface. COSMIC has meant some delay in accessing the equipment, but earlier this year, we have successfully received data across a 2 gigahertz bandwidth, as shown in the plot on the right, which is a proof of concept that our front-end FPGA prototype is working as expected.
2 minutes, Cherry.
Okay, thanks. So from the FPGA, data will be sent via multicast Ethernet to our dedicated SETI GPU cluster. In the GPU cluster, we'll be further channelizing the data to 1 Hertz resolution in order to detect this very small Doppler drifted signal. We'll be forming beams to stars within the same field of view, and this beamform data will be then SETI searched via the Doppler drift algorithms. And we are also actively looking into machine learning algorithms to search for the potential SETI signal. Here is an overall timeline of the COSMIC project. We first secured seed funding in 2019. And I mentioned that earlier this year, we have successfully received a simulated VLA data stream. And we have also the amplifier that we have suggested has just been approved by the NRAO. and we have submitted procurement for the bulk of the FPGAs. So on the programmatic side, we have signed an agreement with the NRAO earlier this year, and we are now working on an NGVLA community study, basically to explore scalability of COSMIC to the VLA, to the NGVLA. And we are very excited to welcome our new postdoc, Savin, and he's actually a joint COSMIC vLite postdoc. And one of his first job will be help install the hardware that we have purchased, all the FPGAs, and hopefully by early next year, we'll have first light with the full relay array. And then we'll move on to commissioning the GPU correlator. And we are very excited to work in partnership with the vLite and the RealFast teams. And the West Chamber will also be upgraded to accommodate these new hardware. And the plan is to be fully operational in 2023 and to have maximum overlap with the VLAS Sky Survey. Well, I'm running out of time, so I just want to mention that we are working on this community study award with the NGVLA program. Obviously, NGVLA is going to be very sensitive, and we would love to conduct SETI search with the NGVLA as well. And we are happy to get support from the NRAO to look into the scalability of this project, and we are working in collaboration with Evan Keane in Ireland. Okay, this is my last slide, just a summary of the COSMIC project. On the strategic development, we have established collaboration with the NRAO, vLite, and RealFast teams, working on the NGVLA community study. And we are very keen to hear from the VLA community if you might be interested in the multicast Ethernet data subscription. On the technical side, we have ordered the FPGAs, amplifiers approved. Overall, we are meeting COVID adjusted schedule. And we're also very happy to say that the amplifiers that we are deploying is actually bringing an improvement to the overall VLA power level. So it's great to also improve VLA through this project. And finally, on the science side, the team is rapidly ramping up effort on the software development. We are using Meerkat as a test bed for the beamforming and the SETI search algorithms. And we expect to, we hope to start COSMIC by 2023. And with that many stars, we'll really provide the best constraint on the existence of extraterrestrial intelligence. Thank you.
Thank you very much. Let's all thank Cherry, and I'll open it up to questions. So I do have a question myself. When you're talking about the number of stars that you could reach, I'm confused because as you pointed out that VLAS, for instance, has very little time on the sky. So is that just, stars within a certain volume, or is that within a certain sensitivity?
Yeah, so shorter observing time. Well, yeah, so it's VLAS is scanning the sky, so effectively spend less time on a given point. So if you use the radiometer equation, it comes down to a smaller sensitivity. But I mean, in terms of SETI searching, we don't really know if we don't necessarily have to integrate down in time. We do have to have the time. We do have to have enough time to see the drift. For example, if the signal is Doppler shifting a lot, we do need that amount of time to actually see the signal coming through. But otherwise, we don't necessarily need to integrate. So if we don't, if we're having a multi-pass survey, so for example, coming back to the same patch of the sky another day is just as good as looking at it for a long time consecutively.
All right, and there's one more quick question from Rick. Also say, Steve Myers points out the VLAS spends 5 seconds essentially on any point in the sky equivalently per epoch. Rick says, I presume you're seeking NSF funding. What's the status of this?
The status of what?
NSF funding he was.
Oh yeah. So earlier this year, we put in an NSF MRI proposal to fund some of the GPUs. Unfortunately, we didn't make it this time, but we will look out for other opportunities within NSF or perhaps other funding resources to, to pay for the equipment.
All right, excellent. And remember to continue the conversation on Slack. Thank you very much, Cherry. We're now going to move on to our next speaker, which will be Amy Kimball, talking about mapping the radio sky with the VLA, which must be a lot of work to do in 15 minutes. So Amy, we can't hear you.
Yeah.
Perfect.
You're seeing my screen though, right?
Yes, your screen is good.
Okay. Here we go. Yes. Thank you for pointing out, Greg, that this is a pretty tough topic to cover in such a short amount of time. So right ahead of time, I want to say that I'm going to be talking specifically about wide field surveys, partly because I had to choose, something, and wide field surveys, so basically all sky, are kind of my bread and butter. So I wanted to kind of give a bit of historical context because this is for the VLA's 40th birthday. But I do not have quite the depth of knowledge of some other folks like Rick, who have been at the VLA for longer than me. So please, just be a little patient with me. But I am going to give a little bit of personal notes where it seems relevant. So I want to start by saying, this is what the sky over Green Bank would look like if we could see with radio eyes, if our eyes can see in radio. This is not actually an image taken with the VLA. This is an image taken with the 300 meter original Green Bank telescope at about 5 gigahertz. And Jim Condon was the principal investigator of the survey that produced this. So as I said, I'm gonna start with a brief history to sort of explain how the VLA's legacy sky surveys came to be. So in the paper about that introduced one of the legacy surveys, it was pointed out that from 1988 to 1990, 3% of VLA science time was used to do snapshots at 20 centimeters. So it seemed like it would be a good thing to produce a survey that would make this frequency, this wavelength, available for radio astronomers and astronomers worldwide. So in 1991, there were actually 2 separate proposals that came in as standard principal investigator proposals to do wide field sky surveys at 20 centimeters. So these were actually proposed separately for slightly different amounts of time and depth, and in 2 different configurations. And so they were sort of competing with each other for time. So the referees at the time strongly supported the idea of doing a sky survey with the VLA, but the question was which one of these should be done. There were some test observations performed over a small area of sky twice, and a special panel was convened to hear from both of these teams, and that panel was led by our own Fraser Owen. So a recommendation was made to the NRA director, who was Paul Vandenbout at the time, to actually perform 2 surveys with some slight variations were made to the 2 that were suggested. So one survey was to be conducted in the D configuration and using D North Sea for the furthest south part of the sky, and that would be extended to go as south as the VLA could go, so to minus 40 degrees declination. And the second survey would be done in a larger configuration in the B config, and the area of sky would be focused on the part of sky that would match where the Sloan Digital Sky Survey was going to be observing. And so so these 2 were going to be done. And also there was a lesson learned after this. So apparently there were some complaints from the community that these 2 surveys were using a lot of the observing time. And so partly as a response to that, the director instituted a large proposal review committee. So that was when that idea originally came about to do such a thing, to basically focus specifically on very large proposals that came in, so they could be reviewed sort of separately, especially. So here's introducing the two legacy VLA radio sky surveys that were done in the 90s. So they were both performed at the same frequency, 1.4 gigahertz. So one was the NRA VLA Sky Survey, NVSS, and the other one was the clever acronym FIRST, standing for Faint Images of the Radio Sky at 20 centimeters. So they were done in the two different configurations, and the difference in resolution was about a factor of 10, and they had slightly different depth. So for the NVSS, which was the lower resolution survey, because it was lower resolution, it had much better sensitivity to low surface brightness, which would result in a better, more accurate estimates of the total, or measurements of the total flux density of sources. And because it had a larger field of view, the survey could be done faster. First was done in the larger configuration, so it had a higher angular resolution. So it was able to go deeper because you didn't have to worry so much about the confusion limit. And because it was high resolution, it would get better estimates of small scale source structure and positional accuracy. And the image is just showing the different areas of sky covered by each of them. So here's just some really arbitrarily chosen, just one example of science that was done with each of these. There's like thousands and thousands of papers, so I just kind of chose to. So on the left is an example of a paper showing that bent radio sources, these are known as wide angle tail sources, are signposts for galaxy clusters. So these sources were identified and followed up to determine that there's identifying the other galaxies that were members of these clusters. So it was a way to identify galaxy clusters. On the right is one example from the NVSS, which this was the first really large study of the famous far infrared radio correlation, which was done by combining NVSS with IRAS and the infrared. And this one is particularly near and dear to my heart because the far infrared radio correlation was actually the subject of my general exam in graduate school. So FIRST and NVSS are still used by astronomers many decades, many papers a few decades later. And Ron Eckers yesterday also showed us just the development of VLA data over time and its use by the wider community, not just radio astronomers. And one of the ways that radio astronomers opened up to astronomers who are in other fields and are not black belt radio astronomers was through these sky surveys that made data available all over the sky without having to do all the complicated calibration and imaging individually. Of course, a lot of complicated calibration and imaging was required by the groups that did these surveys. And so I'm not going to talk about that. I recommend people who are interested to look at the papers because these were really the first incredibly large projects on the VLA that had to do all this calibration and imaging that we've heard about with self-calibration and so forth. And so just as one example of one of these papers that cites both of these surveys is that, I'm going to shamelessly self-promote. So this is actually the topic of my PhD. So this is the paper that made up the main part of my dissertation. And this is actually what brought me into radio astronomy, was this work. So I used NVSS and FIRST and a couple other radio surveys combined with the Sloan Digital Sky Survey to basically create a catalog of millions of extragalactic objects where I could study their properties and how the properties compare to each other. So I spent the bulk of my dissertation basically making multidimensional histograms and seeing how different properties correlated with other properties. And once in a while I still get an email about this catalog and people wanting to use it. So I'm kind of proud of that. So one of the things in particular that I did was to use the data from FIRST and NVSS to create a way to measure morphology of sources in an automated fashion. So that works like so. So here's an example of how the same area of sky might be seen by FIRST and is seen by FIRST and NVSS. So on the left is an example of images from the first survey, and you can see it's higher resolution. You can see some fine scale structure and some of the sources that appear to be a single source in the NVSS. you can see that there are actually, two components, so double lobed sources. But on the other hand, the NVSS, again, it measures more accurate total flux density because it's sensitive to larger scales of low surface brightness emission. So you can also see that in NVSS, there's some sources and some emission that's visible that FIRST does not even see because it resolves it out at high resolution. So we're really, these two surveys, I think some of the power of these two surveys comes not in sort of, the competition of them, but actually combining them together. And so here's just a little graphic that I actually used in my dissertation to show how this works. So each of the surveys teams provided catalogs with measurements of the sources and showing the measurements of the flux density and the peak flux density. And that allows you to combine that data to get an automated estimate of what the morphology of the source looks like without even having to look at the images. So you see my mouse here?
You do. 2 minutes, by the way.
Okay, I'm gonna zoom in. Oh, okay, thanks. So basically by comparing the amount of flux density measured by NVSS on a large scale to the amount of flux density measured by FIRST on a smaller scale, you can automatically determine sort of sources that fall in these different morphology categories. And wow, I must be going really slow. So I'm going to skip some stuff and talk about the VLA Sky survey. So there was the VLA was upgraded with a lot of new power. So much larger bandwidth, a new on-the-fly mosaicing mode, which looks like this. So antennas are scanning across the sky while taking data. Here's an example of that shows an instantaneous field of view for while we're doing basically snapshots as we're moving. So the very first project to use this on-the-fly mosaicing mode, I wanted to give a special call out here, is the Caltech NRAO Stripe 82 survey. So this was sort of demonstrated that this method worked and how it could be used. And so this was a couple decades after FIRST and NVSS. And so the time was ripe for a new all-sky survey with the VLA. So there was a call for white papers, which were reviewed by an independent panel and approved by the NRAO director, Tony Beasley. So here's the new VLA Sky survey that we're now performing. So it's the highest spatial resolution all-sky radio survey to date. As Steve pointed out, it's equivalent 5 seconds on source. It's being done in S-band 2 to 4 gigahertz with an angular resolution of 2.5 arc seconds. Half of the observations have been completed, and in September, we're going to start observing the next round of observations. So can I skip this? Okay, so here is the first ever image that was created for the VLA Sky survey, showing the instantaneous field of view here in a 1 square degree image, and the resolution element as just a couple of pixels on my screen. So in this very first image, if you zoom in various areas, you can see that there's some really interesting sources just in the sort of randomly chosen image that happened to be the first one produced. So here's a nice bestiary of various very interesting sources from the VLA Sky survey that I would believe was produced by Brian Kent. And I wanted to just end with some recent science highlights. So basically science that's already been coming out of the VLA, and this is just an example of some of my favorites. So comparison between VLAS and FIRST helped identify radio quasars that were radio quiet and then decades later became radio loud. Identification of transients is really the bread and butter of this survey. And Heinz Andernack has been working with students to look at the images and basically identify previously unidentified very large radio galaxies. And so that was very whirlwind. And I'm gonna end there and just point people to these web pages if they want to know more about this Sky survey.
Thank you very much, Amy, for that. As you said, having to be very brief on that, all that great stuff. Are there any questions we have? I will ask a quick question, not seeing anyone. So given that we will have VLAS and we'll have NVSS, can you see, is there the sum greater than the parts going to be basically be able to be applied to those, even though they're at different frequencies? Or are we sort of missing out on too much low surface brightness stuff for the sum being greater than its parts?
Both of those things are true. So VLAS is even higher resolution than FIRST, so it's missing out on the large scale surface brightness as sort of FIRST did compared to NVSS. I think maybe the resolution and depth of NVSS and VLAS is so different that I think it will actually be possibly it'll be easier and to combine VLAS and FIRST than VLAS and NVSS, but I wouldn't discount any of those combinations. So I think also they're at different frequencies, so you can get spectral index information.
Excellent. And again, we can continue the conversation on Slack. Casey Law pointed out how FIRST and VLAS together helped identify orphan afterglows, and a couple of other things that are going on in the chat as well. So thank you very much, Amy. And we'll be now moving on to a merger-driven explosion discovered in the VLA Sky Survey by Dylan Dong.
All right. Can you hear me?
We can hear you.
Great. So
hi,
everybody. Excellent. Yeah. Hi, everybody. I am Dylan Dong. I'm a grad student at Caltech, and my thesis is about searching the VLA Sky Survey for transients. And so today I'm going to be talking about one particular transient that has been fun to work on for the last few years. But before I get started, there was some talk yesterday about serendipity. And I was thinking about it while I was putting together my slides. And I think that one way, and even though you can't anticipate serendipity, as mentioned, you can try your best to make it happen. And one way to do so is through blind searches of large data sets. And what I mean by blind searches is really loosely constrained and open-minded searches. And I'll present this talk as an example of this. So the large data set in question is the VLA Sky Survey, which we just heard about from Amy. And I won't say much about it besides that it's covering greater than 80% of the sky. Here's just a scatter plot of sources from the catalog that I've extracted in epochs 1.1, 1.2, and 2.1, covering about 34,000 square degrees. And the transient in question in this talk was identified in a search of epoch 1.1, the first half epoch of VLAS, relative to the first survey that Amy also mentioned, which is started in the 90s. And here you can see the overlapping areas, first in purple and epoch 1.1 in the faint green background. So this transient, VLAS transient 1210 plus 4956, is located, at those coordinates. And panel A shows the image from first at that location on a scale of a few arc seconds. And as you can see, there's nothing there. The 3 sigma upper limit is 0.41 millijansky. But in 2017, 20 years afterwards, there's a 2.7 millijansky source that appeared at that location. And so the central theme of this talk is a mystery, what caused this transient. And in order to figure out what caused this transient, I think that the first thing we have to do is to look for contextual clues. So the first clue is that, of course, the source appeared sometime in the 20 years between 1997 and 2017. And if that were the only thing you knew, and this is what you can get just from the discovery survey and the reference epoch, if that were the only thing you knew, then you wouldn't really be able to say much about the source. It's a source that appeared sometime in the last 20 years. But something else that's really important with VLAS is that it has sub-arc second localization of these sources. And so we can use that location information to get a lot of really important contextual clues. And so here's the location of this transient. It's sitting on this galaxy, which actually is scarily similar to the LMC, except it's located at 150 megaparsecs. The stellar mass is almost identical. LMC is 10 to the 9.2. This is 10 to the 9.3 solar masses. The star formation rate is 0.3 solar masses per year. LMC has been forming something like 0.2 solar masses per year for the last 5 gigayears, plus or minus factor of 2. The metallicity of this galaxy is quite a bit higher than the LMCs. It's about 80% of the 80% of solar compared to 0.2 solar or so for the LMC. And importantly, this transient is not located on the nucleus of the galaxy. And so the fact that this galaxy is a dwarf galaxy, and the fact that it's not located in the nucleus starts to give a hint that it's a little bit of an unusual transient. Most transients are flares from AGN, but this one, based on the location, is not likely to be. And the fact that this is a millijansky scale source, it's a few millijanskys, and it's located at 150 megaparsec, means that it's extremely luminous. It's something of order 10 to the 29 ergs per second per hertz, which in the scale of sources that might be located in off-nuclear regions of dwarf galaxies is extremely luminous. So in sort of the pantheon of stellar explosions, which you immediately start to suspect based on the off-nuclear location and star-forming galaxy, here's where 10 to the 29 ergs per second per hertz sits. The most luminous sources are these Doppler-boosted on-axis gamma ray bursts, where the jet is pointed straight at you, and they can reach something like 10 to the 31 ergs per second per hertz at the highest. And as these GRBs start to fade, as well as potentially GRBs that are off-axis, you can start dropping down after a few years to 10 to the 29, something like that. The most luminous 1C broadline supernovae reach something like 10 to the 29. PTF11 QCJ is an example of this. However, much follow-up has been done of 1C broadline supernovae, and actually most of them aren't even detected at all, with upper limits somewhere in the range of 10 to the 27 or so. Again, the most luminous type 2N supernovae are also quite luminous. They reach something a few times 10 to the 28, but most of them, again, are also not detected with similar upper limits. And most ordinary type 2 supernovae, core collapse supernovae, actually sit in the range of something like 10 to the 25 ergs per second per hertz. And type 1A supernovae have extremely deep limits, never been detected in the radio, way lower, many orders of magnitude less luminous. So VT1210 is sitting somewhere around the off-axis gamma ray bursts, older gamma ray bursts, maybe at the very bright end of type 1C broadline supernovae. And so just based on the luminosity alone, we started getting very excited about this source. Originally, the search was designed to look for these off-axis gamma ray bursts, and based on the luminosity, we thought, that's a slam dunk. It must be an off-axis gamma ray burst. And so one natural thing to do is to look for archival transient counterparts to get additional context. And then grad student, now Miller Fellow at Berkeley, Anna Ho, suggested that I cross-match my list of VLAS transients against this odd class of what are called musts. So musts are MAXI unidentified short soft transients. MAXI is an instrument that is located on the International Space Station. It's an X-ray all-sky monitor. And short means that it's detected only in one pass of MAXI. MAXI observes the entire sky every 90-minute orbit of the ISS. It's soft, meaning that it's detected in the two lowest energy bands of MAXI, between 2 to 10 keV, but not detected between 10 to 20 keV. And burst is a burst. And so I thought, oh, well, there's only 9 of these. What are the chances that I'll actually find a match? But lo and behold, there actually was a match. And this source, MAXI GRB 140814A, has a localization region shown in panel A on the left here. And the star shows the position of the VLAS transient. And when you correct the MAXI light curve observed for the effective area at that position, you get the light curve shown in panel B here. And it turns out that this light curve is quite interesting. It's quite a unique X-ray transient. It's not only only detected in one maxi transient, it's less than 90 minutes, it's actually only detected for part of the scan where the gas slit is drifting over the sky. The duration of this transient is only 15 seconds, and it's quite soft. It's got a similar luminosity between 2 to 4 keV and 4 to 10 keV. And so we think that the peak is probably somewhere in between the two bands, order of magnitude 5 keV. And the fact that it's associated with VT1210 means that, again, it's located at 150 megaparsecs, and that places it at an extremely high luminosity of 10 to the 46 ergs per second. And so how would you explain an X-ray transient that has these properties? 15-second duration, 5 keV peak, 10 to the 46 ergs per second. Well, Udi Nakar did some really good theory on this, and it turns out that you can't explain this with, for example, a non-relativistic shock breakout, which is observed for supernova 2008D. So the reason why is because 10 to the 46 ergs per second simply can't diffuse out within 15 seconds. And you also can't explain it with a relativistic spherical shock breakout, because you have the beaming problem, the classic beaming problem with GRBs. You require an extreme energy of 10 to the 53 ergs. And also your typical energy in your photons would be 100 keV or so compared to the typical energy we see of 5 keV. However, if it's a relativistic jet, then everything works. And all you need is the bulk Lorentz factor gamma to be greater than 2.5 or so. Oh, okay, I need to go a lot faster. So it's a GRB, right? We could have published a paper just then, but it turns out actually no. Follow-up observations are very important. So clue number 6 is that we took an optical spectrum at this location, and we see that there's evidence of very dense circumstellar medium interaction from this intermediate width H alpha line. And this has never before been seen with a transient that has a jet. And this is backed up by multiple epochs of radio follow-up that we took with the VLA. And here you see the synchrotron self-absorption peaks in the two, which you can use to figure out that this is an extremely dense shell of 10 to the 6 particles per cubic centimeter at a radius of 10 to the 17 centimeters or so. And relative to literature supernovae, it's got a much higher density at large radius than you typically see. And this is indicative of pre-explosion eruptive mass loss occurring centuries before explosion. And so how do you explain this shell? Well, it can't just be gas that's sitting around there. The massive star would blow it out in its lifetime. It's not a typical LBV eruption. Those occur during the time the star passes through the instability strip, like tens of thousands of years before explosion. Nuclear burning instabilities are limited to months to a decade before explosion. We observe centuries. But binary interaction works, except you still have to explain why it occurred so close to explosion. And it turns out that this is difficult to explain, especially at high metallicity. It's possible at very low metallicities, 0.01 solar metallicity or 0.04. However, at 0.8, it's basically unheard of that you get anything even this close. And so the most plausible way we think to explain the synchronization is if the ejection is causally related to the explosion. And it turns out that this has been predicted, first by Chevalier in 2012. So the scenario is that you have a compact object, a neutron star or a black hole, that is spiraling in to its companion in a common envelope. And this can occur anytime during the lifetime of the star. It doesn't actually have to be, when it's about to explode of its own accord. And what happens is the compact object, when it spirals into the core, if it reaches the core, it disrupts fusion in the core of the star and it explodes the star. And crucially, this is the only model that explains both eruptive mass loss and the presence of a jet. And this is also an alternative branch to the leading formation channel of these close LIGO binaries that can merge within a Hubble time. So I found out earlier this week that our paper was accepted to Science, and it should be appearing hopefully in the next 2 months or so. And there's a lot more exciting science that's been being done with VLAS. Christina Nyland has a talk tomorrow at 10:25 on young AGN jets, also found in VLAS. Vikram Ravi has a paper that came out this year on a tidal disruption event, as well as student Jean Somawar has several papers in prep about TDEs. My student Carlos Ayala has a paper on flaring stars, and Casey Law and Kunal Muli have done a lot of work on the first orphan afterglow, also found in the VLA Sky Survey. So I submit that the VLA Sky Survey is showing that blind searches of large data sets are engines for serendipity. Thank you.
All right, are there questions for Dylan? So I see Laura has a question. Go right
Hi,
ahead.
Dylan. I was wondering, what is the delay between the GRB and the radio detection?
The delay is about 4 years. So the radio emission that you're seeing is not from the GRB itself. It's from the CSM interaction with the shell at 10 to the 17 centimeters.
And do you know, are there any archival data or any additional epochs that you can plump up a light curve?
We weren't able to find much archival data. We've done a pretty extensive search, which is all detailed in the paper. I wanted to post the paper in archive before the talk, but it's unfortunately embargoed. So you'll see it in a couple of weeks, hopefully. Also happy to chat offline.
I'll just ask a very quick follow-up question. And as you said, it's 4 years afterwards. But don't you only have a slot that is knowing that it's at most 4 years? You don't have other data, or do you have data that clearly shows it wasn't detected up to 4 years?
Yeah, we have, oh, actually, that's a good question. We have optical data that doesn't detect anything at all. But it's also mostly unconstraining, like 1C broadline supernovae, type 2N supernovae are allowed, for example. So there isn't a huge amount of constraining data in between.
All right. And Kate Alexander has one last question. Is this the only transient with similar properties that you have found in VLAS so far, or are there others?
There are others, yes. I'm going to be coming out with a volume limited survey paper on extragalactic transients. And there are 4 total supernovae that we found that have similar optical features. However, this is the only one, similar optical and radio features. However, this is the only one that's associated with an X-ray transient.
All right, let's thank Dylan again, and we'll go on to our last talk of the session. I apologize for running a little bit over. And the last talk is going to be Poonam Chandra on revealing the supernovae progenitors via wideband radio observations.
Hello, everyone. I hope you can hear me and see my slides.
We can hear and see you.
Okay. It's very nice to be part of this 40 years of celebrations, and so thank you for that, and let me already warn you that my talk has nothing to do with the surveys, but it was actually originally scheduled very late in the night, and it's right now 11 p.m. in India, so I tried to move it up, so that's why it is right now. And so I'll be talking about supernovae, not the surveys. So the very simplest of the definition, a supernova is when a star which has run out of its nuclear fuel is undergoing a gravitational collapse. And as you can imagine, there are multiple kinds of supernovae, and each supernova has a different kind of progenitor. But one of the biggest unsolved problems in stellar awaits with its progenitor And while one can imagine doing that via archival images, which has been limited to very nearby galaxies, it is not really serving the purpose. For the reason is that when you see a progenitor star in an archival images, you see the star at the end stages. But unfortunately, in case of massive stars, there is no real mapping between the initial and the final mass of the main sequence star and the exploding just before the explosion star, because of this huge mass loss rate from the star. And this becomes even extreme in case of the stripped envelope supernovae, where the star has not just lost the whole of the hydrogen envelope to mass loss, but in some cases even the helium envelope. And while if you go by the traditional models, the strong stellar winds are the most talked about models for these kind of mass loss rate. But it turns out that it has been seen multiple times now that these winds of massive stars are clumpy, and if you take the clumping into account, the actual mass loss rates reduces by a factor of 2 to 3. And then they are not sufficient to strip the star of its hydrogen and helium envelope. And also such simulations have also not supported such kind of models. In fact, such kind of stars often turn into black holes with a very faint or no transient at all. So one of the things is that effect of magnetism, metallicity, rotation, binarity has not been explored that much in detail. Bernali yesterday, who gave a talk on massive stars, she's exploring the aspects of magnetism. Here I'm going to talk about the binary system, because we all know that these massive stars like to be very social and like to live in an environment where they at least have a binary companion, and 2/3 of the stars are going to lie in this kind of systems. So binarity is an important component, and to understand. But how do we understand that which supernova has a binary progenitor, which supernova does not, and so on? One needs to understand. But thankfully, we have a way to figure that out. And the way is that the mass loss, the star loses its mass in terms of winds, and these winds create an environment around the supernovae. So once a supernova explodes, when you study the interaction of the supernova ejecta with the medium, one can understand the mass loss rate of these stars, which carry the footprints of the progenitor star. And not just that we can study these environments, we can also study in a fast forwarded way. And that's simply because the ejecta velocities are so much more than the wind velocity. So you can trace the evolution much faster. And with that introduction, I would like to give an example of a very interesting supernova, 2001 EM. And I would also like to say that in these studies, we have confined ourselves or explored the aspects of wideband radio observations. And I would like to say that we have opened up a new parameter space in studying the transients via the wideband measurements. And with that, the supernova 2001 EM was a stripped envelope supernova. And the interesting thing about the supernova was that it was a very garden variety supernova. But at that time, since some of the GRBs had been seen to be associated with stripped envelope supernovae, many of the stripped envelope supernovae had been observed in radio and X-ray bands for the late time emission to look for the off-axis GRBs. And so was this supernova observed, and to everyone's surprise, it showed very bright radio and X-ray emission 3 years after the explosion. And initially, it was modeled as a misaligned GRB, but then the VLBI measurements were done, and it was seen that the expansion speeds are less than 6,000 kilometers per second. And not only that, the optical measurement shows the detection of H-alpha emission, and then the GRB model went out of the window, and of course, people modeled in terms of circumstellar modeling with this extended mass loss rate. And so we have collected 19 years of data with VLA, GMRT, XMM, Chandra, and Swift, and we have also these are archival data, and we have also collected the new data with VLA, GMRT, and Swift observations, and we have tried to understand this system. And of course, the early time emission can certainly be modeled with this dense hydrogen shell with which the star ejecta, the supernova ejecta is interacting and giving rise to this radio emission. But that's not what I'm going to talk about today. I'm going to pay you to pay attention to the late time spectra, and here it is the late time spectra. If you see the bottom plot, and if you believe that, which is true, that if the radio emission is coming via the synchrotron, the late time one would expect a optically thin emission of the shock. But if you see, here is something very different. You see that while the measurement at the lower frequencies, which were taken with the GMRT, are optically thin, there is this extra component which is rising up. And if you actually look very carefully, this extra component has started to rise at higher frequencies and eventually moving into lower and lower frequencies. And then this extra component is even becoming optically thin. It is as if the main shock, when the main shock of the supernova became optically thin, at that time one could see this one could unveil this this slow moving ejecta, which was still optically thick at later times. And when you model this is kind of spectrum one sees, which is very very strange, but it has actually been seen in another very interesting supernova, which is 1986J. And in that supernova, even there were VLBI measurements, and one could see that there is this absorbed CSM component, which was seen at a later stage. Unfortunately, in 2001 EM, we are very close to the limit of VLBI, and VLBI is not really that easily possible. But with this kind of the spectra, the only possible explanation is that there is a fast moving CSM and then there is a slow moving CSM. And I'm going to again show the image which just now Dylan showed. And this is basically the common envelope scenario, which shows that this massive star, there were two massive stars, and the most massive star exploded, created a neutron star. That neutron star spiraled in and accelerated this mass loss rate. Because of that, the supernova lost its hydrogen and helium envelope. And it also, if you carry out the simulation, it also creates a very very asymmetric kind of CSM, where you create these blobs around the equatorial plane, and then this the fast moving ejecta. And we believe that we are seeing this very dense CSM because of the binarity of the system of the progenitor. And this is the best explanation of that. And with this, we actually went back to many of the VLA archival data and some publication, and we saw that these kind of late time excess in the flux have been seen in some supernovae. But because of the lack of the wideband measurements, these things could not be used to confirm the nature of the progenitor. But I would like to say that with the wideband measurements, one can do that. In fact, NGVLA is an ideal object. Will be an ideal telescope to do that, because it will have 2 orders of magnitude frequency coverage, where one can see these kind of structure, and it will also have the milli-arcsecond kind of resolution, where one can resolve and see these kind of actual CSM components and such look at the binarity. So it's going to open up a new, in some way, a parameter space. Now, having said that, I think I would just like to say that when we do this modeling of radio emission, things are not that straightforward. Whatever I showed, we are taking a very, very simplistic view. We are taking a very stable magnetic field in these shocks, and then the shocks are interacting with this very symmetric medium, and then they're creating the radio emission. And we, in fact, most of the time take constant density, like 1 over r squared density medium, which indicate that the mass loss rate should have been constant. But of course, we are already dealing with that. But I would say that we have to move to the more realistic models and not take everything on, in a very simplistic view, because it kind of creates a wrong impression. And I would like to show again the example of a wideband radio observations, how it can be used to understand the more realistic models for radio emission. And this is again a supernova, which is a stripped envelope supernova, for which we had 3 years of observations with the GMRT and VLA, and we also had several X-ray observations. And here, these are the VLA and GMRT data. But what I would like to draw your attention to is that if you look at the low frequency spectra and light curve, The low frequency spectra has a spectral optically thick spectrum index of 1.4. And it is not because it is close to the transition region. If you see the left plot, it is staying like that 1.4 for more than 100 days. It means it is an intrinsic spectra of this supernova in the optically thick phase. And if you look at the 610 megahertz GMRT data, and if you try to model that data, you also get the size of the shock. And the problem with this is that the size of the shock is coming out to be a few times 10 to the power 15, and the electron energy index is coming out to be 1.45, which is extremely hard. And it also doesn't agree with the VLA data, because VLA data, being a high frequency data, simply allows us to look at the electron acceleration mechanisms, and let us see that the p-value should be, this electron energy index should be 3 and not 1.45. Similarly, we had the optical measurements for this supernova where even the optical ejecta has a size at least twice as much as what radio is showing, which is very contrary to what radio should be showing, because radio comes from the fastest ejecta. So if at all, the R for radio should have been the size much larger than the optical measurements, which is not true. So in this case, we developed a model which we call an inhomogeneous. Okay, thanks. Inhomogeneous model. So the idea of this model is that when we are assuming the radio emitting shock, we are assuming the homogeneous distribution of relativistic electrons and magnetic fields, but they have no reason to be homogeneous. So what we are suggesting is that the shock has inhomogeneity in the magnetic field, so which is giving rise to variation in this optical depths. And finally, what we are seeing is the superposition of the spectra of varying optical depth. You can think of in terms of AGN kind of analogy. And with this kind of formalism, we could easily fit the data, and we could see that our the shock is indeed having inhomogeneities in its radio emitting region. And this was possible with the wideband data, and it brought us closer to the model, a realistic model. But one of the problem is that this is what we are seeing is a point source with VLA and GMRT, and this creates degeneracies. To be able to see this broadness of the spectra caused by the inhomogeneity, one really needs to have a milliarcsecond kind of resolution to be able to resolve these systems. And for that, again, I would like to emphasize that it is NGVLA alone which will have 2 orders of magnitude in the frequency as well as the milliarcsecond kind of resolution, and can actually throw light on these realistic models. And having said that, I would probably go to my summary slide, and I'm saying that if you have the wideband measurements, one is able to probe the sub-year to thousands of years before the explosion and get some view of the progenitor star which that had been. And one can probe more realistic models with wideband radio observations. And NGVLA is very, very well placed to do these kind of studies. And not just that, it is also turning out that the understanding the stellar evolution, the end stages of massive stars, is not just limited to supernovae, GRBs, and F-bods. It turns out that they are going to die in various ways once you take into account the effect of magnetism, binarity, and so many parameters. And with LSST and NGVLA working, few years down the line, and this time NGVLA comes up, LSST is in this full mode. We are not just going to talk about the photons. We will be talking about multi-messenger astronomy. We would have hopefully had gravitational waves from some supernovae, nearby supernovae. We would have seen some neutrinos, and we would be actually talking about, we have to have this larger picture in mind, and then that will really going to change the transient science with this kind of thing. Thank you very much.
All right, thank you very much. We really don't have time for questions, but I will allow one while Anna probably gets prepared to take pictures. So everyone should start, while we're doing this, everyone should start to put the video on. Are there any questions for Poonam? So Larry asks, points out this is fun stuff. At some point, ejecta and counting the reverse shock generate radio emission, as is the dominant process in what I'm assuming is CAN-A. At what point do you think reverse shock emission might become important? Probably with CAN-A.
That should not come at this stage. It will reverse shock emission has been seen in supernovae remnants, but not at this stage.
All right. Thank you very much. I will hand this over back to Anna for whatever she needs to do for pictures.
Thank you so much, Greg. Thank you very much for the sharing. So I'll start taking the screenshots on the Zoom and I'll try to do it super fast. Okay, so I'm starting now. Okay. Laura, you are walking. Okay, 1 second. Done. First one, sorry, 3 more to go. Too many people are moving. Okay. Oleg, we might just about see you in your picture. Okay. Thank you, everyone. We will have a few more options to take pictures because I'll try to take it a few times so we can cover as many time zones as possible. The next one, I will actually announce it later. We will try by the end of the day. And for those of you that have not joined yesterday, and that's the first break they are on, and you have not heard about the celebratory VLA gift bags, you may want to hang around for a little while and I'll introduce what is that about. So, yeah, you might, I don't know, I'll check it later. Tracy, whether you blinked. Okay, 1 moment. So, let's see. Okay, share screen. Review. Okay, sorry, there we go. So we are going to give everyone VLA 40 celebratory gift bag that is going to be shipped to your place if you'd like to receive one. And we do need a few answers from you with regards to that gift bag. So please fill in our little questionnaire. Now, how to reach the questionnaire? You do need to go to the back to the conference website where you registered. Look for already registered link. It will be probably underneath a registration or register grayed out button. Once you click on that, log in with your information, the email that you use for registration and your confirmation number. And then once you do that, you will see additional links at the very top. So where you normally would pick the program or registration or anything like that, you'll have post-registration and then you have drop-down menu. You'll see a survey page. And over there, we explain what you're going to get and there's a link to questionnaire. So please do fill that in so we know where to send the gift bags. Other than that, I will open in a second breakout rooms if anyone would like to use it for the virtual coffee room, for the informal chats. And also, please do check our highlight poster talks. It was brought to my attention that a few probably did not, they were just too big files and they may have some issues with playing. They've been updated. Yeah, see the scrapbook for the VLA. We have fantastic, fantastic entries there. So thank you so much, but please do add more. And I think at this stage, we will see you all at 11:55 Mountain Time, which is it's not 30 minutes anymore. It's 18 minutes.
Anna, do you want to stop the recording during the break or?
Good point. Thank you. Yeah.
And I don't think breakout rooms are open. I don't
That is
see
correct.
them.
Let me do it. And let me just do it. Let participant choose. They are on now. Thank you, Laura.
Hi, Anna. I'm the next speaker, so I was wondering if I could set up and see if things work.
Absolutely, yes.
Oh, Farhad, I'll be introducing you. I was
Oh,
wondering.
okay. All right. So
I was just curious on how to pronounce your last name.
Farhad Yousefzadeh.
Oh, okay.
Yousefzadeh. That's fine.
Cool.
So,
Yes, so we have Brian and Danielle. We're going to be the
so should I share now and see if things are working? I don't really have anything complicated, video or just to see this. So do you see? I haven't really shared my screen yet. So let me share.
and Ming Yung, yes, it is possible to test connection. Actually, I should mention that any speakers at the next sessions, if they'd like to test it, just do it now.
But maybe after he finishes?
Farhad is still checking, so
yes. Good.
Just trying to find share screen. Let me just
green button at the bottom of your Zoom.
I have to go to my Zoom session first. Everything is just covering up. So okay, share a screen. So if I just go to my presentation here and so let me. Okay, so do you see what I'm showing?
You haven't started sharing. So when you click on share screen and you pick which one, you have to still click share.
Oh, I did okay. I did, I just shared this. I do this all the time, but now I'm all, just because you are hosting. So let me share screen, desktop. Okay. How about now?
You're sharing a screen, but it's not in the, okay. Yes.
Okay, so you also see the laser pointer. If I just,
yes.
So that's good? Okay. All right. So that's fine. Yeah, thanks.
No worries. We can start. I mean, Farhad, we can make sure that you have your screen shared a couple of minutes before the start of the session.
Okay, you want me to
This is your
stop
first one anyway.
to stop it now?
Yeah.
Okay.
Yeah, we will test other people and then.
Right. Sure. Let me just get that. Okay. So I discontinued sharing. So good.
Thank you.
Thanks.
All right. Who would like to test next?
Can I try?
Sure.
Yes, so the camera works fine. Let me try to share the screen. So, do you see my screen now?
Yes.
And I'm gonna do the presentation mode. Do you see the slide in info mode?
The presentation only.
Yes.
Yeah.
Oops. It works fine. Okay. So now you hear me as well, right?
Correct.
Good. Okay, then I'm gonna stop the sharing. Okay. Thanks.
Thank you. Who else? I'm seeing Snezana. I think you.
I'm Steve Spangler. I'm way down in the program, but do you want us to try and bring up our PowerPoint presentations now just to check it out, or do we assume everything's okay?
I mean, yes, it's best to check it just in case.
Well, I always think, I mean, I've always been good at exploring new ways to screw up things like this. So probably a good idea to try it out if it's okay with you.
Yeah, of course. I'm here.
I'm jumping in, Steve, for a quick test. Can you see my slides?
Oh, okay.
Yeah, all perfect.
Okay, excellent. And you can hear me. That's great.
Oh, yeah.
Okay, stop share. So Steve is next.
Sure. We have two Stevens.
No. Okay, Anna, do you want to share with me or not?
Oh, no. Are you sharing?
I don't see the share button right at the moment. Oh, I do. Yeah, I do. Okay, hold on. All right, there we go. And let's share here. All right, now let's see, what do I see?
We can see the desktop, yeah.
Okay, so do you see it okay?
Well, no, so we're seeing the desktop, but not the, so we're seeing plenty of your windows.
If I put the slideshow on.
Yes. Yes, and that will work perfectly.
All right, good.
I think maybe then the issues are only when people have two windows. I seem to be having issue with that always.
Okay, so you saw my presentation, all right?
Yes.
All right, very good. Hey, Anna, I have one more question for you. I want my bag of goodies. I was trying to find your message of where to find it. I was even looking on the website. Where is it?
Oh goodness. I will. Are you on Slack?
What's that?
Are you on? Have you joined Slack?
No.
Okay, I'll put that all information in the chat.
All right. Okay. Maybe you did already yesterday. I was looking for I was looking at the website for the meeting, and I thought there might be a link there. I think, is there?
I mean, you have to sort of log in as if you were when modifying your registration.
Okay. All right. Yeah. Okay. I'll look at it. Okay. Thanks a lot.
I'll put it in the chat after we finish.
Okay. Perfect. Perfect.
Can I try as well now to share my screen?
Yes.
Okay. Presentation. So can you see that?
Straightforward.
And that works as well.
Yeah.
Okay, and my mouse pointer is also.
I can see that. Yeah.
Okay, perfect. Thank you.
Thank you.
Can I also try to share?
Yes.
Is it going through okay?
Straightforward.
And it's, I guess, moving forward. Yeah.
Yes.
Thank you.
Cool. You know.
Yeah, no, I'm on fly as well, Kunal.
Yes.
Is that okay?
Yeah. We do. Where are you? Oh, yeah.
Looks
Also
okay?
forward, yeah.
Oops. Okay, sounds good.
Yep. Okay, fantastic. So Daniel and Trey.
I can try it. This is Trey.
Oh, great. Yeah, we could try that. Oh, also straightforward. Cool. Oh, you're in a job market next year. Sorry, that was the first thing I saw. Sorry, putting you on a spot. Okay, Daniel. Do we have Daniel around?
Yep, I'll try.
Okay. Oh yeah, there you go.
Okay, so
There you go. Okay.
is that full screen?
Yep.
Okay, great, thank you.
Straightforward also. Cool. And I think the only person is Stephen Myers, but I suppose he's done it before. So last one. Okay. Thank you, everyone. 6 minutes left, Brian. So yeah, I guess I'll disappear for a moment, and if you want to say with Harad to start with, yeah, sharing that would be great. Cool.
Yeah, cool. Sounds great. Yeah, I'll say a few words at the start of the session, just saying it's the Milky Way star formation 1, and then introduce.
And just remind me to start recording, just because I start forgetting things.
The record button. Okay, cool.
That was a very good Greg today.
Hey Brian, it's Danielle.
Hey.
So just to remind myself, I'm starting at Minyan, right?
Yes, I think so.
That's what I thought. Just making sure. And we don't have to unmute anybody. That's everybody just unmutes themselves when they ask a question.
Oh yeah, I'm going to. I mean, people normally would unmute themselves. I'll make you co-hosts. I think you may ask to be able to ask to unmute, but you cannot unmute people. I guess privacy issues. So.
Oh, Anna, quick question on the Slack. Are we using the session 7 Thursday mid one for this? Okay.
So what do you work on, if I may ask?
Me?
Oh, okay. Yeah. Did you hear me? Can you hear me all right?
Yeah, sure. I wasn't sure who you were.
So what you work on, Brian?
Hey. I'm a Jansky fellow here at the NRAO, and I study infrared dark clouds in the early stages of high mass star formation.
Oh, cool.
So lots of molecules, ammonia, stuff like that.
It's funny what the topic I'm talking about doesn't really have a lot on star formation. So it is.
But it's got H3 plus, which is the next best thing. So.
Although, yeah, I won't dwell a lot on it, but it is, H3 plus is there for sure. And I think it's more cosmic rays. It's sort of relevant to the last 2 sessions or so, but it's a good it's a galactic center at least, and it's not related to stars.
Yeah, it's a little bit of a potpourri, but after having just organized sort of a postdoc symposium thing, it can be kind of tricky to have so many together.
Especially things that you see, it's sort of, it could go in either way. There's all kinds of overlap between different topics, and
Well, we're here to celebrate the VLA, so
yeah.
It's not. It doesn't have to be so non-casual.
That's right. It's sort of very lighthearted in a way. Also, the topic should be very light in a way.
Exactly.
Yeah.
Okay, just letting you know, I'll probably give like a 30-second spiel in like a minute or two, and then Farhad, you can start at 11:55.
All right. But count time after I start, right?
Yes.
Don't
Oh,
do it. I could use like every minute of it. It's funny. It's just I'm trying to compress as much as I can. Not so much, it is. It can be challenging, actually.
Oh, that reminds me. I believe your talk has 25 minutes, probably like 20 plus 5. Would you like me to give you 2 minute, 5 minute?
Yeah, give me a 5 minute and yeah, and
okay.
I'll try to, and then at 2 minutes it would be if you can, but that's all right. I'm okay with it. If you just remind me.
Okay, I'll just butt in on the voice on that part.
Yeah.
Cool. Well, I think let's get started. Record.
Should I share my screen now?
Yes. Why don't you go share ahead of your screen at the moment? Well, welcome back, everyone, to our next session for the VLA 40th anniversary conference here. I have the pleasure of kicking off our session 7 for Milky Way and star formation. We have a wide variety of talks in. Should be very interesting to hear. And it's my pleasure to introduce Farhad Yousefzadeh, who will be telling us about an abundance of magnetized radiofilaments in the galactic center region, which is our first invited talk of this session. So whenever you're ready, Farhad, please take it away.
All right, great. So you see my picture and you can hear me all right?
Yes, that's right.
Okay, great. Well, it's nice to be part of this conference. It's a wonderful conference celebrating the VLA, and I'm grateful to the organizing committee who invited me to give a presentation here on the sort of 40th anniversary of the birth of the VLA. So let me start off by showing you an image of the galactic center. And this is a picture, an iconic picture of the galactic center at 327 megahertz. And the galactic plane runs diagonally in this direction. And you see lots of diffuse emission, you see lots of supernova remnants, and you see also H2 regions like SAGE B1 and B2. And then you see these linear structures also, these filamentary structures also away from the plane. So this is what I'm going to be focusing on. So of course, the topic of galactic center has really been studied with the VLA over the last 40 years. I'm glossing over all kinds of discoveries that have been made in this region and just basically focusing on one aspect, and that'll be non-thermal radiofilaments in this region of the galaxy. So this is an outline of my talk. I'll be talking a little bit about history of when I was actually introduced to the VLA, talked about evidence for high cosmic ray flux in the galactic center, and then just talk a little bit about what we're doing now and what really holds for future as far as really trying to understand what's going on in this region, this complex region of the galaxy. So let me take you back to 1984 when we had a paper and we reported the discovery of these filaments that you see here in the radio arc, located about 30 parsec in projection from SAGE star. These parallel filaments were linearly polarized, and it was really probably the first signature of energetic activity in this region the ISM of the galactic center. But the morphology was very unusual. It was not like a typical jets, extragalactic jets or radio jets. It wasn't similar to supernova remnants. So it was a lot of something different about morphology of this, but also there were no really source that powered these filaments also. So it was really exciting, mysterious, and of course at that time I was a graduate student, and we had a paper on the cover of Nature. So this is a big deal for a graduate student. I mean, you know, it's like life peaked up, and then ever since then it's been going downhill. But anyways, this was really an exciting time, and it was in the early days of the VLA, just a few years after VLA was already had completed all antennas. And so I was really excited about being part of this this discovery. And but let me take you back. Let me take you back to what how this really happened. I asked around to see if there was a picture of apes, the apes cage at the site, at the VLA site, and nobody seemed to have any pictures. So the best I could do with a friend of mine, try to draw what it was like. You had two workstations. One, they were both running two different VAXs at the time, and I'm sitting here as a graduate student. And those days, because there was so much fight in getting time to process data, as we heard from Rick and Ron, I would come also at night. I would spend all night basically working and trying to process data using apes and basically both VAXs, because nobody was there at the time. And so at the time, you know, we tried to look for H2 regions. That was really the idea when we wrote a proposal. And these H2 regions that had been seen with Westerbork, we didn't really see this H2 regions, but then instead we saw these linear structures that was just more like an artifact. And the whole time I was spending to get rid of it. And then, so just imaging, flagging, just constantly doing this for a while. And then one night, it was about 4 o'clock in the morning, and I had another data set loaded on the other VAX, and it was a different configuration and a different wavelength and a different pointing and a different epoch. And all of a sudden, it just dawned on me that this is for real. These filaments that we see are actually linear sort of structures that are real. And that was a sort of a moment of eureka basically happening to me, and I was just incredibly inspired to really figure this out. Now that we have actually got this right, let's just try to understand what's going on. But in the meantime, over the years, I have collaborated with so many people, and this is just a small list of people that I've worked with, and I formed friendship with them and close colleagues, and I still work with some of them. And this is really I have to really say that the VLA not only enriched my personal sort of professional life, but also it really enriched my personal life to get to know all these people, and and have stories that I remember. So there's a lot of sort of that I can say about these individuals as well. So thanks to the VLA for really doing this magic. So let me now sort of flash back 20 years after the discovery, and by that time many other discoveries have been made by other collaborators, and these filaments are now basically filling in the inner couple of degrees of the galactic center, the inner few hundred parsecs of the galaxy. And so these needle-like structures, basically, they're all essentially polarized. They are sources of cosmic rays. The emission, non-thermal emission, tracks cosmic ray electrons, and that's what we're seeing. So but energetically, they were not really incredibly large. They were not that important. But what was interesting is that this was mixed in with lots of non-thermal emission, that you had both thermal and non-thermal emission. So we thought that, well, now that they have all these cosmic ray sources, let's figure out what the cosmic ray pressure is. And so we wrote a proposal to the GBT, and we observed that multiple frequencies and tried to figure out basically what the total non-thermal flux is, with all the caveats of really sort of removing thermal emission, and also what the spectrum of non-thermal emission is. So that was actually quite interesting, because then we realized that the cosmic ray ionization rate and cosmic ray pressure is actually 2 or 3 orders of magnitude higher in this region of the galaxy. And since then, there are at least 5 different ways to look at this high cosmic ray sort of ionization rate that is in the galactic center. Of course, one is from non-thermal radio flux that we see. There is also that can be used as a way to also explain the warm molecular gas that you see in the galactic center region. It's a globally the temperature is high in the central molecular zone, and you need to have that kind of high cosmic ray ionization rate to heat the gas essentially. And then you have H3 plus measurements, and this is an incredible molecule, because the chemistry is physics. Chemistry of this molecule is actually quite simple, and the 3-3 absorption shows up really as a fingerprint of the galactic center, and it's a very accurate measure of the cosmic ionization rate. And Oka and Tom Jubal really discovered this, and that the cosmic ionization rate is also 2 or 3 orders of magnitude higher in this region. And of course, you can also explain the origin of 6.4 keV line emission from low energy cosmic electrons and protons, as well as high gamma ray emission, GeV emission from molecular clouds in this region. So it is, I think, one thing I want you to take away from this is that cosmic ray flux is actually high in the nucleus of our galaxy, the inner few hundred parsecs of the galaxy. And if you look at it, actually, if you have a high cosmic ray pressure in the plane, basically it drives the wind. This is a very well-known phenomenon, studied theoretically and observationally. People have seen it in nuclei galaxies, and even in our own galaxy, the outer galaxy. And the idea is that if you have a high cosmic ray pressure, the wind is driven, and this sort of a high cosmic ray pressure essentially lifts the material. It drags the magnetic field lines and also heat the gas and to a higher latitude. So that's really the effect of cosmic rays. That is very different than any other processes that I know. So as a result, what you really see is that the magnetic field, if it's linearly, if it is azimuthal, it just drags it into vertical direction. And this is a wonderful map that is showing the magnetic field of stellar light after you correcting for foreground, and it shows that the magnetic field is horizontal along the galactic plane, and it becomes vertical. And if you take this at face value, it actually is consistent with the picture that I'm presenting here, that that you have a different geometry of the magnetic field along the plane and away from the plane. And now, I want to take you back to just a couple of years ago. Out of blue, Meerkat observed the galactic center, and he found this sort of a remarkable sort of bipolar radio structure that extends over 430 parsecs. And this was really very revealing, because now you have some indication of past activity, relic of activity, and in fact also X-ray emission is also filling in this radio bubble. And that was also quite interesting. That means that you have an outflow, and this outflow could be explained in the context of a cosmic ray driven wind, because the wind, as it propagates out, basically it inflates and it creates a bubble. And you can actually think about also the same high cosmic ray pressure. One of the consequences of it is also able to actually produce this kind of a activity in that you see, this sort of a relic of past activity. But even more interesting about this was this discovery was that almost all filaments that have been discovered essentially are tied to this radio bubble. Not all, but most of it is actually filling into this central region. And if you look at their distribution and the densities away from the plane and along the galactic plane, you'll see that they actually are very similar to each other. So this was a really a Meerkat observation that really generated this, that for the first time, a causal connection between the origin of these non-thermal filaments and the more extended radio bubble filled with X-ray emitting gas. So that was really quite interesting, I think. And then another consequence of this kind of a large-scale wind driven from the galactic plane is that it interacts with anything that it's any obstacle basically comes through it, it interacts. Especially in the nucleus of the galaxy, where there are lots of objects. You can have stellar bubbles, you can have clouds, cloudlets, you name it. Anything that is actually along the way, just to interact. And one of the ideas that we had is that, okay, so now that you have this cosmic ray driven wind, then it could also interact with a stellar bubble. And if it's when it interacts, basically the magnetized wind is basically wraps around the stellar bubble and it gets basically compressed, and then it just stretches out in the direction away from the direction of the motion of a star, and you can create a tail, sort of a magnetized tail behind it. So the idea is not unusual. This is something also seen in local ISM and also in solar system, the interaction of a magnetized wind with atmosphere of planets, for example. But anyways, the point here is that if you look at Meerkat images of the galactic center, we see a number of filaments that appear to be basically associated with the non-compact radio source. So we are now investigating this in fully. This is just a morphological, but we are making high resolution observation on VLA. And so this is really a subject of current study to figure out if this picture holds together. If it does, it's a nice way to explain that the stars can also be an important element of really just sort of making the wind basically become focused in the direction away from when the stars are moving. So now
that's 4.5 minutes.
Okay, great. So the next few minutes, I want to talk about some of the things that we're doing now with Meerkat and VLA data sets. And this is a Meerkat image of 20 pointings. They spent over 200 hours observing this region of the galaxy. The sensitivity is incredible, the broadband and all that. And certainly VLA could do this as well. The resolution is about 4 arc seconds. Certainly VLA, there is no 1 arc second resolution or even sub arc second resolution with that kind of a imaging capabilities. And so this is so what we did in order to bring out the filamentary structures in this region. We used a high pass filter, and this high pass filter all of a sudden just showed this incredible abundance of filaments all over. And these are all for real. All these bright filaments that you see, very well recognized, and you see all kinds of sort of a harp-shaped structures. And you see these loops, for example, coming off, and it's just and then you see these spaghetti features along the galactic plane. They are actually thermal structures that you see edge brightened, and of course we just created how we're going to identify these individual filaments, because there's so many of them now. And then we just realized that, well, let's take a page from what solar physicists do, and this is. What we did, what solar physicists do is that when they have a solar loop, they basically filter it, and you see beautiful loops here. And then what they do is they have these automated loop tracing codes that identifies these individual loops, and then they can learn about the properties of these individual loop-like structures that you see here. And one of the things that they're finding is that the loop length distribution follows a power law distribution. So this is what it's showing. It's a histogram of the distribution of the length of individual loops that you see here. So then we said, okay, why don't we just apply the same loop tracing code to our image? And then this is what happened. You can actually now localize individual filaments, the length of these individual filaments. You learn about their intensity. You learn about all kinds of properties that you want, the curvature, you name it, spectral index, and all of that. And then we just basically found out what the distribution of the length of these filaments are, the galactic center filaments. And I'm drawing it to two different cuts here. And you can see it's a power law distribution, similar to what you see also in solar loops. And that's actually really very revealing. I don't know what it means, but it should mean something. That why is it that they have a power law distribution of length of filaments? That's something, if anybody has an idea, I'd love to hear from you. But this is one of the powers of really sort of applying these loop tracing algorithms. And so there are all kinds of other things that we are finding now. I just wanted to just give you a highlight of what we're doing, and and in summary, I just want to mention that I think a study of the filaments in the galactic center led to the idea that cosmic ray flux is fairly high in this region of the galaxy. And of course, there are lots of consequences that are happening as a result of having such a high cosmic ray flux. And we are doing now statistics of radiofilaments, and that's actually a subject that's very exciting to learn more about these. And what really future holds is that I think it would be fantastic to do these sub-arc-second or even arc-second deep survey of the galactic center with the VLA, and hopefully in NGVLA can do some of that as well. And of course, low frequency observations are absolutely critical also, because a lot of cosmic ray, but basically we don't really know what the spectrum of cosmic ray particles are at very low energies. And if you push basically to a lower frequency, you find out all we're doing now is we're extrapolating to low energy cosmic ray particles. And after all these years, the origin of the filaments still is mysterious. And maybe it's okay. Maybe it's okay, because as Einstein said, the most beautiful experience we can have is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science. Okay, with that, I thank you for listening, and I take any questions that you might have.
Oh, thank you. Great talk. Right on time, too. So please, if anyone like to post any questions.
I have a question. Very interesting talk to start with. Very nicely presented. But one of the things I was interested in is you use the essentially minimum energy or equipartition energy calculation to come up with this assumption of a high cosmic ray energy density. And then you had 5 other indications which were consistent with that elevated cosmic ray energy density. Now, the question I have is whether any of those have different energy dependencies. For instance, we know what the cosmic ray spectrum is at the location of the sun, is like a minus 2.7 power law. Is there anything that might indicate whether we could tell whether the spectrum of the cosmic ray protons in the galactic center was different from that? Now, the chemistry is, as you've noticed, is determined only by the low energy ones. But is there any kind of way we could process all these different indicators to maybe get some information about what the cosmic ray energy spectrum is? I mean, we're talking about protons largely in that part of the galaxy.
Right. I think the only way to really do this is to look at the high energy sort of maps of this region. The 6.4 keV emission, which is basically produced as a result of the excitation of iron atom, could be done not only by electrons, but also by protons. And I think this is something that has been, people are working on this. I think that's where, if you want to find out about the spectrum, I think that's a good one. But also, gamma ray emission is also being seen from molecular clouds in the galactic center region as well. And I think that's also a good way to really probe this and figure out what it is. And of course, honestly, we don't even know what the spectrum of cosmic ray electron is at very low energies, and that's why I think low frequency observations could be critical. So there is a lot that we can actually do. For protons, I think we have to rely on gamma ray and X-ray emission from this region. But I don't have any answers, honestly. This is something that has to be for sure. Yeah.
Laura, I see your hand is raised. Would you like to say your question?
I was curious if it would be possible that most of the filaments could be created by that cometary tail following the star, or if the fact that you have this dramatic directionality in the filaments implies that most of them can't be from stars.
No, I think the idea is that all filaments are going to be produced as a result of this interaction. So that's the idea. And there are a number of sources that we see associated, or at least appear to be at one end of the filament. But we don't really know, because you have to do high resolution observations, and you need, also you have to localize also where stars are, and try to figure out. That's one of the things that we're doing with Spitzer data. But still, there is a question. You need high resolution observations, and this can be done. Certainly, that can be done. But if we just find a few of them work, then the rest should also be following the same thing. Because what's interesting about this the density of filaments as a function of latitude follows exactly the density or the scale height of stars. So the scale heights, I didn't really show it here, but I have actually, I have plots that show what the distribution, what the scale height of stars are, and also versus galactic center, especially the ones that are highly extincted, and it looks promising, but I can't tell you for sure yet if that's the case. I think it would be a nice solution to the origin of at least how these filaments are produced.
Great. Well, unfortunately, I think we're out of time, but I'd like to draw everyone's attention to the Slack where we can carry on discussion. And Farhad, there's some more questions in the Zoom chat as well. Okay, the Slack chat is called session 7-Thursday-mid if we want to continue discussion there.
Okay, great. Thanks.
Great. So, Kunal, whenever you'd like to share your screen. Great. Cool. right on time. So I'd like to introduce our next speaker, Kunal Mooley, who will be telling us about a polarization view of the galactic center. Please take it away, Kunal. I'll give you a warning at 2 minutes, by the way. And if you're saying something, you might be on mute.
Thanks for that, Brian. Give me just one moment to get set up here. Screens. All right, so thanks again. So hello, everyone. I'm Kunal Mooley from Caltech, and I will be telling you about polarization studies that myself and these excellent collaborators here, not sure if you can see my mouse pointer, but these excellent collaborators and myself have been conducting in the galactic center region over the past year or so. So this talk will be pretty straightforward. I'll give you a small introduction on the galactic center and polarization, and then a sneak peek on some of the very recent results. So for the students in the audience, let me get started with a quick introduction to the galactic center region. This is the color composite image showing the infrared in red color and the VLA total intensity image of the galactic center in green. The bright clump in the middle is Sagittarius A complex containing a supernova remnant, a supermassive black hole, Sag star, of course, and a mini spiral structure that is presumably feeding material to Sagittarius A star. And there are these filaments and arcs that we heard from Farad's excellent talk, and these may be following large-scale ordered magnetic fields. This region is also quite active in star formation, and radio emission is seen from H2 regions formed by massive stars, such as those residing in SAGB and SAGC regions. And there are supernova remnants all over the place from the deaths of stars that took place in the recent past. Now, apart from all of this, apart from all the extended structure, there are also thousands of compact radio sources associated with X-ray binaries, pulsars, compact H2 regions, etc. So in our study, we are particularly interested in deep observations and deep studies of the central half square degree or so, or about 50 parsecs around Sagittarius star. So just a bit of history here, since we are at the VLA 40 conference, is one of the first VLA images of this region, specifically the Sag-A region, was produced by Miller-Goss and collaborators in the early 1980s. And this is still Stokes eye, no polarization yet. But this image clearly showed for the first time the shell-like structure of the supernova remnant, which is what the bigger structure here is. And this is called Sag-A East, and the mini spiral that is centered on Sag-A star highlighted in black here. And later, more detailed studies were carried out, of course, by various groups, and some of which we already saw in Farad's talk. So the quality of images has improved significantly over the years, and thanks to the VLA upgrade, new algorithms, imaging techniques, and advances in computing. The current state of the art is this image, which combines the GBT and VLA to reach an RMS noise of about 2 microjanskis, so achieving a dynamic range of 400,000:1. But these are still all Stokes eye studies, which have been quite extensive, but really very limited polarization studies. Such as the ones targeted towards Sag-A star, galactic center magnetar, filaments, and large-scale magnetic field that has been traced using these background point sources, extragalactic sources. But there are a number of cases motivating new or deep searches. And so firstly, there is a conspicuous dearth of pulsars in the central few parsecs around Sag-A star that has been attributed to limitations of current pulsar search techniques using time series analysis. But however, there is strong theoretical arguments as well as several lines of observational evidence that show that there should exist a sizable population of neutron stars and pulsars towards the galactic center. And since pulsars are polarized, they can be found through polarization imaging. And finding new pulsars may also explain the gamma ray excess in the galactic center if millisecond pulsars are responsible for the gamma ray emission. The GC region is also has the kind of dense environments where we may be able to find neutron star black hole systems that can eventually merge and produce gravitational waves. And if there is a pulsar in orbit around the supermassive black hole, it presents an excellent opportunity to study the SMBH properties and GR. And there are other motivating factors like the study of magnetoionic environment and how that evolves with time in the immediate vicinity of Sag-A star, the magnetic fields associated with supernova remnants, H2 regions, and other polarized sources. So just to remind the students here, the different Stokes parameters give information on linear and circular polarization, and all sources emitting synchrotron and coherent emission are intrinsically polarized. Linearly polarized light also undergoes Faraday rotation, and this effect, together with the rotation measure, are powerful probes of the magnetic field parallel to the line of sight, and this which can also help us reconstruct the magnetic field of these emitting sources. So the idea here with our particular study is from Stokes Q and U, we calculate the rotation measure as change in polarization angle over the change in the square of the wavelength right here, where this chi, which is the polarization angle, is defined in the following way. So we construct Faraday cubes basically at the end of the day, where the image coordinates are X and Y, and the third axis is rotation measure. And this cartoon is showing just an example search for pulsars, which is where the known sources are shown in blue and possible new sources shown in black. Okay, so we're trying to push the capabilities of the VLA to its limits by using very narrow channelizations and using the full bandwidths available with the Jansky VLA. So L-band 1 to 2 gigahertz. This is all like sub megahertz channels and thousands of channels to cover the entire bandwidth. And this gives us a sensitivity in the RM space of up to like 2 × 10⁶ radians per meter squared. So just for people who don't work with these numbers, this is like 4 times the rotation measure that is seen towards Sag star, which is the highest that has been seen so far in our galaxy. And the kind of resolution that we get in RM space is better than 20 radians per meter square. So quite impressive in terms of like what we can get out of the VLA. This is just showing you the spread function. So just consider this like an analog of, if you have a radio image, you have a certain point spread function. So this is just the point spread function in the rotation measure space. So we're dealing with large amounts of data. A single image cube is more than 2 terabytes. So you can imagine the computing involved. And we are able to reach for now with some small amount of data, 5 to 10 microjanskis per beam in Stokes QUV. So just now going into a little bit of sneak peek of our results. This is showing you the polarized intensity image, which is basically just square root of Q squared plus U squared averaged over all the channels. And you can clearly see this one striking source, which is Sag star or black hole. So the plot here is showing you the basically the chi versus lambda squared, which is what we use to find the rotation measures. And so we find a rotation measure, which is a few 100,000 radians per meter squared, which I must mention that this is kind of low compared to the high frequency measurements carried out so far, which indicate that the rotation measure is greater than 400,000. Now, what this implies is probably the difference is because we are probing the ionized material that is intrinsic to the radio source itself, meaning the at the immediate vicinity of Sag star. At L-band, we are measuring things that are further away, but at higher frequencies, we are measuring really the magnetoionic environment that is very close to the black hole. And we also are finding, I believe for the first time, some Faraday complex structure, which is still sort of under investigation. So that work is still in progress. Nevertheless, we also find several pulsars in this image, and this one is showing you the chi versus lambda squared for the galactic center magnetar, and we are able to recover the rotation measure for that. So study is still underway, but some preliminary results here. And this is also just a preliminary Stokes V image, so circular polarization, where we are seeing Sag star, some H2 regions, and also some pulsars. So this hasn't been exactly corrected for the beam squint, but that's underway, and really require high computing for that, high performance computing. So I must also mention that
2 minutes.
Yeah, thanks. I must also mention that all of this is being possible because of all the exciting developments in terms of the algorithms that have been implemented in CASA, like AW project and multi-term, multi-frequency synthesis, and all parallel imaging. So this is sort of an excellent thing that we can take advantage of for this polarization wide field imaging. So I'd like to thank this algorithms R&D team at NRAO for that. And really not just the R&D team, but I have had the opportunity over the past, I'll end with this, I was saying that over the past 12 years, I've been working with the VLA. It's been an excellent experience. 10 years ago as a Groth-Reber fellow, and just until last year as a Jansky fellow. I wouldn't say that I've been I have the I've seen the VLA for 40 years, but I've dealt with a large data sets and over 1,000 hours of the VLA, if at all that is a qualification. But I'd really like to thank everyone for this excellent experience on this 40th anniversary, and congratulate everyone at NREO. It really takes a world-class staff to maintain a world-class facility. So thank you, and I'll take questions if any. Thanks.
Great, thank you, Kunal. We have a few minutes for questions, so if anyone would like to ask, please post in the chat or pipe up or raise your hand. We have 3 claps. While we wait for a question, I was just curious about those are enormously large data cubes, 2 terabytes.
Yeah.
I was just curious if you could comment on maybe the challenges computationally that you've worked through working on these data sets.
So the first challenge is I've received several warning emails from NREO saying that I've exceeded the limits on the cluster. But apart from that, it just takes a long time. I mean, it's just sometimes patiently waiting for the processing to be done. And I'd really like to see more of Carta moving forward to analyze these image cubes. And maybe just faster processing with AW projection or things like that, if that's possible at all.
Cool. Oh, we have a question from Anne. Please go ahead.
Thanks very much for the talk. I have a quick question. Maybe I've missed it. So what limits the frequency resolutions that you have shown us at L and S band?
So it's just basically data rates, achieving reasonable data rates. We can still go finer. We are maxing out on the baseband boards. But just, I mean, practically sort of what data we can handle in a reasonable time scale is what drives this.
Thanks.
Well, great. I think that's about the end of the time, but if you have any more questions for Kunal, please direct them to the Slack channel.
Thank you.
And I believe we'll move on to Jackie's talk next. If you'd like to share screen. Oh, there it goes. Cool. Is your sound on?
Can you hear me?
Yes, can hear you now. Great. The next talk we'll hear from is Jackie Ma, and he'll be telling us about the complex magnetic fields in the first galactic quadrant revealed by broadband VLA observations. Please go ahead.
Thanks, Brian. Hi, everyone. My name is Jackie, and I'm a postdoc at the ANU. I would like to first thank the organizers for arranging this wonderful conference, and it's an honor for me to speak on this occasion about our study of the magnetic fields in the first galactic quadrant using new broadband VLA data. So we all know that we can find magnetic fields everywhere in the universe, basically, starting from the solar system to different galactic objects that were discussed so far in this conference, and of course also in the diffuse medium in the Milky Way. And as we look beyond our own galaxy, we can also find magnetic fields in other galaxies, the IGM, etc. And we also know that magnetic fields are important in many of the astrophysical topics because it can regulate the star formation rate and also affects the initial mass function. It can provide pressure support to galactic scale structures such as the disk of the galaxy itself, and also it can provide a shielding effect to infalling high velocity clouds that can trigger the next episode of star formation. So that's why we know that magnetic fields is very important for the topics of galaxy formation and also evolution. So to measure magnetic fields, we can use the Faraday rotation effect. So we just have to point our telescope at a background synchrotron emitting source, such as radio galaxies or pulsars in the Milky Way, and make use of a property of synchrotron emission that it is linearly polarized. with the polarization plane being perpendicular to the magnetic fields in the emitting volume. And as the polarized light travels through the foreground medium towards us, through, of course, the Milky Way interstellar medium, it can experience the Faraday rotation effect, causing the polarization plane to rotate. And the amount of rotation is given by the formula here. So the observed polarization angle is equal to the intrinsic polarization angle, which tells us about the magnetic fields in the emitting volume, plus the Faraday rotation term here. So this Faraday rotation term here includes magnetic field strength along the line of sight, and also is a function of square of the observed wavelength. And often this term in the square bracket is simply condensed into a single term called the rotation measure, or the RM. So what we need to do to measure RM is that we make polarization measurements at multiple wavelengths, such as in the lower right plot here, join them by a straight line, and the slope tells us about the rotation measure that tells us about the magnetic field strength in the intervening medium. So in the past few decades, we have learned a lot about the magnetic fields in spiral galaxies. On the left, I show an example of a typical edge-on spiral galaxy. And we can see that if we look away from the mid-plane at a height of about 1 to 5 kiloparsec, we see an X-shaped halo field. And if we look closer to the mid-plane itself, we see that it's dominated by the disk field up to about 1 kiloparsec or so. And the disk field can be appreciated more if we turn this galaxy to look at it face on. So on the right, I show the well-known spiral galaxy M51, and we can see that the magnetic fields exhibit as a beautiful spiral pattern. For this case, going clockwise and without any reversals in the magnetic field direction. And I would like to also take this opportunity to point out that the VLA has been very important for the study of galactic magnetism, since more than half of the studied systems so far, including both face-on and edge-on galaxies, more than half of them have involved VLA data, and the broad number of systems studied with broadband observations is rapidly increasing. And of course, the same can be said about the Milky Way studies. And here I list just a few papers here as an example. In fact, in this very conference, we will see Drew Dieth's talk on the study of edge-on galaxies with the changes survey actually a few hours from now, and also a pre-recorded talk by Timea on the direct study of of galaxies at a redshift of 0.4 and beyond. So moving on, why do we care about the nuclear magnetic fields in particular? Well, since we are situated within this galaxy itself, it will give us a unique perspective of the Milky Way structure, magnetic field structure. And because of this, we can also study it at the highest spatial resolution possible compared to other galaxies. And it's also very useful to study the Milky Way magnetic fields in details because it affects other experiments as well. For example, the diffuse polarized synchrotron emission of the Milky Way is kind of a foreground contamination to cosmological data such as CMB polarization and also hydrogen intensity mapping experiments. And the same magnetic fields will also deviate the trajectories of ultra high energy cosmic ray particles. And so we need a very good model of the Milky Way magnetic fields in order to trace back to the source of these exotic particles. Despite all these importance, we still do not have a very good knowledge in the field strength and structure of the Milky Way magnetic field. But one thing we do know is that the Milky Way magnetic field structure seems to be pretty rare among spiral galaxies. So here I bring back the M51 that I showed before on the right. And again, we see that the magnetic fields go in a single clockwise direction, while if we look down to the Milky Way magnetic field from the north galactic pole, as I show on the left, we see that in general, it goes in a single clockwise direction also, but then near the Sagittarius arm, the magnetic field direction is reversed into an anti-clockwise direction. This is known as the large-scale field reversal of the Milky Way. So if we look towards this Sagittarius arm region, we will be looking through one of the most complicated Milky Way region in terms of the magnetic field structure. But even so, we do not have a very good number of measurements of its magnetic field in terms of RM values from extragalactic sources. And this has motivated our study here. So we have defined a region of interest of in galactic longitude from 20 to 52 degrees and the latitude between plus and minus 5 degrees. And in the bottom panel, I show the previous best catalog of RM measurements in this region. And here I will swap to what we have achieved with our new observations. So with our new broadband observations done in September 2018, we have increased the RM density by almost a factor of 5 using the VLA in D array for observing from 1 to 2 gigahertz. So here I plot again our newly measured RM values as the dots on the right plot, while the background color map shows the predicted RM values from the FANG-EC 2011 model. From this, we can immediately see that in the galactic longitude range of 40 to 52 degrees, the RM values are very different on either side of the galactic midplane, which is pretty surprising. And we can still see the same trend if we plot instead the RM profile across galactic longitude, with the sources separated into above versus below the galactic midplane. So the difference in the RM in this galactic longitude range is large and also statistically significant, and it is not seen in other galactic longitude ranges. And before we start to interpret what we are looking at, it would be good if we can get a distance estimates to what we are looking at here. And that's why we have used existing pulsar RM measurements in the literature, because these pulsars are situated in the Milky Way itself at various distances. And so we can use this as to give us a tomographic view of the magnetic fields in the Milky Way. But the drawback is that the number density is rather low compared to what we can achieve with the extragalactic sources. So these two data sets kind of complement each other. And here I show the pulsar RM trend across distance in the longitude range of 40 to 52 degrees, as I was saying before. So we can see from this that for the pulses above the galactic midplane, it seems to, the RM seems to increase monotonically with distance, while for pulses below the galactic midplane, it seems to split into two populations at a distance of about 5 kiloparsec in the Sagittarius arm. So we conclude that the RM disparity may be occurring in this Sagittarius arm, but we also acknowledge that with the currently available pulsar RM data, we cannot put a very accurate constraint on this. With this in mind, we can move on to try to interpret what we are actually looking at. So we have come up with three different, thank you. We have come up with 3 different scenarios to explain our results. One is that we are looking at an anti-symmetric disk field in the Sagittarius arm. In this scenario, the galactic regions with a symmetric magnetic field will shift the RM profile on both sides of the galactic midplane up to about 300 to 400 radians per meter square. And then the split in the RM profile is caused by the anti-symmetric magnetic field in the Sagittarius arm. So this would be a kind of a surprising result because as I said before, in other galactic regions, we have kind of been seeing a symmetric magnetic fields across the midplane. And indeed, this is not predicted by the dynamo theory. However, we are looking through the Sagittarius arm here, which we already know that it has a very peculiar magnetic field structure hosting the large scale field reversal. So as we will see, this is our currently favored scenario. The second possibility is that we are looking at the anti-symmetric halo field of the Milky Way. For this case, the symmetric disk field will shift the RM profile up to about 300 radians per meter square, and then the split is caused by the anti-symmetric halo field. So this is also a possible explanation, particularly because the dynamo theory does predict such an anti-symmetric field in the halo. However, this conclusion will kind of be in contradiction with a previous study of the Perseus arm by and Mao, who found that the disk halo transition is occurring at a galactic height of about 500 parsec. While for our case, if we look at the RM profile across latitude, we see that it is not symmetric, well, not mirror symmetric on either side of the galactic plane. And if we put a conservative estimation that this is occurring at a latitude of 1 degree, this will translate to 90 parsec at the distance to the Sagittarius arm, which is much lower than what N has found. Finally, we also looked through different traces of ionized structures in the Milky Way, and we do not see anything obvious. With our new data, we have also compared with 3 major models of the Milky Way magnetic field, and we find that none of them work perfectly. But we note that the FANG-X 2011 model is matching with our data the best, and this has motivated us to try to use our data. And with our new knowledge that the Sagittarius arm magnetic field can be anti-symmetric, we try to refine the model. And indeed, as we can see below in the lower right corner, we have found that many of our models are showing better fits than the original FANG-X model. But we also acknowledge that it's not showing a super good fit to our data. And that's why we still need to do more work on this in the future. To conclude, our new study here adds to the already impressive list of VLA's contribution to galactic magnetism. With the high quality broadband VLA data, we have discovered a disparity in RM values that we attribute to an anti-symmetric disk field in the Sagittarius arm. Thank you for listening, and now I'll take any questions or comments.
Oh, thank you very much. I also appreciate the VLA crossing sign in the background. Yeah, we have 1 clap. Please, if anyone has a question, just speak out and or raise your hand. I had a question, but I suppose it's probably a really minor effect. The sun is elevated above the galactic midplane, so I was curious if that might cause any geometric, maybe it was just a very small geometric effect in the rotation measures, just because, you know, looking through diagonally through the galaxy a bit.
That's a good question. Actually, I think it's kind of like, yeah, definitely it's a possibility that we didn't look into. And I think in many of the galactic magnetic field models, it's also not considered so far, as far as I know.
Oh, great. Well, in the interest of time, I think we will have to move on to the next talk, but please direct any more questions in the Slack. Cool. So I can hear you and see you. So our next talk will be by Andreas Munthaler, who will be telling us about the GLOSTAR survey, a global view of star formation in the Milky Way at radio wavelengths. So please take it away.
Okay, thank you. Yeah, so I would like to thank you for giving me the opportunity to talk about this large project that we've done in the last years. So this is work that was initiated by Carl Manton some time ago. And most of the work has been done in Bonn at the Max Planck Institute since I actually, the whole project started when I came to the VLA for a full year during the resident shared risk observing program, which started this project and also several other projects. So, of course, in the galactic plane, there have been many surveys at various wavelengths over the last decade or so. And here are just some examples from the radio. So on the top, you see the TOR H1. Well, the second one is H1. The top one is L-band continuum. And also for example, in the submillimeter here, this one is the APEX data. And then, of course, in the infrared, like here, the Spitzer Glimpse survey and also Herschel. And all these large-scale surveys of the galactic plane have really changed our view on high mass star formation over the last couple of years. And one key aspect of these surveys was that they really probe all scales from degrees down to the arcsecond level. If you look at higher frequency radio observations, so far there has been at C-band a single dish survey, the Messel multi-beam survey, to look for Messel lasers with the Parkes telescope. And then there has been surveys, the MAGPIES and the Cornish survey, which used still the old VLA, and that was limited to the narrow bandwidth of 50 megahertz at that time. So with the upgrade of the VLA, we started this new project, again a C-band survey, but this time observing 2 gigahertz radio continuum in full polarization, to mainly find all the extended compact, hyper, and ultra-compact H2 regions. At the same time, we observed the 6.7 gigahertz metal laser line, which is a signpost of high mass star formation, and can be also used to study the structure of the Milky Way, as seen by our Bessel survey with the VLBA. We also observe formaldehyde emission and absorption, which is also a tracer for star-forming regions, and also recombination lines, which gives the kinematics of the ionized gas. So the total area that we observed is 145 square degrees. So the coverage is seen here, basically just south from the galactic center to a galactic longitude of 60, with plus minus 1 degree. And then also here the Cygnus X region, where we go a bit from -1 to +2 degrees. And the key of the survey is that we did everything twice, once in the deconfiguration with 18 arcseconds resolution, and then again in B configuration with 1.5 arcsecond resolution. And on top of that, we are currently still observing the entire area also with the 100 efforts per 100 meter with the same frequency setup for 0 spacings. So since we are observing at higher frequencies than the typical L-band large-scale surveys, the SOL project was quite challenging. So we always observed within a 5-hour observations a 2x1 degree field. And in that field, we had 750 pointings. That means we could observe each scan only twice for about 11 seconds. Which is of course not a lot of time, but thanks to the very high bandwidth, we got much deeper than previous surveys. So in total, this survey, we observed around 50,000 individual pointings, and we used a bit over 700 hours in observing time of the VLA over several years. And the calibration and imaging for the continuum was done in OBIT. And this was done mainly by 2 postdocs in Bonn, Sergio Zip and Ayuan Yang. And the spectral range data was calibrated in CASA by a PhD student, Hans Nguyen. So here is some example data. This is our pilot region from L28 to 36. And here you see the VLA deconfiguration only. And I used here a contrast, which is made so that you can see there is still some problems in the data, and that's mainly from the missing flux. The missing 0 spacings. And if you add the efforts per continuum data to this, you get this combined image, which is of course much better. There are still a few problems, like if you here look at this really bright source, there are still some problems, but this is the price we have to pay for this only to 11 seconds pointings, observing times on each pointing. So with Effelsberg, we have observed a bit more than half of the entire area. And another great example of how good the Effelsberg telescope, which actually turned 50 this year. So they're two old telescopes that are doing still very, very great science. So this is the Cygnus X region, a nearby star-forming complex where you have a lot really of extended emission, and this is just the VLA deconfiguration image, which looks not that great, but if you add the Effelsberg data, you get a quite spectacular images, still with some problems around the around the brighter sources. So here's, since we have these multiple configurations, we can also combine them. And this is just one example from our pilot region for all the different data programs that we offer in the end. And so the first one, this is a deconfiguration plus Effelsberg image. If you just take the deconfiguration image, you do some of the diffuse emission from Effelsberg, of course. And then, but now if you combine the D and B configuration data, you see basically the same structures, but with much higher resolution, and you can see all these fine details here in the sources. And then if you go to the B configuration only data, then you're basically only left with the very compact sources. So for us, so we have published 5 papers, so one 2 years ago, and the other 4 papers came out actually 2 weeks ago. So the first one is our deconfiguration catalog by Zach Medina, former PhD student in Bonn. So there we found almost 1,600 radio sources, which is like a factor of 4 to 5 more than the previous survey, including just 100 new H2 regions in this region. And you can see poster talk 10 about this paper. And the full catalog from the deconfiguration data will come out later this year. Another nice example of what you can do with this data is a search for supernova remnants. So there's one problem that only 30% of the expected supernova remnants are known. And just if you look at our VLA deconfiguration images, so Rohit Dokara, who was also a PhD student, detected 88 new supernova candidates. And here you see one.
I think we might have lost Andreas. Oop, there it goes. Well, I suppose we can wait a couple minutes to see if he logs back on. I guess use this time to think of good questions.
Yeah, Brian, how much time did we have left for this talk?
Let's see, it's at the 10.5-minute mark at the moment.
Oh, right.
So I think there's about 4 minutes before we move on to Trey.
Yeah, we probably can wait in case he does manage to reconnect.
Yeah, I suppose maybe just wait another 2 minutes or so. Oh, and just to keep everything on schedule, I'll wait till 1:05 Mountain to before we begin Trey's talk.
Oh, Andreas is back.
Yeah, I'm sorry.
Oh, it's great.
Okay, I tried.
We got, I think, about 2 more minutes left. So I think if you want to finish the talk, please just share your screen.
Yeah. Oh, yeah. Yes. Okay, can you see that?
Yes.
Well, it's not in. Okay, so yeah, okay, so here you can see polarized emission, and so this is then probably a real supernova remnant. We also have galactic center data. Here's the CMZ, and there were a number of YSO candidates in the infrared, and 30 of them have also radio counterparts, 11 with new confirmed H2 regions. And so you can also see a poster talk 11 about this paper. And the final paper that we published is the MESA survey of the Cygnus X region by Gisela Ortiz-Leon. That's poster talk 13, where we also detected new methane lasers, and they have 40% of them have also ultra compact and hyper compact H2 regions. In the total survey, we find 530 methane lasers with 83 new detections. And some of them, if you could look at the spectrum here, you see the comparison between the multi-beam, the deconfiguration, and the B-configuration, and you can see that one component is variable while the others are not, and that's some interesting aspect that was discovered recently in methane lasers. That's almost my final slide. So we just, this weekend, we finished our Effelsberg observations of the galactic center region. And here, so that's mainly done by Jan Gong and Michael Rogel. And here you see the methyl, the formaldehyde, and the recombination lines in the galactic center. And so this is now my last slide. So I think the important thing is that our first catalog and the deconfiguration images from the pilot region are public now at this location, and more data products, including images of the full survey and also the deconfiguration, and at some point also the DMP combination and the Effelsberg images will be all published on that webpage. And then sorry for the disconnect, and I guess you can send questions on Slack if you have any.
Yes, well, great, thank you. I'm glad we got to see the rest of it. It's really great stuff. Please direct more questions to Slack, though. We'll move on to Trey's talk now.
All good?
Yep, all good. If you'd just like to take it away right there, please go ahead.
Awesome, thanks, Brian. So my name is Trey Winger. I'm a Covington postdoctoral fellow at the Dominion Radio Astrophysical Observatory here in smoky Penticton, British Columbia. And today I'd like to talk about some of my work using the VLA to map the chemical structure of the Milky Way disk using H2 regions. So understanding the chemical structure of the galaxy is important because it sets constraints on models of galactic formation and chemodynamical evolution. And if we want to map out that structure, we need some sort of tracer that we can use to do that mapping. So the tracers that I use are H2 regions. These are the zones of ionized gas that are surrounding recently formed massive stars. And they're the classic tracer of structure in galaxies. So if you look at this picture of the Whirlpool galaxy here, in red you see the H alpha emission from H2 regions in the galaxy, and it clearly follows the spiral structure of the Whirlpool galaxy. But they're also great tracers for looking for the structure, the chemical structure of the Milky Way. So here on the right there, I think these are the 5 most important reasons that H2 regions are good chemical structure tracers. First and most importantly is that they're bright, especially at the radio wavelengths. The thermal free emission is among the brightest sources of emission in the sky at about 10 gigahertz or so. Second, they have a unique spectroscopic fingerprint. They're recombination lines like H alpha, and also their collisionally excited lines. And then using those spectral lines, you can derive all kinds of interesting physics of the nebula. So relevant to this talk is the metallicity, which at the radio you can infer from the electron temperature, since a more metal-rich plasma is more efficient at cooling and therefore has a lower temperature. And then you can get the electron temperature in the radio from the radio recombination line to continuum ratio. So just measuring the recombination line strength and the continuum brightness, take a ratio, assume LTE, and you get an electron temperature. So it's a really simple observation. And then lastly, if you want to get to make a map of the chemical structure of the galaxy, of course, you have to get a distance to your tracer somehow. And for H2 regions, you can get a parallax distance, either from the stellar parallax of the ionizing stars, a maser parallax if the source has an associated maser emission, or a kinematic distance where you measure the radial motion of the object and use a galactic rotation model to infer a distance. So the idea here is if we can find all of the Milky Way's H2 regions, we could make a map of the chemical structure of the galaxy. Over the past 10 years or so, my collaborators and I have been working on the H2 region discovery surveys. These are pointed observations of infrared identified H2 region candidates, where we're looking for their radio recombination line emission to prove that they are in fact bona fide H2 regions. This kind of renaissance in radio recombination line science has really been enabled in the past 10 years or so by new technology. So wide bandpass receivers and flexible correlators that allow you to look at multiple radio recombination line transitions simultaneously. So for example, in our first experiment with the Green Bank telescope and the old spectrometer, we were able to observe 7 X-band radio recombination line transmissions simultaneously, which we can then average together and improve our sensitivity dramatically. Here's an example radio recombination line spectrum showing antenna temperature versus velocity here. This is a stack of 7 transitions, and so you see a very clear and bright hydrogen recombination line, a much fainter helium line, and then in this case, there's no evidence for carbon. So over about 10 years, we used the GBT and Arecibo for these experiments, and they were wildly successful. We observed about 1,000 infrared H2 region candidates, and our success rate was nearly 95%. And so we more than doubled the number of known H2 regions in the northern sky, in the part of the sky that we surveyed. Here's just a visual representation of that. This is a longitude velocity diagram showing in black the previously known H2 regions before our experiment, and in magenta, the newly discovered H2 regions as part of our single dish experiments. Of course, there's a little bit of a gap here. That's the southern sky part of the Milky Way. And so I've been leading over the past 6 years or so, I've been leading a southern extension of the H2 region discovery survey using the Australia Telescope Compact Array. Again, we lose a little bit of sensitivity since there's just not as much collecting area, but we make up for that a little bit because the ATCA has such a broadband receiver. The CX band receiver goes from 4 to 10 gigahertz, and the flexible backend allows us to observe 20 recombination lines simultaneously. We just published the latest data release from this survey, which adds about 400 new H2 regions to the galactic census. So now in total, over the past 10 years, we've more than doubled the number of known H2 regions across the entire sky. And so now we can start to do the fun stuff. Now that we have this census of Milky Way H2 regions, we can start to look for the chemical structure of the galactic disk, which is what I'm interested in. We had done this before using some of our single dish observations. So we used the single dish radio recombination line and radio continuum measurements to measure the line to continuum ratio. We used that to derive an electron temperature, and then we use this empirical correlation to infer metallicity. The primary limitation of those single dish studies, however, are the uncertainties, the systematic uncertainties in the continuum flux measurements. Because these H2 regions are located in the galactic plane, there's a bunch of diffuse foreground and background continuum emission that really makes deriving the continuum flux density uncertain. And so this is a prime example why the VLA is a great instrument, a great tool for this kind of experiment. The upgraded VLA in particular, because the WIDAR correlator allows us to observe multiple radio recombination lines simultaneously. So a few years ago, we had this VLA survey where we targeted about 100 H2 regions, some of which were the newly discovered H2 regions as part of our survey, and really short observations. They were only 10-minute snapshot observations, and that was enough sensitivity to give us electron temperature precisions between 1 and 10%, partly because we could average 7 different radio recombination line transitions together to improve our sensitivity. So we measure the line to continuum ratio, we get the electron temperature, we infer a metallicity, and then here are the results from that survey. So this is a face-on view of the Milky Way. Here at the red cross is the location of the sun. This is the galactic center, And the points here are all of the H2 regions for which we were able to derive metallicities in this survey, color-coded by their inferred oxygen abundance. And then the background color scale here is just kind of an interpolation between the data points. There's no points down here in the bottom left part of the figure, so it's poorly constrained, just ignore that. But what you can see is that there's a radial metallicity gradient. The metallicity of the galaxy is higher in the center of the Milky Way, which has been known and well measured using many different tracers for a long time now. But what we found that was fairly interesting was that there's kind of an azimuthal variation in that gradient. The Milky Way's metallicity structure does not appear to be azimuthally symmetric. I think this is easier to see in this right-hand figure, which is showing the slope of the metallicity gradient as a function of galactic azimuth, where 0 degrees is the direction from the galactic center towards the sun. In that direction, the metallicity gradient is fairly shallow. And as you move to higher azimuths, you can move clockwise on this diagram, the slope of that gradient can changes by about a factor of 2. It gets much steeper. So this is kind of interesting, and it's unexpected. It's not really explained by modern galactic chemodynamical evolution models. So something interesting is going on here. Of course, the obvious next step is to expand this to the southern sky. And since our southern H2 region discovery survey was already an interferometric survey, we get really precise electron temperatures and metallicities there kind of for free. And so I'm working with a co-op student, Aidan Mackay from the University of Victoria, to expand our survey to the southern sky, to expand our chemical structure analysis to the southern sky. And here are just some preliminary results showing the oxygen abundance versus galactocentric radius, and then another face-on map of H2 region abundances. The semicircle here is just an artifact of our kinematic distance method. You could just ignore that. So stay tuned. I think we're about to create the first Milky Way wide map of galactic chemical structure, which is going to be pretty exciting. But as just kind of a side note here, since these are interferometric surveys and we're getting these really nice detailed images, we had this idea that we could, for some of our resolved H2 regions, we could make a map of the physical properties of the nebula across the nebula. So the original idea here was to make a map of the electron temperature to see if you could see variations in the electron temperature across the source. So what we did was we took some of our data cubes from our VLA survey and our ATCA survey. We ran a Gaussian decomposition algorithm on those cubes, and then we made plots of the radio recombination line parameters across the source. And what we found was very unexpected, and here's just an example. So this is one of our VLA H2 regions, and this top left figure here is showing the fitted line center velocity across the source. You can see it's just barely resolved, but there's a very clear velocity gradient from one side of the source to the other, a gradient that varies by about 5 kilometers per second from one side to the next. The top right panel here is the uncertainty in the fitted line center, which you can see is very small. And on the bottom left, this is the fitted Foa-Taft max line width, which has a centrally peaked profile, and then it decreases as you move to the edge of the nebula. So this is kind of interesting. People have seen velocity gradients in H2 regions before, typically in compact H2 regions, and it's attributed to outflows. Sometimes you see it in the center parts of more classical evolved H2 regions. But what was interesting here is that we see this kind of kinematic structure in about 200 H2 regions between both our VLA and ATCA survey. What's going on? We're not entirely sure. We have run some really simple simulations. We've tried outflows and an expanding H2 region, but the only kind of simple explanation that makes sense is a rotating H2 region. And here are some results of that model on the right. So the top panel here is showing a rotating H2 region. The line width, the line velocity as it would appear, you can see a very clear gradient. And the bottom here is the simulated line width, again with essentially peaked profile. So is it a rotating H2 region? It's not entirely clear yet, although that seems to be the best explanation. We have some follow-up observations. I'm leading a project with the ATCA to get much higher angular resolution radio recombination line observations to maybe disentangle between some of these proposed models. And then also we have a VLA project led by Joe Dawson, where we're mapping recombination lines at L-band, as well as OH, which will allow us to see if this kinematic structure extends out into the molecular gas surrounding the H2 region. Here are just some preliminary results from our ATCA experiment showing with much higher angular resolution, the line center velocity and the line width for one of our H2 regions.
Hey, Trey, 1 minute.
Thank you. So just as the last thing here, I want to talk about what we're going to do in the future with NGVLA. Just the sensitivity and the angular resolution is going to allow us to do a lot of science. Step 0 is going to be to find the rest of the Milky Way's H2 regions. NGVLA will have no problem detecting radio recombination line emission from all O-star H2 regions in the Milky Way, and probably most of the B-star H2 regions as well. And as a bonus, if you observe at L-band, you can look for H1 absorption, which will allow you to resolve the kinematic distance ambiguity, look for OH masers, do some OH kinematics and recom line kinematics like I've talked about. So there's going to be just a whole bunch of science to do there. H2 region physics, of course, with the sensitivity, you'll be able to derive the electron temperatures with much more precision. But also something that's interesting is looking for magnetic field strengths, trying to measure the magnetic field strengths using the Zeeman effect. People don't really know that the radio recombination lines are sensitive to the Zeeman effect. And so in principle, this could be a new tool to measure magnetic field strengths in high mass star forming regions. And then finally, because it has such great angular resolution, you'll be able to take a lot of what we've done in the Milky Way and do it extragalactically. So have an unobscured and unextincted measure of the total high mass star formation rate in external galaxies, and also tracing out the diffuse ionized gas. So just to conclude here, H2 regions are a great tracer of galactic structure, and over the past 10 years, we've more than doubled the number of known Milky Way H2 regions. Follow-up surveys with the VLA have found interesting azimuthal structure and the Milky Way's chemical structure, as well as what appears to be a large population of rotating H2 regions. And I'm really excited to see what the NGVLA is going to enable in the future in terms of radio recombination line science. Thank you.
Cool. And we'll take a couple minutes for questions, I think. Yes, for anyone, just please chime in or raise your hand on Slack. We have got 2 claps.
Looks like John's asked a question about cloud collisions. Instead of a rotating H2 region, could it be a cloud collision? I haven't looked into that, John. That's an interesting idea. We will add that to the long list of possible explanations.
I was curious too that if you had high resolution follow-up observations planned, because if you just had 2 H2 driving sources in the center and they're offset in velocity and they're marginally resolved, then you'd get a gradient that would kind of look like rotation.
Yep, which is exactly why we went to the higher angular resolution to see if that was what was going on.
Oh yes, yeah, cool.
Any other questions?
Well, if anyone's had more questions for Trey, please throw them in the Slack, and I'll hand off this session to Danielle Lucero, who will be chairing the next talks.
Thanks, Brian. Can everybody hear me? So I'll make sure. In case you've just joined us, this is quite a long session. The Slack channel for this particular session, if you want to have discussion outside of the talks, is session 7-THU-mid. So you can go there, put down and chat. But with that, I'd like to introduce the next speaker. By the way, I will keep to what Brian was doing with giving a 2-minute warning to each speaker. So just keep that in mind. For the first speaker of the rest of this session, it will be Min-Young Lee, and she will give a talk on unrepresented view of the cold neutral medium in molecular clouds revealed by ESPLR. Go for it.
Do you see my slides?
Yes, but you're not in presentation mode.
Yes. Excellent. Gonna have the pointer. Hello, everyone. Today, I will introduce our VLA H1 absorption survey called ESPLR that aims to measure the cold neutral medium in molecular clouds. First, I'd like to start my talk by stressing that H1 is one of the key ingredients in the formation and evolution of molecular clouds. In our rough understanding of a molecular cloud embedded within a warm H1 envelope, the cold H1 is accreted onto the cloud and condensed into molecular gas. This idea of the buildup through accretion was observationally confirmed in the Large Magellanic Cloud, where the H1 mass of molecular clouds increases as star formation progresses. However, exactly what roles the cold H1 plays in the formation and evolution of molecular clouds remains highly uncertain, simply because observing the cold H1 directly requires unique observing techniques. So in this talk, I will mainly talk about two flavors of H1, the cold and warm neutral medium. Among them, the CNM is expected to be more critical for the formation of molecular gas thanks to its colder temperature and higher density. Observationally, these two flavors can be separated by having on and off measurement. The on measurement is made toward a continuous source behind the cloud and measures the CNM in absorption. Since the diffuse emission from the cloud should be resolved out, the on measurement is typically made using interferometers like the JVLA. On the other hand, the off measurement is made around the continuous source and measures the CNM and WNM in emission. Since the diffuse emission from the cloud should be detected, sensitive single-dish telescopes like Arecibo are used. The obtained spectrum is often called expected emission, since this is what we would expect toward a continuous source, but without the source. So these on and off measurements have been made numerously to examine the properties of the CNM and WNM in the Milky Way. For example, this shows the CNM fraction, which is defined as the ratio of the CNM column density to the CNM plus WNM column density toward 77 quasars probing galactic molecular clouds. In this case, both on and off measurements were made using Arecibo, and the target clouds include the famous ones in the solar neighborhood, such as Perseus, Taurus, California, and Rosette. As you can see, however, it is very difficult to see any trend in the CNM fraction, mainly because the observations are limited to bright sources only, and they are almost randomly located across the sky. So this strongly calls for an H1 absorption survey dedicated to the main body of molecular clouds, where the CNM is expected more abundant. And this is where our H1 survey comes in. The espoir is hope in French, but means earliest stage of star formation proved by observations of interstellar absorption for us. So we designed this survey to provide specifically unprecedented source number density, and we achieved this goal by measuring H1 absorption along 62 line of sight, probing in and around the low-mass star-forming cloud Perseus. The observed continuous sources are shown here as crosses on the 12CO120 integrated intensity image. And depending on the presence of CO emission, the crosses are shown in blue or in red. So for our survey, I have to emphasize that the VLA is a key to success of our project, since its high sensitivity allows us to measure H1 absorption toward sources as weak as 0.1 Jansky. This sharply contrasts to the previous Arecibo observations that were limited to the sources stronger than 1 Jansky. So there is order of magnitude improvement in our VLA survey. To stress one more time our unusually high source number density, here I compare the previous Arecibo measurement. So please pay attention to our much smaller spatial scale compared to this. With espoir, we are gonna address the following science goals. First, we will measure the CNM in and around Perseus in detail. Second, we will prove the roles of the CNM in the formation of molecular gas. by combining the SPOA data with the CO observations. Finally, we will constrain the CNN occlusion rate. As for the current status, the observations were made over 3 different semesters, comprising almost 100 hours. In this talk, I will present the preliminary result for 14 out of 62 spectra. Among the 14 spectra, 2 were found to be saturated, and expected emission spectra were extracted from Arecibo Alpha H1 survey. Then the obtained absorption and emission spectra were analyzed following highly central in 2003, so-called Gaussian decomposition method combined with radiative transfer equation to derive the physical conditions of the CNM and WNM, such as the opacity, spin temperature, and column density. So from now on, I will present some science result based on this Gaussian decomposition method. So here, this shows the CNM spin temperature along 12 observed line of sight as circles. So color represent the values. And then the background is the 12CO120 integrated intensity image, and prominent dark and star-forming regions are indicated. As you can see, the spin temperatures are particularly low in IC348 and B1 East areas, as well as in the west end of the cloud. Interestingly, these spin temperatures are systematically lower than what we randomly measure in the local interstellar medium. For example, this gray histogram shows the spin temperature distribution for SPOA, which is compared to the previous Arecibo measurement shown here as the black histogram. For fair comparison, the Arecibo line of sight are limited to galactic latitude lower than -5 degrees. So in summary, our result suggests that the CNM spin temperature is colder in the main body of Perseus and changes across the cloud. Similarly, this shows the CNM fraction along 12 observed line of sight as circles. The measured CNM fraction is found particularly high in the B5, IC348, and B1 East areas, and decrease toward the outskirts of the cloud. But note that the CNM fraction never reaches 1, meaning that there is always some amount of the WNM. Nevertheless, our CNM fraction is systematically higher than what we randomly measure in the local interstellar medium, shown here as the black histogram, suggesting that the CNM is more abundant in the main body of Perseus. So I finished my talk with some conclusions. So first and foremost, our preliminary result clearly show that the properties of the CNM evolve in and around Perseus, which hint that the CNM is closely linked to the formation of molecular gas. And with unusually high source number density, SPOA will shed light on the roles of the CNM in the formation and evolution of molecular clouds. And finally, but not least, our survey will serve as a key stepping stone toward NGVLA and SKA, whose exceptionally high sensitivity will produce a large amount of H1 absorption spectra. And that's all I have, and I will take questions from now on. Thanks.
Thanks, Min-Young. You actually finished a minute or so early, so we have plenty of time for questions. Anybody has raised it? It has been very interesting to see how you do this kind of work in at cloud scales. I myself am very interested in the H1 to H2 ratio, but of course, extragalactic. So very different resolutions and ways of determining the fractions.
Yes, so VLA makes this survey possible, I think, because the previous measurement were limited to bright sources only, but now with the VLA, we can get the very faint sources probing the CNM directly inside a cloud.
I have a question. With your defining of the filling factor, isn't that a hard to define in some sense? And it must be an area filling factor that you're considering to start with, isn't it? That the fraction of the area on the sky subtended by the molecular cloud has a CNM in it. But then that requires that you be able to draw a boundary to the molecular cloud. And isn't that difficult, or is it not difficult?
So the filling factor you mean mainly by the CNM fraction we derived? Do you mean by the CNM fraction?
You were talking about the fraction that was occupied by the CNM, and we're saying that was larger in Perseus than local molecular clouds. So,
so
that's what I'm calling filling factor.
Filling factor, right. But remember that our measurements are absorption, which means that our measurements are done in pencil beam way. So there is less concern about the beam dilution in this case, especially for the CNM. Because our measurement is mainly limited by the size of the continuum source, which is a point source in our case with a VLA. So yes, there is less concern for the beam dilution in our case. Does it address your concern?
Yes, thank you.
Yeah.
All right, thanks everyone. I think we better move on now. So if anybody has further questions, you can ask them in the Zoom chat or the Slack channel. Moving on.
Thank you.
Thank you. Our next talk will be given by Snezna Stanojevic. She'll be giving a talk on 21 SPONGE, New Perspectives on the Neutral Interstellar Medium in the Milky Way.
Thanks, Daniela. Hi, everyone. It's great to be here virtually and celebrate 40 years of wonderful cutting-edge science done by the VLA. And I just want to take this opportunity to congratulate all NREO staff members. So I'll stay with the H1. Min has started talking about H1 and H1 phases. And together with Claire and Murray, I would like to tell you a little bit about the project that has been going on for quite a few years now and has primarily been possible with the use of the VLA. So we call this project 21 SPONGE, and this title stands for 21 centimeter spectral line observations of neutral gas with the VLA. Our collaborators, long-term collaborators, are Miller Goss, Carl Heiles, John Dickey, Brian Babler, and this project was really possible with the hard work of many undergraduate students at the University of Wisconsin in Madison. So Min already hinted and showed how important H1 is for galaxy evolution in general, and it occupies a very important space in the ISM between hot and warm ionized gas and cold and dense molecular clouds. So as we heard from Min, H1 represents fuel for the formation of molecules, fuel for the formation of giant molecular clouds, and those eventually lead to star and planet formation. So constraining and understanding physical properties of H1 and how those influence formation of molecules, formation of giant molecular clouds, and therefore star formation is really very important, especially as a function of different interstellar environments. So we already heard about two main flavors or phases of H1, the warm neutral medium and the cold neutral medium. And quite often we like to sort of show that as a phase diagram. So by considering thermal equilibrium and heating and cooling processes, we can plot thermal pressure as a function of volume density And generally, H1 gas congregates into two thermally stable phases, the warm gas and the cold gas. And in the case of weakly turbulent medium, the land in between, which is supposed to be thermally unstable, is not very heavily populated. Another way we can plot this is we can just basically ask the question of what's the mass fraction of H1 in the Milky Way as a function of spin or excitation temperature, and that's shown on the right-hand side. So based on the phase diagram, we have two peaks, the cold neutral medium peak of this histogram and the warm neutral medium peak, and then unstable gas in between. So for many, many years, starting with early 70s, and VLA has really played a very important role in these studies, we have been able to measure very sharp absorption lines coming from the cold gas and constrain its spin temperature. So one example here is coming from Strasser, Dickey et al. 2007, where you see basically histogram of excitation temperature, and that nicely peaks at about 50 Kelvin and corresponds well, relatively well, to predictions from state-of-the-art numerical simulations. So this is that first blue bump that corresponds to the cold neutral medium. However, for many years, we have been wondering what's happening beyond the temperature of about 100 Kelvin once the H1 starts to warm up and transitions more towards the warm neutral medium. And essentially, there have been only sporadic observations, many of those done with a VLA, like an example shown here by Wagner, 2002, where by looking in the direction of strong background sources, we detect very sharp absorption lines and then some very, very weak line wings that correspond to temperatures of the warm neutral medium. But really, one of the key problems for many, many years has been, can we actually match or can we actually reproduce the numerically predicted or theoretically predicted histogram, and can we actually detect that second peak that corresponds to the warm neutral medium? So this is really one of the key goals for 21 Sponge, which actually represented a giant portion, basically all of Claire Murray's PhD thesis, wonderful PhD thesis. And for this project, we observed using VLA H1 in absorption in the direction of 57 background faraway galaxies, basically point sources, with exceptional sensitivity. So we really integrated long and deep and achieved optical depth sensitivity of about 10 to the minus 3, a few times 10 to the minus 4. So this project took about 600 hours of VLA time, so this was a substantial telescope investment. All of the time was basically in a filler mode. That's where the name really comes from. This project has been sponging away tiny little gaps in the VLA telescope schedule and collecting slowly integrations and building up sensitivity for our spectra. So on the bottom left-hand side, you can see the spatial distribution of our sources. So we mainly targeted higher galactic latitudes because H1 is much easier to deal with at high latitudes. And let me just show you a brief movie. Basically, this project was possible only with the upgrade of the VLA. So I have at the start a spectrum, an absorption spectrum obtained with the VLA prior to the upgrade. And you can see a lot of wiggles and bumps. Some of those we're not even sure are real absorption lines. And then a little bit later, another spectrum will show what happened early on as the EVLA started. So it's again, slightly choppier spectrum, arriving in the final spectrum, which is sort of at the end once the upgrade was finished. So basically, the upgrade of the VLA really contributed greatly to the phase stability, which was essential for this project. So besides 600 hours of telescope time, we also worked with state-of-the-art numerical simulations. So we had about 10,000 spectra, simulated spectra, synthetic spectra of H1 absorption and emission from Kim and Ostreicher to basically quantify our observational biases and radiative transfer calculations. So just a brief summary of what his 21 sponge achieved. So some of the key questions we went after is the fraction of the thermally unstable gas, temperature of the warm neutral medium. We have developed outstanding automated routines for calculating spin temperature, and some of those have been used and further developed by other groups and are now heavily being used for other observations. We looked into correction of H1 optical depth, small scale structure, and many other groups have actually used our data in connection with other observations and have done really wonderful science. In particular, Dan Robarczyk, after me, will talk about a project called ALMA Sponge, which is actually ALMA complement to 21 Sponge, which is probing and trying to understand formation of molecules in the ISM. So, yeah, just briefly, let me give you a few highlights. This is GaussSpy. Many of you have probably heard about this, the autonomous Gaussian decomposition tool developed by Bob Lidner and now being used by other groups. This has been instrumental in constraining observational biases. Can you give me a minute, Stephanie?
No.
Oh, yeah, wonders of working from home. This is fun. Okay, my apologies. I'm having a little helper here who's trying to help me with my talk. Nikki, this is a conference. This is not nice. Okay, Stefan, please. Okay. All right. Yeah, I think my son has taken away probably a few precious minutes from my talk. So yeah, anyway, fun stuff. Okay, so yeah, so basically the synthetic spectra have been instrumental in constraining our observational biases and really figuring out, allowing us to figure out completeness issues and also understand what's happening with our derivation of the spin temperature. So let me move on. So yeah, as I started, we really wanted to constrain the second portion of that histogram of the temperature distribution. And really go after that warm neutral medium. And you can see on the left-hand side in gray, our best, basically our final result. So this is really showing the H1 mass fraction as a function of spin temperature. And you can see that we have managed to extend the temperature distribution to higher temperatures. And basically the survey was designed to be able to measure all spin temperatures up to 4,000 Kelvin. And that 4,000 Kelvin is really what numerical simulations are telling us that the highest temperature of the warm neutral medium should be in the Milky Way. So the survey was designed to be able to measure that, yet, as you can notice, we are not really seeing still that peak of the warm neutral medium. We were able to constrain fractions of gas in the cold neutral medium, about 30%, the unstable gas of about 20%, and the rest is, of course, warm neutral gas of about 50%. So, yeah, it's a really, so the unstable fraction has been—
You have 1 minute, Snissa.
Topics for debate, and many numerical simulations have been working on this. So I'll just skip and tell you that by doing a stacking analysis and adding a bunch of spectra, we have been able to measure a very high temperature for the warm neutral medium of about 7,000 Kelvin. And what this really suggests is that, yes, numerical simulations are about right, but that second peak that corresponds to the warm neutral medium should be shifted to the right-hand side. Essentially, the Lyman alpha photon flux is prominent in the Milky Way, and that provides secondary excitation for the 21 centimeter line and essentially pushes that peak of the warm neutral medium to the higher, to the right, to higher temperatures. Okay, so I will also just highlight briefly work by Dan Robarczyk on double sources. So a good fraction of our sources in the 21 sponge survey are double sources. So essentially by taking and comparing absorption spectra in the direction of two lobes, we can essentially probe structure in the interstellar medium, in the cold neutral medium, on spatial scales of few astronomical units. And this has been very interesting because Dan has been able to quantify that the level of variability in H1 absorption spectra correlates strongly with the hydrogen column density and the hydrogen optical depth. And what that really tells us is that those AU scale structures in the ISM are more prominent in the disk of the Milky Way, where there is some secondary excess energy excitation and turbulence driven likely by supernova remnants. And I will skip this part, work in progress, trying to constrain the CNN scale height and spatial variations. So these are briefly my conclusions. Dan will continue next. And I just want to emphasize that the future of H1 absorption is very bright, and GVLA will allow us to basically probe the H1 phases across different interstellar environments, not just in the Milky Way, but to really get out into many nearby galaxies where metallicity, interstellar radiation field, and other parameters are very different. Okay, thank you very much. I'll stop here.
Thank you so much, Snezna. We have time for maybe one question before we have to move on. After that delightful interruption.
Yeah, just not about a jet lag kid who doesn't want to go to bed because he's at the US time zone and right now we're in Serbia.
Understandable. Well, if anybody thinks of a question they have for Snezna, please put it in the Slack channel or in the chat here in Zoom. But if not, we might as well move on to Daniel. Next talk is, as Snezna mentioned, Daniel Verbeertje. He'll be talking about constraining atomic conditions suitable for formation of diffuse molecular gas. Take it away, Daniel.
All right, can you see my screen?
Yes, I can.
Okay, great, thank you. So yeah, thank you for allowing me to discuss this work. And the project I'll be discussing, as Snez alluded to, follows naturally from her previous talk on 21 Sponge. So we're here to commemorate the VLA. So I wanted to briefly state from the outset why this talk is relevant. And so as we saw in previous talks, especially the previous two talks, sensitive absorption measurements made by the VLA provide environmental constraints on cold atomic gas in the Milky Way. But the significance of these constraints isn't just limited to studies of the H1. We can also use them to characterize environments where diffuse molecular gas forms. So some background, as we've already heard, the atomic ISM is a turbulent and multi-phase medium. Most of the H1 is found in the stable warm neutral medium or cold neutral medium, while about 20% of the H1 is in a thermally unstable phase with intermediate temperature and density. Now, I'm sure we've all seen this image showing star formation process, and here I'm talking about the very early stages of this process where molecular hydrogen and other important molecular species form out of the diffuse atomic ISM, where the visual extinction is of order 1 or lower. And as has already been pointed out, the multi-phase nature of the H1 is relevant to molecule formation in the diffuse ISM. So as Min has already discussed, molecular clouds tend to be surrounded by H1 with a higher CNM fraction than just randomly distributed sightlines, which is shown, for example, in this histogram from a 2014 work by Snez. And so also from a theoretical side, Shmuel Bialy and others have shown that the fraction of H1 in each thermal phase, so in the WNM, the CNM, and the UNM, significantly impacts the H1 to H2 transition layer. So this multi-phase nature of the H1 is really important when we're talking about atomic to molecular transition. So of course, understanding the chemistry is also crucial to understanding molecule formation. And chemistry in the diffuse ISM is often modeled as photodissociation regions, PDRs. So here's a schematic of a PDR from Hollenbach and Thielens, where UV photons are attenuated by dust as AV increases to the right, causing the abundances of various molecular species and the temperature to change deeper in the PDR. And PDRs have been used to successfully predict molecular abundances for a variety of species. But PDR models calculate molecular abundances assuming steady state. However, non-equilibrium chemistry, driven by shocks or turbulent dissipation, for example, is believed to play an important role in enhancing the formation of certain molecules, often by over an order of magnitude. So I recommend Benjamin Goddard's work on turbulent dissipation regions for a much more detailed discussion of this problem. And later in this work, I'll discuss how we use H1 gas properties to constrain PDR model fits, and then how those results can be interpreted. So this brings me to our observations. Here I tried to summarize the 21 sponge and ALMA and NOEMA sponge observations. So on top is the overview of 21 sponge, which you should now all be familiar with, thanks to Snez's wonderful talk. As a reminder, they obtained extremely sensitive 21 centimeter absorption measurements from the VLA, and with complementary emission from Arecibo, they constrained the atomic gas properties in the diffuse ISM for 57 lines of sight. And for each line of sight, they derived the H1 column density, as well as the fraction of H1 in each thermal phase. Then for individual components, they derived the spin temperature, line width, optical depth, and column density. Now, with two new projects, we've obtained observations of 3 millimeter absorption in the direction of 20 of the 21 sponge background sources using ALMA and NOEMA. And so by observing the same background sources at 3 millimeters, we now probe the molecular component of the gas structures observed by 21 sponge. So we derive the line of sight column densities for the ground state transitions of HCO+, C2H, HCN, and HNC, and we measure the peak optical depth, line width, and column density of individual diffuse molecular gas structures. And so using the complementary atomic and molecular line observations, we can address some key questions about the role of H1 in molecule formation in the diffuse ISM, including what atomic gas properties are required for molecule formation, how does the amount of thermally unstable H1, so the H1 in the UNM, correlate with molecular column densities, and how can constraints on the atomic gas properties inform PDR modeling of molecular gas. So we can try to address these first two questions by looking at the line of sight column densities of different species. So in these plots, the y-axis shows the molecular column densities, and each shape represents a different molecular species, and then colored points show detections and are colored by the dust temperature, which I won't discuss here, but which is addressed in our paper. And non-detections are shown as gray 3 sigma upper limits. So in the bottom left plot, the x-axis is the column density of all of the cold H1s. That's the CNM plus the UNM. And you can see that molecular gas is found only where the cold H1 has a column density greater than about 10 to the 20 per square centimeter. Meanwhile, in the bottom right plot, we look just at the UNM column density on the x-axis. Now, there's no correlation here, but there's still a clear dichotomy of sources, where the sources with the highest molecular column densities also have high UNM column densities. And the fraction of H1 in the UNM is 30 to 70% for these sight lines. All of the other lines of sight have very little UNM gas. And this is suggesting then that the UNM gas likely plays an important role for molecule formation and survival. Of course, the UNM does play a role in shielding, and these are high UNM column densities, but it also can trace the turbulent mixing of the cold neutral medium and warm neutral medium, which can lead to the enhanced production of certain molecular species, which may contribute to this observed trend. So now I'll very briefly mention an interesting observation in the HCO plus absorption. So in this plot, we show the HCO plus optical depth as positive in blue and the H1 absorption as negative in red. So for some sources, including the one shown here, we detect HCO plus absorption across nearly all velocities where 21 sponge detected H1 absorption, including this broad faint component outlined in the green regions here. And we see this broad underlying component in a majority of sightlines with HCO+. So this suggests that a low level of HCO plus is common in the diffuse ISM for sightlines with a significant amount of cold H1. And then from the H1, we can measure the optical depth weighted mean spin temperature, which is essentially a proxy for the cold neutral medium fraction. And we can do this for each of the velocity ranges, which is what we do in this plot here. So I know it's a little confusing, but we compare the integrated HCO plus optical depth on the y-axis to the optical depth weighted mean spin temperature for each region outlined in this plot for all of our sources. And so the points in blue are for where we see strong narrow HCO plus absorption. And these points in green, the diamonds, are for where we see just this broad faint component to the HCO plus absorption. And you can see that these blue points where we see strong absorption have a lower value, whereas the points where we see just broad absorption have a higher value, which is indicating that the CNM fraction is lower for gas at these velocities where we see the broad weak absorption, perhaps suggesting that this HCO plus traces slightly warmer regions of the diffuse ISM. All right, so again, thinking about what H1 properties are required for the onset of molecular formation, we looked at the individual components identified in the H1 and molecular line absorption spectra. So we identified H1 features with a molecular component. So here's a clear example. You see a negative 10 kilometer per second here in black, in the H1, which is associated with molecular absorption for all 4 lines. So then in these cumulative distribution functions, we compare all of the H1 features along our 20 lines of sight in black to just those that have a molecular component, like this negative 10 kilometer per second feature, in different colors. The different colors represent the different molecular lines, but we don't see a significant difference between the different lines. But what the CDFs do show is that H1 features with a molecular component have systematically lower spin temperature, higher optical depth, and a marginally higher turbulent Mach number than the total population of H1 clouds in these directions. So specifically, all of these structures have spin temperature less than 80 Kelvin, while about 40% of all H1 features are warmer than 80 Kelvin. They have optical depths greater than about 0.1, whereas about 60% of all H1 features have optical depths less than 0.1. They also have a turbulent Mach number
2 minutes
greater than about
left.
2. Thank you. But that's related to the fact that they have a lower temperature and doesn't necessarily signify a higher level of turbulence. So most previous molecular absorption line observations haven't had access to these kinds of environmental constraints. And these are valuable for a number of reasons, because they indicate what kinds of diffuse environments are conducive for molecule formation. And they can also be tested against predictions from chemical models, which brings me to my last point. So finally, we test how the observed molecular column densities compared with PDR predictions, given the H1 constraints, so that given the H1 spin temperature and optical depth. So we worked with Munan Gong, who developed a PDR code that solves for the evolution of different species, including H1 and HCO+. So on the right are some plots from Munan's 2017 paper showing how abundances of different species vary with AV under different environmental conditions. Now we ran a grid of PDR models with fixed density, UV field strength, and cosmic ionization rate incremented by factors of 10. And then using both the H1 constraints and the observed HCO+ column density, we identified the PDR model that best matched observations. So what we find is that features fall into 2 categories. All of the features with spin temperature less than 40 Kelvin were fit by PDR models with densities, radiation fields, and cosmic ionization rates expected for diffuse molecular gas in the solar neighborhood. On the other hand, all the features with spin temperature greater than 40 Kelvin require higher densities, stronger interstellar radiation fields, and higher cosmic ionization rates than would be expected for diffuse molecular gas. So they're more similar to what would be expected close to, say, H2 regions. So just quickly, these plots show the HCO+ column density versus the H1 optical depth. The points are colored to the H1 spin temperature, and then the model fits are shown and labeled by density. So in some, but not all cases, we find that the fits for the higher spin temperature features are implausible based on previous observations for some sightlines that reveal no sites of nearby young star formation and suggest that densities of 10 to the 3 or 10 to the 4 are far too high. So this suggests then that some structures in this category mark sites of non-equilibrium chemistry, where the PDR model fails, likely because of the steady state assumption. So sorry for going a little over. Here are my conclusions. And if there's time for questions, I'll be happy to take them.
Thank you so much, Daniel, for a very interesting talk. And I see how this very well highlights SNESMA's previous work. So do we have questions for Daniel? Everybody's getting tired in the end of the day. We have plenty of time, 2 minutes still. You didn't go over that much.
Okay, great.
So if you have any more points you want to make while people are thinking.
I think I'll just leave these here, and if anybody has questions, I can fill them here or in the Slack.
Yes, I've definitely thought about how often these equilibrium cases actually occur in reality. And we always try to start, in the ideal, easy way, but it looks like PDR modeling definitely has to be updated. Okay, well, if there are no questions for Daniel, we can move on to the next speaker, which is Stephen Spengler. Thank you. Stephen, go ahead and share your screen. Remember, if you think of questions for Daniel, you can put them in the Slack channel. Stephen's going to give us a talk on the VLA as an instrument for plasma astrophysics measurements.
Okay, can you hear me and see my slides?
Yes, we can.
Okay, very good. So as the host has just indicated, the title of my talk is the VLA as an instrument for plasma astrophysics measurements. I'd like to start, as some of the other speakers have done, with a little bit of a personal view. This is a wonderful occasion to be able to speak at and to participate in the 40th anniversary of the dedication of the VLA. My first trip to the VLA was in January of 1977, when I worked with Fraser Owen on a project. And it was really exciting at that time to see this instrument, which was the future of radio astronomy. And at that point, we had 3 or 5 antennas working, and part of the time. So I think there were 3 at a given time. But still, it was exciting to see this. And it was exciting to be part of the NRAO in the late 70s, early 80s as a staff member here. And so now we've had 40 years of this, and as Luis Rodriguez said yesterday, I think one of the greatest tributes to the VLA is the fact that at this meeting, we have papers presented, and in some cases invited papers, by scientists who weren't born at the time of the dedication of the VLA. I guess my main reflection on this time is to acknowledge the engineers and scientists and all the NRAO employees who brought this project to fruition. And there were very many challenges during that time, but they built this magnificent instrument. And I haven't heard reference to the point, but in around 1980, it was brought up a lot that it was the VLA was an example of a large federal project that came in on budget and on schedule. And so again, we should acknowledge the NRAO staff at that who made this possible. All right, so getting on with my talk, the basic idea here is, again, most astronomical media, maybe a large majority, are sufficiently ionized so that electrodynamic phenomena are important. And so then that means that the branch of physics that is going to help us a lot is plasma physics. So if we're going to understand the plasma physics processes in our astrophysical media, we have to get what are called plasma diagnostics of them. Measurements of basic plasma parameters such as density, magnetic field, flow velocities, electron and ion temperatures, and so forth and so on. And radio astronomy is very good at this for reasons I'll describe here in a moment. And radio astronomy has helped diagnose a number of media, and the VLA has played an important role in this. And some of the media that for which we have knowledge of the plasma properties there's a wide list here, but is the interstellar medium, The solar wind and the solar corona, I'm drawing a somewhat artificial distinction between those two. The intra-cluster media of clusters of galaxies, and the Earth's ionosphere. Now, probably most people participating in this meeting say, well, I'm not interested in the ionosphere, but I think as Joe Lazio's talk this morning indicated, that if you want to do a certain large class of measurements, you'd better be interested in the ionosphere because it's doing important things to your signals. Now, the bottom line in this slide gives a remarkable fact that the same instrument, the VLA, has contributed to studies of all of these plasmas. And as one example, for instance, is a Faraday rotation measure of a few radians per meter squared can be typical of a line of sight out through the galaxy at a large galactic latitude, a line of sight through the solar corona at a distance of about 10 solar radii from the center of the sun, or the Earth's ionosphere. And so that's it's kind of remarkable that that's true, but it's helped the VLA contribute to all these fields. Okay, so what I mainly want to talk about is the basic physics of how do you extract the information on a plasma medium that is out there using radioastronomical techniques. And I think the way that has most interested me is by radio propagation effects. And this comes from, utilizes the basic physics, the refractive index of electromagnetic waves in a plasma. And this is an expression then, the refractive index squared, which is the square of the ratio of the speed of light to the phase speed of the wave, is then given by this expression right here. This is taken from Dwight Nicholson's textbook on plasma physics. So the parameters here, omega is the angular frequency of the electromagnetic wave, 2 pi times the regular frequency in hertz. Omega p is the plasma frequency, a natural jiggle frequency of plasmas, which is a property only of the density, and omega e, which is the electron gyro frequency. So here is this expression. Now, one of the best approximations one can make in all of plasma or all of physics is that omega is much, much larger than either of these fundamental plasma frequencies. So you can do an expansion and come in with an expression like this. So at the bottom, the square of the index of refraction is 1. It's minus the first time is the ratio of the plasma frequency to the frequency squared. That is dependent only on the density of the medium through which the waves are propagating. And then there's another much smaller term, which involves the electron gyro frequency, and that then is sensitive to the magnetic field as well as the density. Now, as I say, this is much, much smaller than this one, so you think you could ignore it, but the plus and minus indicates the plus refers to one sense of circular polarization, the minus to another. And that is the basis of the phenomenon of Faraday rotation, which Jason Cooey described so well yesterday, and which is a technique that has been used throughout radio astronomy. Okay, so this is kind of an indicator of what's happening. And the rest of my talk is largely going to be dealing with the effect of plasma turbulence on radio astronomical observations, which has interested me. So let's say here in this case, it illustrates the solar corona or the solar wind, although it could be more general than that. And we have radio waves propagating from a distant source, say an extragalactic radio source going through this medium. And these blobs here would indicate regions where the plasma density of the magnetic field was elevated over the normal value. And so after a certain amount of time from when this wave comes in, the phase will be more advanced than the average, in some places less advanced than others. And that leads to a whole host of phenomena, such as, for instance, an initially plane wave will then get tilted or converging phase fronts, causing a focusing in some regions, defocusing in others, so you'd see intensity variations. Alternatively, from an interferometer point of view, appropriate for considering the VLA, what's going to happen is there's going to be a phase difference introduced with an interferometer, depending on what this line of sight, the separation between the line of sights. And so depending on the details of what path was followed by these radio waves, there's then a interferometer phase difference. And if this whole medium is moving, or if the radio source or the radio telescope is moving with respect to the medium, these will vary with time, and that causes then scintillations. Well, so these effects depend on the magnitude of the fluctuations that are there, the spatial spectra. In other words, are there a lot of fluctuations on small scales, or all the fluctuations on large scales? And the frequency of observation. So that's why people who do these sorts of observations will make observations at a number of frequencies. All right, well, here are some of the effects, the types of scintillation phenomena that occur. There's a whole panoply of these, and all of these have been observed with the VLA, but the one that is probably most relevant is that of angular broadening. And so this then indicates the visibility that would be observed with a radio source versus the baseline length. And if we'd consider a point source, in the absence of a turbulent medium, it would just be flat at a normalized visibility of 1. If there's a turbulent medium there, you get rays scattered in from different lines of sight. And so the source then appears as blurred. So you can measure this angular broadening and infer properties of the medium. And again, all of these effects have been observed in the case of the VLA. Now, I decided to choose one paper to illustrate the contributions the VLA has made to the study of turbulent plasmas, and I gave some thought to this. And the one that I chose was a paper by John Armstrong of the Jet Propulsion Laboratory entitled Observations of Field-Aligned Density Fluctuations in the Inner Solar Wind. So this then refers to using the VLA to study turbulence in either the outer corona or the inner solar wind. And this was published in the Astrophysical Journal in 1990. Now, yesterday, when Tim Bastian gave his talk, I was telling him he stole my thunder because he actually cited this very same paper to illustrate some of the contributions of the VLA to solar astronomy. And I think it's then the fact that both of us independently came up with this paper is an indication of what an important result it was. So here's what John and his colleagues presented. This is the normalized visibility. So here one would be a completely unresolved source. Here's the projected baseline here. And
2 minutes left, Stephen.
Here we have the measurements that were reported, and it looks like they didn't calibrate their data properly. But what they were doing in this plot was just to show the raw baseline length, not taking any account for what the orientation is. But it turns out if the irregularities are anisotropic, then the scattering is also anisotropic and has an elliptical form. And when they took that into account and fit for an axial ratio or an anisotropy of scattering, they got this beautiful result here, which is about as good a fit as you would have in any area of physics, and indicated that the scattering is asymmetric, and it indicates that the irregularities responsible for it are anisotropic as well. And so what they further show, this is the heliocentric distance in solar radii going from about 1 to 30 solar radii. And what they found is outside about 10 solar radii, this number is about 2 or 3. Inside, it can get to be very, very large. So what this then indicates is the irregularities responsible for interplanetary scintillations or turbulence in the corona are strung out, they're anisotropic, and they're strung out along the magnetic field. And this is a quote from a later paper by Russell Grahl et al. Russell Grahl was a student of Bill Coles at UC San Diego. And so he's saying those irregularities may be an indication of a plasma mode that is responsible for coronal heating and the acceleration of the solar wind. Now, the final slide I'd like to have is to make an emphatic sort of endorsement of the paper presented by Jason Cooey yesterday, which is the collaboration of VLA results with those of the Parker Solar Probe. Now, the Parker Solar Probe is a spacecraft that is getting ever closer to the sun. Yesterday, about the time we began our talk, or our meeting, it began its 9th perihelion encounter. It will be at perihelion next Monday when it's about 15 solar radii from the center of the sun. For point of reference, 1 AU is about 215 solar radii. So what we're going to be able to do is in the future with Jason and his group doing this is to make a comparison between the observations that can be made remotely with the VLA and hopefully the NGVLA in the future, and direct measurements with magnetometers and plasma instruments. And this then points to the importance for going forward the NGVLA. The Parker Solar Probe won't last forever. We should use this opportunity to learn a lot about making this comparison, checking them out, maybe sort of seeing the degree of agreement, and trying to understand where there isn't agreement. And then in the future with NGVLA, we can continue to study the inner solar wind and outer corona. Thank you, and I'll try and answer any questions.
Thank you so much, Stephen, for that historical perspective. Moving on to the future. Does anybody have questions? Anecdotes? Jason, did you want to say your comment?
I was just going to say, in the continuing tradition of coronal angular broadening, Tim Bastian and colleagues have done some really interesting stuff with it in the last couple of years with the VLA. So I don't know, maybe Tim wants to comment too, but maybe on Slack.
Well, there's still a few moments, so go for it.
One paper. So. Tim, did you want to say something? I guess he's infuriated with me that I didn't mention that, but anyway.
His comment, the magnetic field is generally ignored in the refractive index. Other than FR, can you think of scattering phenomenon where its inclusion might be important? Jean asks why you're showing Quanah Parker and not Jean Parker.
Yes.
Okay.
Okay, thank you.
Thank you. We'll move on. We have now come to the last speaker of the session.
Can I make just a quick comment? This is Tim Bastian.
Sure, Ken.
Turns out, Steve, I was not infuriated. I was simply unplugged from my USB device.
I'm glad to hear that. I value your good opinion, Tim.
Anyway, I stuck a question in the chat bar that you may or may not want to answer.
All right, I will do that.
All right, thanks for your good talk.
Yes, thanks again. Okay, so if we could move on for our last talk again. This will be Steve Myers. His talk has a very long title, From the VLA to the NGVLA and Beyond, Radio Surveys and Follow-up in the Era of Very Large Multi-Wavelength, Multi-Messenger Synoptic Surveys. Multi-messenger. All right, take it away.
Okay, can you hear me and see my screen?
Yes, sir.
Thank you. Now for something completely different. In case you're wondering, I was the talk that swapped with Poonam from earlier in the morning. As far as reminiscences go, my first visit to the VLA was 1983 with my undergraduate advisor, Steve Spangler, who just spoke. But today I'm going to talk about something new or ongoing. And I'll note that in the greater world of radio and other astronomy, we are entering a new era of multi-everything surveys. They're multi-wavelength from radio to gamma ray. They're multi-messenger, electromagnetic, cosmic ray, gravity wave, neutrinos. They're multi-tiered, all sky wide, shallow surveys to narrow, deep surveys of, for example, frontier fields. They're multi-epoch, synoptic, explicitly tracking the time domain now in a variety of cadences. And in this new era, the role of radio is not too surprising. It has always been used to follow up surveys from other wavelengths triggered both prompt as soon as we can get on a target of interest, or delayed. Tracking phenomena evolve or are quasi-static, like, you know, the radio galaxies that we know and love. But we're also doing new radio surveys, and these are spectropolarimetric. I'll focus on continuum surveys in particular, but there are also line surveys that we've heard about. Wide area surveys, in particular, sort of 10,000 square degrees or more. And by doing these surveys in the radio, we can uncover otherwise hidden phenomena, explosions and events from deep within galaxies and in other regions. Now, the radio time domain contains phenomena on a range of scales, sort of fast phenomena that we've heard about, pulses from pulsars, fast bursts in time scales up to seconds, sort of intermediate, scintillation, scattering, flares, and shocks. Slow transients that we've also heard about, including things like AGN variability and blast waves from supernovae and gamma ray bursts. And those are timescales from days to years, and I'll talk about those more. And of course, even the things we think about in the universe, like our galaxy, other galaxies, do evolve on cosmological or dynamical timescales. For example, the radio jets burrowing out from the centers of galaxies. Amy already gave a nice summary of past VLA surveys, so I don't really need to go into detail here. And I'll focus a bit now on the VLA Sky Survey, and note that Tracy's talked about the commensal survey at 300 megahertz. Casey talked about real fast, which is also commensal. But at this meeting, you'll have heard numerous other surveys, galactic and extragalactic. So in particular, I'm going to talk about the VLA Sky Survey as a tool for finding centimeter wave transient radio sources. And Dylan talked about example of such a thing. This plot's from Mark Lacey's VLAS paper from 2020. And if you want to know details about all the various things in this, I urge you to go look at that. Here at the top is a line for the first survey, and that represents the source counts. Goes up to about 90 sources per square degree at a millijansky. About a % of these are variable, and those provide targets of interest. Christine will talk about that tomorrow. And also a foreground of things that have to be sorted through before you want to find other sorts of transients. Now in this plot, as you go down in the plot, you have increasing area times number of effective epochs. And here's the VLA Sky Survey here. And also the CNSS, which was mentioned earlier today, is also here. And the VLA Sky Survey with 3 epochs spaced at 32 months, covering about 34,000 square degrees, is in this diagram sort of the deepest in rate survey here. Covers 1965 to 4013 megahertz at 2.5 arc seconds resolution from B configuration, and with our about 5 seconds on source, it gives you an RMS of around 120 microjanskis per beam. And we went as shallow as we could by scanning the VLA as fast as we dared to using on-the-fly mosaicing. And we had a net surface speed of about 20 square degrees per hour. I'm not going to dwell on this. This is a plot courtesy of Greg Hallen, and about the various astrophysical things that you might find in these transients. For the 3 epochs, we cover this whole phase space. Up at the top is where we're sensitive. And we've seen things like orphan GRBs, tidal disruption events, GRBs of various kinds, and maybe some new things that we can populate this plot with. I'll return to this at the end for a list of the some of the relevant papers that have come out, including Dylan Dong's paper and Stroh's paper that recently came out, and as well as Christina's. We take the data with the VLAS, and within a few weeks, we can get some images out, 2 to 3 weeks. But that's only the start. We have to go through those images, identify the good transient candidates, and then compare to what we see in the optical. These should all pretty much be from nearby big galaxies, so we compare to what we see in these optical surveys. And we use what we call a transient Marshall for that. Now, generating transient candidates is not enough. You have to follow them up. And in this era of transient factories and multi-everything surveys, follow-up rules. Amy didn't mention this, but we are halfway through the sky survey. We finished the first half of the sky twice, and we're getting ready to look at the second half of the sky for the second time. And this survey will go on into 2024. But we're not the only survey out there. I'm not going to mention in detail Thundercat on Meerkat or Aperitif on Westerbork, but I will note on the ASCAP, the VAST survey, because it's a very nice time domain survey. It has a wide component that's shallow, but with a daily cadence for about 2 years. And that will give us radio light curves for a wide variety of objects, and something we've really not done in a big way. Now, the deeper survey in the same area, about a little over twice as deep as VLAS, gets 7 visits within 5 years. And this whole thing will be an interesting data reduction and classification challenge, as the larger optical surveys have discovered. So I await those results. And if we look a bit further in the future, there's 3 big things at centimeter wave. There's the Deep Synoptic Array, DSA 2000. Greg Hallinan at Caltech is the PI. 2,000 5-meter antennas going from 700 megahertz to 2 gigahertz. And it's a true radiosynoptic survey telescope with a large number of small dishes. For those who remember from that discussion in the SKA consortium. The SKA itself is putting some dishes on the ground, and that's getting going. And at this meeting, we've heard a lot about the next generation VLA. So here's a conception of the DSA 2000. I'll refer you to various documents and websites for that. But with 2,000 dishes and 5-meter aperture, you really get unprecedented survey speeds. And this diagram shows that with survey speed going upward from the bottom. It's up there in this corner with the other big future telescopes, but with a significantly more survey speed, mainly from large number of small dishes. This is following on from the current DSA 110 that Vikram Ravi is working on at Caltech. Likely be sited in Nevada, public-private partnership, and there's a public data component. And we're just sort of putting this together and awaiting Astro 2020 comments on this. And 2020s and 2030s will really be a fantastic decade of surveys. Now in this very large multi-everything era, it will be a target-rich environment, and we will almost certainly
1
be
minute left.
overloaded. Thank you. Many alerts per day, and we'll need to allocate these follow-up resources, possibly through coordination with projects, and ideally rapid response when proposing and scheduling. I just put a thing here noting, probably start some discussions about how you stake out follow-up in response to alerts. Here's the NGVLA concept that you've seen already, but we'll want to equip NGVLA for this very large multi-everything era with fast scanning, wide bandwidth subarrays for multi-band and co-observing, new software, pipelines, and high throughput algorithms, and agile operations, and ideally service calibration for efficient observing. And there will be a transition to the NGVLA from the VLA and VLBA that will want to continue the science that we're doing now, in particular commensal activities and follow-up events for ongoing other surveys, but we can prototype new features, things I've described above. So in conclusion, the VLA surveys have a role in pioneering the radio time domain. We're opening synoptic space, but we're now launching into a new era of very large surveys. And follow-up and new surveys in the radio are critical. And there's exciting new facilities. And there's an upcoming transition, hopefully, that will make things interesting. So thank you.
Thank you very much, Stephen. Do we have questions or comments for this particular last talk?
Steve, I've got a question. So this DSA 2000, is that actually a proposed new project for the decadal study then? Is that my understanding?
Yeah, so it's it was proposed. There's a white paper for Astro 2020. It went, it's less than 100 million, so it's not a large one. So it's targeted for mid-scale infrastructure funding. And it's also now taken on as a principal instrument, possibly for the US pulsar timing community, for example, with the loss of Arecibo. And it'll be really important for next generation gravity wave work and FRBs.
So it's a different scale than NGVLA, so that's the reason it wouldn't be destructive interference.
Yeah,
Okay.
it's not in direct competition there, and that's very important.
Thanks.
We maybe have, we've come to the end of the time, but we could have one more question. I noticed there's a comment from Hari in the chat. Would you like to ask a question live?
Yeah, sure. So it was a nice talk. So how better do you think existing facilities can actually sustain in this new era? Because it's also bound to cause a lot of funding priorities, right? So what's your...
I wish I knew the answer to that. It's, you know, that's why we have things like Astro 2020. But I do hope we can really support the wide range from small, medium, and large projects. And especially in time domain studies where you want as many telescopes on the sky as possible to catch these events.
Well, great. All right, well, thanks again, Stephen, and I'd like to take this time to thank all of the speakers from this session.
Yeah, if you want further talk with me, I'll be in a breakout room, by the way. So.
Thanks for
Thank
that.
you.
Thank you. At this point, we'll break until 15:05 Mountain Time, unless Anna has any announcements she'd like to make before the break.
I have still the same one, but Tracy, are you still there? Did you want to?
make a quick
Yeah, sure, I'm here. So Anna just gave me a moment. I asked her if I could make a brief presentation here or statement. So, you know, all of the amazing science that we're seeing yesterday, today, and it'll come up, you know, we're only able to see that. It's only possible because of the dedication of all the NRAO staff over the past 40 years. And many of these folks, you know, really work behind the scenes and aren't even aware of the impact of their efforts on enabling our science. So I just wanted to take the opportunity to ask everyone who can to take a few minutes and go to the scrapbook page and add memories, comments, or thank yous to the hidden staff that are behind all of this work we're seeing. And that'll be, you know, something that they'll be able to look at and really see the difference it makes. Thanks.
I just shared how the, if for those of you who have not yet reached the scrapbook, that's very much what it looks like, and you can page through it, and we have some fantastic stuff. And I think Tracy will start another page to put a thank you all. So yeah, thank you. Thank you, Tracy, so much for that. And yes, as Danielle said, we will resume at 3:05 Mountain Time. I do have again announcements, but are the same as every single break. So if you have not heard from me yet about the goodies bag that we're going to ship to our attendees, you may hang around for a tiny little while. Also, if you had an issue accessing your registration, you may as well stop. I got some nicer slides this time. Thank you, Justin. So you all will get a celebratory VLA 40th gift back, unless you don't want it. But to get it, we ask you to fill in a quick survey for us so we know the details. Now, how to reach it. Go to the website of the conference. If you see the overview or summary slide, scroll down. If you do that, hang on. At the very bottom, you'll see grayed out register now button, and underneath it says already registered with question mark. Click on that. It will then take you, like, there'll be like this pop-up window where you just very much put your email address and confirmation number that you used, email address that you used for the registration and the confirmation number you got. It just, something that we just realized today morning, that this platform seems to have some quirky error sometimes happening, that it will tell you that it does not recognize it or there's some issue. If that happens, I suggest to just basically pick a different browser and try there. And honestly, it's a random. So if you try Chrome and it doesn't work, go onto Safari. If you try Firefox and it doesn't want, try Chrome, and so on. It's pretty weird, but one of them should work. And then once you're there, at the top, you should now see post-registration pages and the logout button next to it. So click on the drop-down menu for the post-registration, and then you'll see survey. If you click on that, this is what you'll end up with, and that's the information, what we're going to do, what that whole gift back is about, and link to the questionnaire. So please do fill in if you'd like to get the goodies. And other than that, if you do still have problems or any issues, just shoot us an email at vla40@nreo.edu. And other than that, all the announcements as all the other breaks, do check out our highlight poster talks on the website. They'll be there forever, but do come and check it out because the speakers are present throughout the conference, so you may ask them questions straight away. And the breakout rooms are also open. And don't forget about the Slack. And so we are resuming. Yeah, I think I leave this one on. If any speakers for the next sessions are available and would like to test their screens, we can do it at any time. Now I'll mute myself.
Anna, it's Larry. I'm not until tomorrow, but I'd like to give it a try if there's time.
Sure, no worries.
There we go. Is that working?
Yeah.
Okay. Good.
Actually, I
Okay.
wanted to say that you had some. Actually, I should stop recording. Hang on. Yeah, I know, right? This just has to be like edited later on. But I thought that you had some noise happening, but it's not now. So I don't know whether that was just during your connection when you first unmuted.
Yeah, and I will move to another place tomorrow because there's construction going on outside my house. Yeah.
So maybe that's what it was. Okay, cool.
Hi, Anna. I'd like to make a quick test of my slides.
Go for it. Oh yeah, Mark, who has tested? Sorry. Yep.
Good on your end?
Great. Yep. Full presentation mode and yeah.
All right, let me, can you see an animation? Hold on. There we are.
Yes.
Things are moving. Great.
Now
We're done. Awesome. Thank you.
I had, oh, here. Eric. We have 3 Erics in a row for the next presentation.
Yeah, we all noted that. So we're grateful that you scheduled us into our own session.
Right.
And I'd like to quickly test my slides as well. Okay, so all looks good over there?
Yeah.
All right, and that movie's playing?
Yes, it is.
Okay, perfect. Thanks.
Hi, Christina.
How's it going?
It's good. It's good. It's good.
Good conference so far. I've had a lot of fun hearing all the talks. I'm looking forward to chairing this upcoming session.
So I did notice Eric Murphy just joining. Do you want to try testing stuff or you're all confident and good?
I am pretty confident in it, but I can share it all the same.
That's fine.
Yeah, if it didn't work, if it doesn't work, then it's not going to work. Open, let's see. Is that good? And then
What else we have? Judith.
okay, share.
That's what it is, Eric. I just made you look for it.
There we go. Got it. Good.
Yes.
All right.
Are you
Good.
second in the session? So
Huh?
you're second in a session.
Good. Good. Yeah, I noticed that. Well, hopefully that's enough. I just got the kids from a camp, so hopefully they entertain themselves long enough before they run in or something by the time I'm done.
I think I also saw Sean. Did you want to check it out or?
Yeah, sure. I can quickly test.
And Eric. Yeah, 3 Erics, seriously. It will be fun. We have 3 Erics in a row for the session. So it's Eric Koch.
Great.
But
I get to follow the 3 Erics.
Is your middle name by any chance Eric?
No, unfortunately, but I did work with Eric when I was in Virginia, so there is a through line there. Okay, so can I just share my screen whenever?
Sure.
Okay. Does everything look?
Yep.
Okay. Okay.
Perfect.
quick question. Is the third speaker here right now?
No, I do not see.
So I know all of the speakers except for the third one. I'm just not sure how to pronounce that last name. Anyone know?
Is that Eric Koch?
Kosh? Okay.
Yeah, I think he prefers Koch to Koch.
Oh, right. Thank you. Yeah, I would pronounce it Koch, but
Yeah, and a perfectly acceptable choice. But yeah, he prefers the SH sound.
And do you have Judith online, or is Judith on break? Okay, I think Judith is on a break. I'll disappear then for like, oh, actually we do have 17 minutes. It's fantastic. I'll probably disappear for 10 minutes. Christina, yeah, it was only Eric Koch, and Judith that has not tested their slides if they wanted beforehand.
Oh, I'm back. I can quickly test.
Sure.
Does that look all right?
Okay.
Excellent. All right.
Hey, Judith. If Judith Irwin is around, if you'd like to test your slides, I think you are the one person we haven't had do that in the session.
So clearly I only disappeared for like a few minutes. Christina, I've just made you co-host, so you can do many things. And I just remembered, could you remind everyone at the very beginning that we'll do another photo? Just because for the new people that especially just tuned in for this session, but that it will be after the last talk, before everyone disappears for the day.
Sure, no problem.
Yeah, I've been speaking too much here, so it's good if somebody else speaks as well. Thank you.
question to any of the upcoming speakers. Are there any preferences on warnings for time?
Two minutes.
2 minutes before the end of the talk, or once you hit the questions time period? Are there any preferences on that?
Well, then you're tired, then you're late.
I can interrupt you multiple times.
I don't care.
All right, I'll give a warning 2 minutes before the scheduled talk time is up. And yeah, please do try to stay on time though.
Yeah, that plan sounds good to me.
Anna, are you there?
Yes, and I'm recording.
Okay.
That's what you wanted to say?
That is exactly what I was going to tell you.
Thank you.
All right, shall we get started or should we wait? Well, I guess it's 3:05 Mountain Time, so we should go ahead and get this session going. So my name is Christina Nyland, and I am going to be chairing this session. So this is session 8, Nearby Galaxies, and we have 6 talks lined up. You may enter questions into the chat in Zoom or Slack. Just to remind you, the Slack session right now that we'll be using is session 8-THU-PM. And one quick announcement, please stick around after this session is over. We'll be taking another photo and you don't want to miss that. So our first speaker will be Kate Alexander, and she will be giving an invited talk And her talk is titled, titled Disruption Events with the VLA, Past, Present, and Future. All right, go ahead, Kate.
Thank you so much, Christina. I assume you can all see me and see my slides.
Yes, it looks great.
All right, perfect. Well, thank you so much. I'm really honored to be here giving an invited talk at this wonderful conference. And my name is Kate Alexander. I'm currently a postdoctoral fellow at Northwestern University. And I'm really excited to talk to you about the past, present, and future of a very young field, which is the study of tidal disruption events. And I'm going to try to focus during my talk on the key role that the VLA has already played in this field. And it's a story that's particularly exciting to me because I've gotten to be in the middle of it for the past few years, which has been a lot of fun. And also, I think there's a lot of really exciting things coming up in the future in this area. So I think it's a lot of exciting things coming. So since this is officially the Galaxies session, and also to give a little bit of background for some people who may not be familiar with TDEs, I just wanted to motivate briefly why we like to study them. So we know that pretty much every galaxy above a certain mass has a supermassive black hole at its center. And sometimes these black holes shape their galaxies in very dramatic ways, such as here with the famous radio galaxy and these very large, beautiful radio jets. But in many galaxies, the interplay between the supermassive black hole at the center and the evolution of the galaxy is a lot more subtle. A lot of galaxies don't have an actively accreting supermassive black hole. The black hole is fairly quiescent, so they're much harder to study because we don't see these dramatic features as easily. So in our own Milky Way, we can study the supermassive black hole by resolving stars in the nuclear star cluster as they orbit around it. But it can be very difficult to study the processes of what's going on right around the black hole and how the black hole is actually accreting material and growing and feeding its galaxy once you move beyond the Milky Way. And so this is where tidal disruption events, or TDEs, come in. So for the purposes of this talk, when I say the word TDE, what I'm referring to is the process by which a supermassive black hole shreds a star. So every so often in this nuclear star cluster, a star will have a random encounter with another star and it'll get perturbed on its orbit and end up passing very close to the event horizon of the supermassive black hole. If it passes within the tidal radius, the tidal forces from the black hole's strong gravitational well will actually overcome the star's self-gravity and tear the star apart. So if you go from a star to a long stream of debris, about half of this debris stream is gravitationally bound to the black hole, so the gas will fall onto the supermassive black hole and eventually accrete. As it falls on, it will heat up. It'll probably form some kind of transient accretion disk, and we see a flare of thermal emission peaking in the far UV or the X-ray, and possibly some other electromagnetic signatures as well. And people are very excited about TDEs also as potential multi-messenger events. If you have a compact object spiraling into a supermassive black hole, that's the kind of gravitational wave source we might see with things like LISA. And very recently, it's been proposed that TDEs are a source of high energy astrophysical neutrinos. There was a neutrino association claimed for a nearby tidal disruption event by this paper, Stein et al. So TDEs are multi-messenger objects, and they're very unique probes of the accretion process onto supermassive black holes. And to see why, I always like to show this little cartoon picture, which basically just shows as the stellar debris stream is falling onto the black hole, the accretion rate onto the black hole will change by orders of magnitude in a very small amount of time. So in particular, for a period of perhaps a few months, the accretion rate onto the black hole, the mass fallback rate onto the black hole, will exceed the Eddington limit. And so this allows us to study this process of super Eddington accretion, which is still fairly poorly understood, but which we expect to possibly result in the launch of jets or outflows, winds off the accretion disk. So it gives us more insight into this whole question of how do relativistic jets and outflows, like we see in other supermassive black holes, form? How are there state changes in the accretion disk as the accretion rate rises and falls quickly over this period of time? And because you might have outflowing material, a jet or a wind interacting with the ambient medium, you can also, if there's a shock that sets up between that jet and the ambient medium, use these outflows and their interaction with the ambient medium to learn what's the environment right around a supermassive black hole that was recently quiescent, recently didn't have a big active accretion disk prior to the TDE. What does that actually look like? So the VLA and radio observations in particular have been very crucial to study the jets and outflows in TDEs. And there's been a lot of exciting developments just in the past 10 years or so. So 10 years ago was the first big surprise that radio observations brought to the study of tidal disruption events. And that was the discovery that in some cases, TDEs can actually launch powerful relativistic jets. This was not something that was initially predicted for tidal disruption events. People thought they'd mostly show up as these very hot thermal transients, but they didn't necessarily predict jet formation. But in 2011, we detected this very unusual TDE, Swift 1644. This event was actually first detected in gamma rays. People thought it was an unusual long gamma ray burst until it lasted much longer than any other gamma ray burst we'd ever seen before. And the had very strong X-ray variability. And then it also had this very bright, very long-lasting luminous radio emission. And radio observations with many telescopes, including with the VLA, were crucial for this event in a number of ways. First of all, they proved without a doubt that it came from the nucleus of this distant galaxy at a redshift of 0.35. And as we were able to track the radio emission over many years, it was revealed that it became clear this radio emission was coming from a relativistic jet that was pointed towards us, pointed towards Earth. And that jet was launched about the same time that the gamma ray emission was launched. So this was very exciting, and it has led to a lot of really interesting science. And so how do we go from these radio observations to understanding something about the physics of jet formation? Well, the VLA's superb frequency coverage, together with other radio telescopes, has let us track the evolution of this radio counterpart to this TDE over a period of going on 10 years now. This paper is from a couple of years ago, but this source is actually still detectable with the VLA. It even showed up in the VLA Sky Survey in the first epoch. But the synchrotron emission mechanism is very well understood. So if we measure the full SED and we can measure the locations of these break frequencies in this very simple power law SED shape, we can use that to infer things like the kinetic energy of the outflow producing the radio emission, the density of the medium it's expanding into, and details of the shock physics, like what fraction of the energy in the shock is carried by the electrons versus the magnetic fields. And so when we fit this synchrotron model to Swift 1644, we can get an independent measurement of all of these quantities at each one of these different snapshots where we have multi-frequency observations. And so we can learn some interesting things. For example, we learned that in this case, if you're thinking about comparing to, for example, gamma ray bursts, you might expect the energy of this jet to be constant in time, but we find that's not what's going on here. We actually observe an increase in the jet energy for about 200 days before it levels off at a very large amount of a few times 10 to the 51 ergs. And this can be explained in a couple ways, but one possibility is that there was actually relativistic material launched with a range of Lorentz factors. So the initial fastest moving material, the head of the jet, decelerates as it interacts with this dense ambient medium around the supermassive black hole. Slower moving material is able to catch up, participate in the particle acceleration happening at the shock front. And so you start seeing more energy participate in the shock front with time until you finally see everything that there is to see. So we have this idea that we've learned something about not only that this launched a jet, but potentially the structure of the jet as well from monitoring this radio emission over a very long period of time. So we could already do a lot 10 years ago, but since then the VLA underwent its amazing sensitivity upgrade and there's been a lot more radio follow-up of TDEs. And we've started to learn that TDEs have a very diverse range of radio properties. Yes, some of them launch these very bright relativistic jets, but it turns out such powerful relativistic jets are very rare in TDEs. Most TDEs have were either not detected in the radio at all or have much less luminous radio emission down here in this part of the plot. And so one of the biggest questions that we're trying to answer with the VLA and other radio telescopes today is what is the origin of the radio emission for these radio quiet TDEs, which may constitute the bulk of the TDE population. So I wanted to take a moment to take a closer look at this event that's the blue stars right here. This is a TDE called Assassin 14 Li. It was sort of the first well-studied of these radio quiet TDEs. And it's also a special object for me because this was one of the first projects I worked on as part of my thesis back when I was a graduate student. We got multi-frequency observations of this transient with the VLA. We were able to watch its synchrotron emission evolve in time from high frequencies to low frequencies. And just as we did for Swift 1644, we could fit a synchrotron model at each epoch independently and trace out how the radio evolution is evolving in time. So in contrast to the jetted TDE, where there was a relativistic jet, here we find that the radio emission is also expanding, but the velocity of this outflow is much slower. It's just a few percent the speed of light, so still quite fast, but non-relativistic. And rather than energy increasing, we find that the outflow energy is roughly constant in time. It's several orders of magnitude less energetic than the relativistic jet, so this is a much lower energy outflow, but it's also not decelerating and it has a fairly constant energy. So it's just some kind of wind or something potentially outflowing material. So then the question is, what's the physical mechanism that gives you this sort of different kind of outflow in TDEs? In my paper, we presented a case of some circumstantial evidence for it being a super Eddington a wind. So a wind launched off the transient accretion disk formed while the accretion rate onto the black hole was super Eddington. We inferred this by figuring out roughly when the outflow was launched by extrapolating back to when the radius of the emitting region would have been roughly 0. And then we compared it to some modeling of the mass fallback rate onto the black hole done independently from the optical and X-ray observations of this source. And we find that this outflow would have been launched around the time the mass accretion rate was super Eddington. So that's one possibility. Other possibilities are also still not ruled out. For instance, some of the stellar debris from when the star is torn apart doesn't actually end up accreting onto the black hole. It's gravitationally unbound. So you have this tail of debris that's also flung off into the ambient medium. And that should also generate a shock and be moving at roughly these kinds of speeds that could potentially, so that should potentially produce radio emission. But the details of whether this is at a level detectable by current radio facilities depends on the density of the ambient medium. It depends on whether the shock stays in a narrow self-gravitating stream or whether it kind of spreads out like a fan like this. So it's still unclear whether this can explain the radio emission in these radio quiet TDEs. It's sort of looking like it probably can't explain it in all of them. But to really narrow down what's causing the radio emission in these fainter radio TDEs, what we really need is two things. First of all, we just need a larger sample of events that are well studied in the radio. And secondly, we need to keep doing very detailed studies of individual events to really try to not just detect them, but also so we can do this detailed synchrotron modeling and try to really understand what's the physical origin of these different systems. So I'm not going to talk too much about the detailed studies of TDEs in my overview talk here, but I do encourage you all to check out Yvette Sendis's poster talk. This is, she has a very nice paper that we worked on together that's just been accepted to the journal, and it shows joint constraints on this tidal disruption event AT 2019 DSG, that we were able to combine the VLA data with some ALMA data to fully measure not just the peak of the synchrotron SED, but also the synchrotron cooling frequency as well. So this helps us break some modeling degeneracies, get a slightly better handle on what the energy of the outflow is, which is a really key parameter if you are then trying to look at other aspects of this event. This is the same event for which a neutrino is tentatively associated with it. So knowing the energetics of the outflow launched by this event may have implications for mechanisms of neutrino production in this event. So I don't have time to talk about that too much, but I encourage you to go listen to her talk if you want to hear all the details about that event. So for the rest of my talk, I'm going to sort of transition into this idea of building a statistical sample of radio TDEs, which I think is really one of the key directions this field is going to evolve in looking ahead into the future with the VLA and the NGVLA. So now is actually the perfect time to start building a statistical sample of TDEs because we are now finally discovering them at a rate conducive to rapidly building a statistical sample. So TDEs are rare. In a given galaxy, a star gets disrupted by the black hole maybe once every 100,000 years, once every 10,000 years. So you have to look at a lot of galaxies before you start discovering a lot of tidal disruption events. And fortunately for us, that's exactly what a lot of these wide field optical surveys that are online now are doing. Surveys like ASSASSIN and ZTF in particular have been really excellent at finding lots of tidal disruption events. This plot is a little bit old, but the dashed line has proven to be a very accurate representation of how the future has turned out. So ZTF is now finding about 10 TDEs per year. So within a couple of years, we're sort of rapidly increasing the number of known tidal disruption events, and we can really start doing statistics if we follow them up systematically in the radio. And so that's exactly what we're doing right now. My ongoing VLA project that I'm very excited about is I'm running a large program on the VLA to observe systematically for the first time all nearby tidal disruption events that are discovered in the next couple of years. We started observing last November, and we've got some data in hand. We've been publishing our observations on using ATELs and Astronotes. We're working on some papers. This is an international collaboration, and we're always very happy to work with new people. So if you're interested, come talk to me afterwards, shoot me an email. I'm always happy to chat more about it. But I think this is my excitement about where the future is becoming the present for this program. We're really going to have statistics to kind of start to answer some of these questions. And just to give a little bit of a flavor of the kinds of things we're going to be able to do when we get this larger sample, going back to this question of why do some TDEs launch relativistic jets and some do not, and how special is it for a TDE to launch a jet? I like to show this plot, which is basically showing energy of a radio outflow versus the velocity of the fastest moving material in that outflow. So things over here are energetic relativistic jets. Things down here are non-relativistic, less energetic outflows. And so you can see again visually that these relativistic jets in TDEs are rare, and most TDEs seem to launch instead non-relativistic kinds of outflows. And interestingly, you can draw an analogy. It's very similar to the situation with long gamma ray bursts and type 1b supernovae. When a star explodes under certain conditions as a type 1b, type 1c supernova, you do not get a gamma ray burst every time. In perhaps 1% of events, you get a collimated relativistic jet that we see as a long gamma ray burst. But in many of these supernovae, you don't seem to have a jet produced at all. So this may be telling us something universal about jet formation, that you need some particularly special conditions to launch a powerful collimated energetic relativistic jet rather than dumping your energy from your explosion or your accretion event or what have you onto slower moving outflowing material. So this is potentially interesting. We'll continue to build the sample size and learn more about it. On the flip side, you can also use these outflows to study the ambient environment around the supermassive black holes themselves. So here I've plotted a density profile that we've built up from these observations of various TDEs and also a couple of other well-known supermassive black holes for comparison. So for example, we have these direct measurements of the density profile around our Sagittarius A star in our own galaxy, and they have a pretty shallow there's a pretty shallow density profile. The density decreases as r to the -1. And this is kind of what you expect for a quiescent black hole that is not very actively accreting material and where there's stellar winds modifying the density profile near the black hole. But in contrast, some TDEs have a much steeper density profile right near their supermassive black hole. This radius is in units of Schwarzschild radii, but you can think of it as sort of like parsec and subparsec scales. The density profile around these black holes is quite steep. So this may be indicative that some of these black holes have a different accretion history from Sagittarius A star, perhaps a more active accretion history. Some of these host galaxies of TDEs show other signs of pre-existing AGN activity unrelated to the tidal disruption event itself. But this may be telling us that our population of radio TDEs has some interesting and different, it's probing a different set of black holes potentially than some of the other samples we've seen of TDEs so far. So this is really interesting and may tell us more about the accretion history of these black holes as well. And so in the last few minutes, I kind of want to move from the present and start thinking a little bit more about the future. Originally, this is a futures only slide, but really, as we heard in the last talk before the break, and we've heard throughout this conference, in terms of radio surveys, the future is now. We have the VLA Sky Survey, which is ongoing and is already, we're already finding lots of exciting transients in that. We have the first blind detections of a couple of tidal disruption events in the radio. So most of the TDEs I've talked about and shown on these plots were first discovered at other wavelengths, but you could imagine that there are some kinds of galaxies where you might not actually see transients in the nuclei, like very dusty galaxies, for example. The optical emission might be hidden by dust, but you might still be able to see the radio emission from these TDEs. So it's going to be very interesting as we build up a sample of radio discovered TDEs. It'll be an independent way of looking at the TDE rate and also potentially seeing TDEs in different kinds of galaxies. So this was the very first TDE candidate blindly detected in the radio just 2 years ago. And then, the paper came out 2 years ago. And then there's already been one TDE discovered by comparing FIRST to VLAS. This is the Ravi et al. Paper that also got mentioned earlier today. And then there's also various other surveys that are ongoing and underway with current and future facilities. So ASCAP, SKA, all these things going to be great for finding TDEs in radio surveys. I particularly wanted to take a moment to highlight the NGVLA because the NGVLA, unlike many of these current radio surveys, is going to be active at higher frequencies. And because TDEs are synchrotron transients that occur in very dense environments, at early times, their synchrotron radiation is self-absorbed at low frequencies. So you wouldn't actually see you wouldn't actually see them as a fast evolving transient at early times. By the time they're bright at these low wavelengths where things like VLAS are happening, they're already going to be pretty old events. So if you want to discover them early and really see their full evolution, doing a survey with something like the NGVLA that's sensitive at very high frequencies is going to be really exciting. The other thing that the NGVLA is going to be exciting for is, of course, long baseline observations. So right now there is one TDE for which a jet has been directly resolved. This is this very nearby object where it was observed over a period of about 10 years. And in the final observation, you actually can see a resolved jet in this particular event. So it'll be really exciting to be able to directly resolve the structure of these radio outflows in events that are slightly further away. And in the farthest away events, it'll still be useful for helping confirm that these transients are indeed associated with the nuclei of their host galaxy and uniquely identifying a host galaxy. So the NGVLA and other VLBI facilities are going to be really important for that as well.
You're into overtime, Kate.
Yep, I was just going to say, I think I am over time, so I'll leave my summary slide up and happy to take any questions for a minute or two. Thank you.
Thank you so much, Kate. That was fantastic. Let's see, it looks like we have a question by Dylan Dong. Dylan, do you want to go ahead and unmute yourself and ask?
Sure, yeah. So I was wondering whether you think there are good methods for identifying TDEs besides early time optical spectroscopy?
Yeah, so there's a couple things. There's actually, I work with a lot of optical astronomers who are trying to figure out ways to identify TDEs without needing to get a spectrum. And the problem is, as you know, lots of transients when they're young are very blue. So, if you have a young blue featureless transient, it could be a lot of things. Supernovae 1As are more common than TDEs. So even if it's pretty close to the nucleus, 1As are still one of the biggest contaminants. But something that starts blue and then stays blue for a long period of time, is something that's more likely to be a TDE. Supernovae will expand and cool, get redder with time, and TDEs will stay pretty blue throughout their evolution. So that's one thing. Being able to confirm it's nuclear, so using these VLBI observations to really confirm it's probably associated with the supermassive black hole at the center of a galaxy as opposed to offset a little bit can be helpful. But yeah, people are definitely thinking about other ways that don't require you to have a spectrum of every single thing, and also don't require you to wait a month or two to confirm it. But right now we're sort of, the longer you can wait, the more confident you are, as it usually goes with these things.
Cool. Just real quick, do you think that this can also distinguish TDEs from AGN flares, or is there an overlap?
Yeah, so one thing, so I also think that we're going to learn an awful lot about all the very interesting things AGN can do in the radio. I think Christina is going to give a talk and we're going to hear a lot about that, in the session tomorrow as well. So I think we don't necessarily know all the things AGN can do. TDEs, their variability in the radio is more dramatic than we usually see from AGN. Most AGN flares in the radio only have flux changes by factors of a few, although again, not all of them. There are definitely some AGN flares that are much more dramatic than that. But I think it's a very interesting direction for the research is how do TDEs fit into other kinds of accretion episodes around supermassive black holes. So I think we may end up seeing we're already sort of seeing there may be more of a continuum of events. There's some things that are TDEs, but then there's also accretion disk instabilities that can kind of masquerade as something similar, because again, you can have a instability that causes the accretion rate to bump up briefly for a short period of time. So yeah, it's going to be a challenge. I think smooth evolution and very large variability are definitely indicative that it's not a normal AGN flare, but whether it's an extreme AGN flare or a TDE may be a little bit more hard to distinguish.
Awesome, thanks.
Okay, we have 3 other questions. I don't know if we'll get through all of them, but please continue discussing on Slack if we don't. One question is by Ari, and the question is the host galaxy of the radioluminous TDE unusually luminous? In AGN, jets are found in massive galaxies.
So TDEs actually can't occur in very massive galaxies because the tidal radius of the black hole scales with the mass of the black hole. So when you get a supermassive black hole that is too massive, the star will just get swallowed whole because the tidal disruption radius will be inside the event horizon of the black hole. So most of these galaxies that have TDEs in them, the black hole mass has been about 10 to the 6 solar masses. Above about 10 to the 8 solar masses, you are not going to see TDEs because the stars would just get swallowed whole.
All right, it looks like there's some continued interesting discussion on that topic, and sorry for the questions that we didn't get to. Looks like we do need to keep going with our schedule to stay on time. So thank you very much, Kate. And our next speaker will be Eric Murphy. And so while Eric is sharing his slides, I'll go ahead and introduce the title. So the title is Science with an NGVLA.
Yeah, are we in business working?
Looks perfect.
Okay, great. Thank you. Yeah, so a little bit of a detour for this session right now on topic, because I'm going to talk about all of the science, well, the key science that that'll be done with the next generation VLA, which includes TDEs, things you just heard about and have heard about so far. I am operating under the assumption that you've already seen the overview talk given by Mark McKinnon. So I'm not going to go too much into that, though I can certainly take any sort of questions you have on the project at the end. And a reminder that Rob Salini, the project engineer, will be giving a talk tomorrow on technical development and various interesting areas of technical research we're doing. So quickly though, what is the NGVLA? It is a replacement of the existing VLA and VLBA, both of them. It has the scientific frontier we're after is thermal imaging on milli-arcsecond scales, which you probably already heard. We have it's an improvement to both VLA and ALMA for over 2 orders of magnitude, an order of magnitude improvement in sensitivity and another order of magnitude improvement in angular resolution. We increase the frequency range covered by the existing VLA, well, using the main suite of receivers, going from 1.2 now to 116 gigahertz. So from L-band, the detection of 21 centimeter H1 atomic gas, all the way to low JCO, the fundamental transition of CO, J equals 1 at 115 gigahertz. The facility will, as I said, replace the VLA, so it'll be located in the US Southwest, expanding well within or beyond the plains of San Agustin throughout the state of New Mexico and into neighboring Arizona, Texas, and down into Mexico. So the NGVLA is what I consider to be sort of this last suite, a piece in a suite of next generation radio interferometers. We have the SKA that will be, construction will be starting very soon. And it's really optimized below 1 gigahertz. ALMA is fully functional, doing great stuff, and is really optimized at sort of higher frequency observations to be able to detect emission in terahertz windows. That's why it's at such a high dry site. On this plot here sort of shows where the NGVLA fits into this gap in frequency. There's a plot of sensitivity versus frequency here. And if Al's online, he'll complain about the fact that ALMA looks like it's not getting its fair due, but remember this cuts off at the end of 3 millimeters here, and then ALMA, if you keep going right, is game changing at the higher frequencies. The other area of improvement, of course, is angular resolution. And this plot shows angular resolution as a function of frequency for a range of wavelength facilities, radio facilities, some millimeter facilities, optical facilities. And this demonstrator shows, what we're really after here, and it gets to the key science goals. So the line there you see is the angular resolution necessary to resolve 1 AU scales at a distance of 140 parsecs, the nearest major star forming region, to be able to study the habitable zone where rocky planets form. And this is, something that the US ELTs, if and when they go online, and will be able to do. That's what they're targeting. Of course, they're targeting planets that have formed. They want to study those rocky planets, as well as try to characterize their atmospheres. And we, at the frequencies where the NGVLA operates, it's quite complementary. We're studying the planets as they're forming. So before I go into these key science goals, I just want to make it clear that we didn't make them up, NRAO didn't do it. This wasn't on us. This was all facilitated by the community, and specifically our NGVLA Science Advisory Council, who's gotten an extended term because of the delay of the Astro 20 Decadal publication. So they're still hanging in there on board, waiting for that to come out. But yeah, they are the ones who worked with us and, was our conduit into the greater astronomical community to come up with the key science that they felt was exciting and worth building a next generation radio facility for. So this is really, on, they are totally owning this, and we appreciate it. And I think the project is been greatly rewarded for the fact that they're so involved with the development of the science, and of course, in leading into the development of the technical activities. So after going through a process of collecting, over 180 science use cases, they prioritized them into 5 very general, broad key science goals, and they're up here. So unveiling the formation of solar system analogs on terrestrial scales, probing the initial conditions for planetary systems and life with astrochemistry, charting the assembly, structure, and evolution of galaxies over cosmic time, using pulsars in the galactic center as fundamental tests of gravity, and understanding the formation and evolution of stellar and supermassive black holes in the era of multi-messenger astronomy. Clearly very broad, which is, it tells you that what the community is mostly in, what you all are mostly in, is having a telescope that you can carry out your science, whatever that science may be, a very multi-purpose, PI-driven facility. And that is exactly how the NGVLA has been designed. So in doing so, it's naturally highly complementary to pretty much any other facility that you can imagine that exists or will be coming online, or maybe coming online in the future. I mean, it is really highly synergistic with any one of the NASA flagship missions that may fly, obviously SK, ALMA, and the ground-based OIR ELTs. So I don't want to go through this list, but just to make that point, that the users of these facilities will naturally be NGVLA users. So David Wilner already talked about this in quite a bit of detail yesterday, so I won't go over it in too much depth right now. But it'd be criminal not to point out, our headline science case, and that is detecting or studying the formation of planets on terrestrial scales. So the NGVLA really delivers 3 things: frequency coverage, to be able to penetrate the dense gas and dust in the central regions of protoplanetary disks, sensitivity to be able to detect the emission, and then the third thing, angular resolution, to be able to detect it on those scales. So this is exactly what the NGVLA is designed to do, and it will be able to study the distribution of exoplanets and young planets embedded in circumstellar disks, and discover many hundreds of planets with orbital motions of less than 10 years. And why is that exciting? David already sold the punchline, because we can study, sort of the planet formation in situ. We can make these sort of movies to see how the planets are forming. We don't, take a picture of a large sample and then, try to piece together how the formations happen by having different sources. We can study the formation of the planets for a single system, and many systems, that is. So yeah, I find that to be absolutely, remarkable. So the second key science goal is probing the initial conditions for planetary systems life with astrochemistry. So this is illustrating 3 prebiotic molecules that are hypothesized to exist in the ISM that have not been detected. And while these prebiotics have features at higher frequencies, they're totally line blended. They're impossible to observe at sort of, at higher frequencies and distinguish what the lines are. You see how dense of a line force you already have down here at 35 gigahertz. So the NGVLA will have the sensitivity to detect these features in a part of the spectrum where we can distinguish them from other nearby lines. Charting the assembly and structure and evolution of galaxies over the first billion years. So what the NGVLA really does here is it provides the ability to detect low JCO at all redshifts, CO1 to 0 and 2 to 1 at all redshifts. And why is that important? So this image up here, the simulation of a massive star-forming galaxy at redshift 4.4, the sub-millimeter galaxy. This is a simulations of the molecular gas in the galaxy as traced by various CO lines. So the image on the left shows what ALMA would be able to detect in CO4 to 3, higher density tracer of CO, tracing the warmer CO gas that is actively participating in star formation. Whereas if you just jump all the way to the right and see what the NGVLA would see in CO1 to 0, it's qualitatively different. You're seeing the total bulk of molecular gas that is available for star formation, as opposed to just the gas that's actually forming star formation, which is what we can do today. And then we have to try to, figure out how we convert that emission into what the total bulk is. But with the NGVLA, there'll be no ambiguity. We'll be able to detect the gas directly, as well as the dynamics of the gas.
2-minute warning.
Oh, geez. Okay, so studying, looking for pulsars in the center of our galaxy to constrain gravity. So quickly, there are roughly, something like 1,000 pulsars that are expected to be in the galactic center that have not been detected. And one of the thoughts is due to pulse broadening, because you have a highly turbulent ISM and there's high scattering events. Too bad, there was a talk by Michael Kramer earlier today, unfortunately it overlapped with this, in which he went into great detail about this and how the NGVLA will play a role. But one of the ways to mitigate this is to go to higher frequencies. And the NGVLA will have the sensitivity at the higher frequencies to maybe detect these pulsars if they exist. And pulsar next to in the potential of the supermassive black hole Sagittarius A star will be able to provide new constraints on tests of GR. Finally, the NGVLA will have the sensitivity and angular resolution to resolve dual AGN in black hole binaries. We sort of saw this a little bit in the last talk with TDE events, having the resolution to resolve the jets that form with those. So yeah, with the long baseline array, the NGVLA will be able to follow up, say, a LISA event. Hopefully, LISA will have a trigger for supermassive hole binary that'll be ready, planning. I think that's on the order of maybe days or so. If we could follow up, we can maybe even get there before the event happens. And then with the long baseline, there'll be enough sensitivity to actually measure the proper motions of any sort of ejecta from kilonova over 5-year periods, which is the only way really we can get at the astrophysics of what's going on with those systems. Last highlight, this is a study by Lynn Matthews and Kazuo Akiyama as part of our community studies program. So I like this because it's something I hadn't thought about. It's a simulation of an AGB star pulsing, and the reason for their study was basically to see if SMILey, a maximum entropy imaging algorithm, how that worked, which was used for HT, compared to just using CASA. The finding was that CASA actually doing pretty well in recovering the emission, but it's a whole new interesting science case where we'll be able to make movies of the envelopes of AGB stars being ejected and watching in situ dust formation in the galaxy. So I thought that was super cool. Last slide here is just to show like some of the highlights to date. If people really want to dig into the science with the NGVLA, we had a science book. Many of you have published chapters in it. It's nice to dust off every now and then and take a look, because it gets you pretty excited about the project again. Submission of the NGVLA white papers, there's plenty of those. They're all in the archive, and they largely stem from the white paper, or sorry, the science book chapters. We've had 4 rounds of NGVLA community studies covering a range of topics. Those memos are published online in NGVLA memo series. I suggest people checking that out. And finally, if you haven't noticed, and this has been led by Joan Roble, we've had every e-news pretty much since before COVID or right around COVID, we've had a science showcase, usually from early career scientists, talking about it. There's usually a figure and a paragraph of what the NGVLA will do for their science. And that's, again, thanks to Joan, who digs through sort of archive and sees papers that come out that look applicable. But we thank the community for participating in that, and that's been great. So I will end there. Sorry for going long. There's a lot of exciting science.
All right, well, thank you very much, Eric. Are there any questions? We have time for a quick question. All right, well, while people are thinking, I'll ask a question. Could you give a super quick update on plans for the transition between the VLA and VLBA to NGVLA?
Sure, be happy to. So right now we're in the process of developing a process for how that happens. So we thought it'd be a little bit premature to kick that off until the decale comes out and let's see how everything goes. But we anticipate putting together a community-led working group. Largely it'll include members of the users committee, probably science advisory committee and a visiting committee, to go over various options on how this might look, going from running the VLA through as is versus turning it off. We're looking at them to come up with a finite set of options and bring those to NRAO, at which point we would cost them and look at the implications of them, feed them back to the working group, then they can try to come up with some sort of a priority list. Then this would be handed over to some maybe blue ribbon panel put by NSF that would come up with a formal recommendation on how we go forward. But our intention is to make sure this is done hand in hand with the community.
All right, fantastic. So we're out of time, so please continue discussions on Slack if there are more. And let's go ahead and let's move to our next speaker, Eric Koch. While Eric Koch is getting his slides up, I just want to remind everyone to please stick around at the end of this session because there will be a group photograph. All right, so our next talk is titled Unraveling the Atomic ISM Across the Local Group. And everything looks great. Go ahead, Eric.
Great, thanks, Christina. So hi, everyone. My name is Eric Koch. I'm a postdoc at the CFA. And I'll share with you today some of our first results of the maps that you see here. This is tracing the northern half of M31 and the entirety of M33. And this is using the VLA to get high spectral resolution 21 centimeter observations. And so over the past 40 years, I mean, the VLA has had an enormous amount of impact on atomic ISM studies, primarily through tracing the 21 centimeter line. So I've just cherry picked parts of two recent surveys. So Thor tracing the Milky Way plane and Things tracing some nearby galaxies, just to give this contrasting view of the same atomic ISM, but viewed at high resolution in our own galaxy and sort of the galaxy scale, what we see in nearby galaxies. And I think one of the most amazing parts about the 21 centimeter line is just the vast range of science that can be addressed with this single spectral line. And so for the purposes of my talk today, I will be focusing on how do we use the 21 centimeter line to place the atomic ISM in the context of the star formation life cycle. And so just like the 21 centimeter line being used for a variety of science goals, the atomic ISM also plays a large role throughout different parts of this cycle. And so this is a vast oversimplification, of course, but if I take away the parts that the atomic ISMs may be not directly tracing, it's pretty much just the stars. So the atomic ISM is either directly involved with each of these steps or is directly impacted by each of these steps. So for example, H1 hole is driven by different types of feedback. And this means that when we trace the atomic ISM through the 21 centimeter line, there's just an enormous amount of information within a single spectral line. And our view of, or when we trace this in observations, it's important to remember that we're tracing some part of this process, or particularly in extragalactic work, is some average of all of these different steps. And so if we return to this sort of contrasting picture of the atomic ISM and what we see in our observations of the Milky Way versus nearby galaxies, it's the highly resolved H1 and this beautiful structure that we see on the left, where we really understand from within our own Milky Way the atomic ISM properties. So the properties of turbulence, the thermal phases from the absorption studies that we heard about before the break. But on larger scales, it's really in tracing nearby galaxies where we can place the atomic ISM in sort of the context of the entire galaxy. And while these spatial pictures are typically what we look at, I think it's really important to also include what does this picture look like with representative spectra. And so I'm showing the same picture as before with the Milky Way on the left and the nearby galaxies on the right. And we see a significantly different picture that's limited by the observations that we have. So when we look in the Milky Way, particularly this spectrum on the top, the emission, we're looking through the galactic plane, we're looking through many different things along the line of sight. So we get these very complex spectra. As well in the Milky Way, just given our place in the disk, there are numerous bright background continuum sources against which the absorption can be measured. So that's a direct tracer of the cold atomic gas. When we move to nearby galaxies, the information that we have tends to start being a lot more limited. So this is an emission spectrum from the same galaxy I showed before, NGC 628. And so you can clearly see that there's signal there, but the sensitivity is limiting how much we can say about the detailed shape of this spectra. But we want to be able to bring these two views together to understand atomic ISM properties from the small scale to the scale of an entire galaxy. And what I'm going to argue with the results I'll show today is that the VLA can do this right now for the nearest galaxies to us. So these are our local group galaxies. And I'll show these spectra and describe it a little bit more going ahead. But what I want to point out is qualitatively, the spectra that we're now getting at high spectral resolution are qualitatively closer to what we see in the Milky Way versus nearby galaxies. And so the question is, how do we use this information to then study the detailed atomic ISM physics? And so the observations that I'm showing today really emphasize the importance of high spectral resolution. So this is tracing about 80 parsec scales in both of these galaxies, but the clear difference from previous surveys is a much higher spectral resolution. So this is 400 meters per second. And this is really enabled by the upgraded VLA to get a very high spectral resolution, but with enough bandwidth across the H1 line to trace the entire rotation velocity of these galaxies. And so simultaneously, we can get a lot more information. And as well, these observations are now part of the larger local group L-band survey that Eric Veselowski will talk about in the following talk. And so the emphasis here is really this high spectral resolution. So with these data, we see these vastly different spectral shapes. And these aren't really cherry picked, these are just representative spectra, 4 out of a few million in both of these galaxies. So the question that we want to address is, how do we interpret these to then learn about the atomic ISM physics? And so I'll share now just a couple of the results that we found so far, focusing on the data. So I'll start on large scales. Because we have this really high spectral resolution, we have a lot of spectral information. And that means we can start taking advantage of higher order statistical moments. So for example, on the right-hand side, I'm showing a plot of the skewness. So that's related to the third moment of a spectrum. And that's telling us how asymmetric the spectra are between the center around the peak. And what we noted, particularly in M33, is that most spectra have these extended line wings that you can kind of see in the examples here on the left. But from mapping that with the skewness, what we discovered was that in the northern half of M33, most of the spectra, most of these line wings are skewed, are redshifted. So that's skewed towards the systemic velocity. In the southern half, it's the opposite. We have this blue shifted tail that is, again, skewed towards the systemic velocity. And so what we're seeing with these extended tails, or some fraction of them, is we're tracing H1 atomic gas that is rotationally lagging compared to the midplane of the disk. So the interpretation here is this is tracing H1 that's farther off of the midplane from the center of the galaxy. We also find various interesting structures that are large, have larger offsets in velocity from the main disk. So I'm just showing one example here of a likely high velocity cloud in the northern part of the disk. And so this integrated intensity image at the top right is taken over tens of kilometers offset from the main disk. So in that dashed red line that you see, we take an average spectrum that's shown at the bottom. And so we have this narrower disk component, but also this very prominent extra feature offset by about 30 kilometers per second. And this one is particularly interesting because it might be an example of a cloud impacting the disk of the galaxy. And one thing that we can note by looking at larger scales, so this is a larger scale map of M33 taken with Arecibo, is that there's this kinematic feature that they noted called the northern arc that seems to be potentially related to the feature that we see here. And so that gives us some idea of when we look at these, again, these detailed spectra, this is giving us some idea of what these fainter structures are looking like. The next question we wanted to ask is maybe the thing that catches your eye a little bit more, which is the bright H1 and the vast different ranges, multiple peaks and other features that we see here. So how do we interpret those? And in particular, we wanted to revisit this question that was brought up first in the previous set of local group H1 surveys. And that specifically is some of the spectral complexity that we're observing, is that due to tracing an opaque cold atomic gas component in the local group galaxies? And so on the left is a single spectrum. This is one spectrum in M31 taken by the Westerbork telescope, as paper by Robert Brown and collaborators. And the main difference with this previous survey compared to ours is really just the difference of a factor of 5 or 6 in the spectral resolution. And what they noted in this previous survey, looking at some of the spectral complexity that we now resolve quite well, is they noted that there was these spectra with these like top hat-like feature. So you can see that an example of the model plotted here. And their interpretation of this was that this could be due to very cold opaque gas. And so you get this top hat-like shape over the velocity range where the medium becomes opaque. But given the vast different shapes that we see in our data, we wanted to test of whether or not we still see this apparent cold opaque atomic gas. So the way we went about that is through a model comparison test, basically fitting the data with 2 different models and seeing which one the data prefers. So we did that with the model that was used before, that's a single opaque component. And then we allowed for this more flexible multi-component Gaussian.
2-minute warning.
Thank you. And we compare them with this BIC statistic. The important part here is that it penalizes very heavily for extra free parameters. So the more complex model has more difficulty winning the battle, essentially. So when we do this across both galaxies, we find a very clear result, and that is that the H1 spectra really strongly prefer this multi-component Gaussian. And so these are maps of the model preference. So as you get progressively darker shades of blue is showing a stronger preference for the multi-component Gaussian. And so essentially everywhere that we have really high signal to noise spectra, we find multiple components. The reason why this is important is because the opaque model infers this, this cold component and would suggest that there's a large fraction of H1 that we're actually missing. It's dark H1 and it's opaque. The reason why this is important comparing to the new data is it shows the importance of picking an appropriate spectral model that actually fits the data, because it vastly changes the basic properties we measure about the atomic ISM. And so just to end off, this is a first look at some of these complex shapes that we see here, but it's by no means the end of the story. And luckily, we're going to be getting a large amount of VLA observations over the next few years that will really allow us to dig into what sets these vast range of shapes that we see in the H1 across the local group. And so as I put up my conclusions here, I'll end with just one note as we look towards the future with the NGVLA. And one of the main parts that an NGVLA can really revolutionize this field for the H1 is enabling the arc-second high surface brightness sensitivity observations. And so that extends the number of galaxies where we can get data of a similar quality by orders of magnitude. The upshot here would be, instead of just picking the most nearby galaxies, you can pick a representative sample for highly resolved H1 that spans the star forming main sequence to better understand how the atomic ISM is related to galaxy evolution in the star formation process. So thanks very much, and I'm happy to take a few questions.
All right, thank you very much, Eric. Let's see, please enter your questions in the Zoom chat if you have any. We can also continue the discussion on Slack. While people are thinking, I have a question. Could you elaborate a little bit more on dark H1? Would there be any other way to constrain the quantity with other multi-wavelength observations, or is this like really a new frontier?
Right, so the dark component would be this opaque part. So you can imagine if it was optically thin, you'd get the whole shape. So that missing component would be called dark. H1 absorption is certainly the gold standard. We're just limited on the number of background sources, but as the sensitivity increases with something like an NGVLA, you have more sources that are accessible to do that type of work. The other way that you could do this is by comparing different dust tracers and seeing if there's a missing component there, though there is a possible degeneracy as well, depending on the molecular component. But there are a few ways that we can come at this and try to constrain it better.
Okay. And I have one other question. I guess, could you just comment on sort of the future landscape for extragalactic H1 science in the post-Arecibo world that we're in now, and also further along in, as we transition to NGVLA, which may not have the most surface brightness sensitivity for thermal lines for H1.
Sure. So I think for especially the high resolution work that I'm talking about here, there may be some limitations, but it's still a massive step forward. And so we're at the nearest galaxies in the local group, we're still pretty limited to about 20 parsecs. And so that's sort of a limitation of you're getting down to about the size of a giant molecular cloud. But if you want to be able to match to maybe Milky Way or Magellanic Cloud surveys, you can also push forward to get to closer to parsec scales, where you can actually tell how does the H1 evolve across a molecular cloud. And that'll tie in a lot better with the evolution and how molecular clouds form stars.
All right, well, thank you very much. That was an excellent talk. We'll now move on to our third Eric in a row. Our next speaker is Eric Roslowski, and his talk is titled The Local Group L-Band Survey. And
all right, thank you very much, Christina. I appreciate being able to speak in 8A, session 8A, the session with all the Erics. And today I'm talking about the local group L-band survey. And really, I've really enjoyed listening to all of the retrospective perspectives on the VLA over the past 40 years. But today I'm going to be really talking about what the VLA looks like as we go towards the future, and what the VLA is very different from me, for example, in getting older, is that every year it's more powerful and has bigger capabilities. And so I wish that my 40s were traced by a linear growth in capability the way the VLA is. The survey here is really catalyzed by that growth in capability in instrumentation. And where I'm going to be talking about the survey, I really want to recognize that the reason why I'm here is not necessarily the project management team that you see here, but it's really the key work of two postdocs who have made the technical work for this project possible. You just heard about Eric Kosh and the science that he's been doing, but the technical work has really enabled the survey that we're talking about. And I'd also like to call out Sumit Sarbadhakari, who's going to, whose contributions have really made the continuum efforts possible. But what is the local group L-band survey? Well, it's it is an X proposal, which is a larger than large project on the VLA, and we are just kicking off 1,800 hours of observations that are going to span the next roughly 3 years in the L band. So it runs across all 4 VLA configurations, and our targets are 6 northern local group galaxies. They're shown down here in the bottom in their near infrared images, and the most common target here is probably M31 or Andromeda that we're familiar with. And you just heard a bit more about M33, but we're also targeting 6 dwarf galaxies. That's IC10, IC1613, NGC 6822, and WLM. And those 6 targets are great because they span a huge range of stellar mass, of atomic gas mass, and star formation rates, and therefore metallicities. And we're getting a lot of these questions being able to ask in the context of galactic evolution. Now, our strategy is that of pointed mosaics. We're going to have 90 pointing centers spanning these 6 targets, shown here with their H1 distributions in the background, and the little circles are indicating the pointing centers. And every one of these mosaic pointing centers is going to get 11 hours in each of the VLA configurations, except for D, where we'll only observe for about 5.5 hours. So we're going to take these targets and put them together and use the capability that really came with the JVLA upgrade, which is the ability to study the entire L band all at once. And that allows us to multiplex a couple science cases together and ask a bunch of great science questions. Our 2 key science targets are the Stokes-I radio continuum and the H1 21 centimeter line at the 0.4 of a kilometer per second resolution that Eric was showcasing in the previous talk. We'll get some other observations. We're collecting full Stokes, so continuum polarization is going to be possible, as well as the OH lines and several radio recombination lines. But ultimately, we're going to have our key deliverables focus on the Stokes-I continuum and the 21 centimeter line. Now, these 2 observed tracers are going to allow us to tackle several science questions. And we've heard a bit of, you got some teasers of what the H1 21 centimeter science is going to look like. But with our set of observations, we're going to get about 4.5 arc-second resolution, which projects to about 20 parsecs at the distance of these targets. And we'll be able to use that to really isolate the interface between the atomic and the molecular medium in these galaxies and really drill down into it in detail. So one of the questions we're asking is, where is the cold bound atomic gas in these targets? Now, we think that this gas should exist. It should be the progenitor material for molecular clouds, but you need kind of this combination of high resolution in both spatial and spectral directions to see those narrow line width bright features that we expect to be the progenitor systems for molecular clouds. We can also trace interstellar turbulence, and here we use these multi-scale turbulence methods looking across a wide spatial dynamic range, and we're surveying such large areas that we'll be able to map out, for example, the turbulent power spectrum in different sections of the galaxy. And by then looking at what's happening in those sections of the galaxies, we can start to isolate what the driving mechanisms are for this just based on galactic environment. We can start to tackle how the sort of cold, warm, and unstable phases of the neutral medium vary across galactic environment, focusing on line widths of decomposed Gaussian components, and use all this to find out what are the conditions for forming this channel of atomic gas into molecular gas, and then feedback-based response coming back out of the star formation and stellar phases. So, just to showcase some of the data, here is a map of M31 in D configuration. This is our observations that were made as kind of part of our pilot projects. And what I'll do is sort of illustrate the ability we have in having spectral line data cubes to get this full 3-dimensional perspective on the gas. This is a volume rendering of our D configuration data. And it's just the raw size of the area on on the sky that we can capture with the VLA plus the correlator. We can really span high resolution observations spectrally. And then with the full survey, we're actually going to go from the 45 arc-second resolution of the D configuration down by a factor of 100 in angular resolution to go after the high spatial resolution. But this really shows the ability on these scales to connect and understand galactic structure and the connections to the intergalactic medium that we start to trace with the atomic gas. I'll pivot now to the continuum science for the survey. Here, we're expecting to get 2 arc-second imaging once we do MFS imaging, and that projects to about 8 parsecs and 2 microjanskis of thermal noise. And when we're looking at these targets with this resolution, what we're seeing are individual H2 regions and supernova remnants. So we can start to ask questions about how this all connects to the optically visible stellar populations and start to interrogate questions about supernova explosions in the context of these well understood stellar populations. For example, we can look at how the supernova explosions couple to the interstellar medium. We directly see the interstellar medium around these explosions, so we know what they're going to be, what environments these stars are detonating in. We can use this in combination with the stellar populations to really isolate what stars are exploding. And then also, because we have this extinction-free perspective on the thermal continuum, we can estimate what the true ionizing fluxes of H2 regions are in regions of star formation. Going into the sort of source populations in a little more detail here, these are simulations of the targets populations we expect in M31. And these are mocked up for H2 regions on the left and supernova remnants on the right. Both of these graphs are showing the L-band radioluminosity on the vertical axis and the size of the object on the horizontal axis, with the array configurations shown in the shading and the completeness limit shown as the dashed line. And what we see here on the H2 regions, these are generated from an optical catalog, so we'll be quite sensitive to almost the full population of H2 regions in the thermal radio. And the supernova explosions will be able to address a large fraction of all of the possible supernova here and recover them in our observations, both the thermonuclear and core collapse types of supernova. Now, to be fair, it's challenging to separate H2 regions from supernova remnants in our observations because it relies on in-band spectral indices. So we'll probably, the science cases are going to rely on carrying this out probabilistically in a Bayesian framework and in the context of multi-wavelength data. Now, the final thing I want to talk about is how this is a pathfinder for NGVLA science, not necessarily the actual instrumentation, but more about how do we use the vast amounts of data that will come from the NGVLA to drive towards science. And one of the large reasons for the gap between when we proposed 2 years ago and the commencement of observations last configuration was that we really need to demonstrate that we were able to handle the data as it comes in and complete our science case. And we met this challenge in part by developing a lot of infrastructure that enables this science for this large distributed team. One thing we're quite proud of is that we can do all of our data calibration using the VLA pipeline, controlled through a browser-based interface. No one has to download data or have access to specific machines. We just give them a web page and they can flag RFI, in front of the TV or out on a walk. But we can also do a lot of our imaging on heterogeneous high performance computing clusters. So we've learned to kind of scrounge cycles here and there and take advantage of running imaging in a bunch of places and system architectures that we didn't originally anticipate having to use. And we really are we've closed the loop on self-calibration to achieve the high dynamic range imaging that we're going to need for our continuum science case. The NGVLA's main promise is the ability to make surveys like this and executions of the science basically routine. Out to about 10 megaparsecs, you can do a wide variety of galaxies and expand beyond just the 6 targets that we have here in our here in this particular survey. And we'll also expand to different tracers and different parts of the radio band. So we finished our first D configuration observation. C configurations are in progress. Here's data that came down on 21 centimeter observations of 6822, moment 0 on the left, moment 1 on the right. And all of these data are going to come out and be released through the NRAO archive. We started our official survey basically in June. And so that means after the first configuration cycle, or about 1.5 years from now, we'll have a full pass through our galaxies, and we'll commence a sort of delivery, an intermediate delivery of imaging products. We anticipate that'll happen come out in a couple of years. And then after the final observations, we'll do another pass through the imaging and make a second delivery. And from there, after that, we'll do a dot I, cross the T, get best quality effort, probably 1 year after that, to produce our final sort of release products. The table here on the right illustrates all of the stuff that we are planning to release. So it will suit a wide variety of different science cases. So at that point, I'll wrap up and see if anyone has any questions. Thank you very much.
All right, fantastic. Thank you so much, Eric. We do have a question. Jose asks, would the browser-based tool be able to visualize data in cubes like your simulation shown in the talk?
So the browser-based solution is really just for quality assurance. We're just looking for, we're looking through calibration tables and find where things have gone awry, adjusting our flagging and pipeline controls and sending that off. That being said, there are browser-based solutions for cube visualizations that we are using. If you are using Casa, you already have access to a tool called Carta. And it is relatively easy to set up Carta on a server and connect your web browser to it and view data in it. Because I was able to do it, and given where I am, it's that indicates it must be relatively easy.
All right, well, thank you very much again. We can continue discussing on Slack. Let's go ahead and get our next speaker set up. So our next speaker is Sean Linden, and Sean will be telling us about beyond 30 gigahertz, decomposing the high frequency radio emission of H2 regions in nearby galaxies.
All right. Can you see my screen?
Yes, everything looks good.
All right. All right. Well, I just want to first start by thanking the organizers for giving me the opportunity to talk at this anniversary conference for the VLA. Although my name is not Eric, I actually spent my time in Virginia working with Eric Murphy. And so part of my thesis I defended last spring involved many long nights reducing and imaging VLA data. And so much of the stuff I'm going to talk about today is now an extension of some of the results that we got as part of that work. And so what I want to talk to you all today about is, and actually Eric Rosolowski gave a really nice introduction, is the radio continuum emission from nearby galaxies can actually be a really robust measurement of the star formation activity. And so as he was mentioning, in the radio between about 1 to 100 gigahertz, and I've highlighted what the specific NGVLA frequency range is here on the figure. At low frequencies, the emission is dominated by the synchrotron component, which is caused by the acceleration of cosmic rays due to supernova ejecta. And you can see in the top left for M51, the 1.4 gigahertz emission is much more diffuse. It sort of traces larger scale emission associated with sort of ongoing star formation activity in the disk of the galaxy. And as we go to higher and higher frequency emission, in the bottom panel on the left, at 8.3 gigahertz, you see that the emission in M51 is really only tracing the brightest H2 regions within the sort of arms of the galaxy. And you can see on the SED is that as you go to higher and higher frequencies, the contribution from free emission, which is this direct measure, sort of extinction-free measurement of the ionizing photon rate, starts to dominate the SED. And however, there is an additional emission component in this frequency range, which can complicate our interpretation of the radio SED as a star formation rate indicator. And that's what's called the anomalous microwave emission. This emission is a dust correlated component of galactic emission and has been detected over the frequency ranges between about 20 to 90 gigahertz. It has been seen in foreground CMB experiments since the 90s, and is in the last 10 years or so, there's been strong detections of AME in individual molecular clouds within the galaxy, as well as a very recent, as of last year, detection of the AME component in the integrated spectrum of M31. So this is an important component of galaxies that is both present globally and in individual star forming regions. And it's crucial that we understand to what level this emission component arises in galaxies, what conditions are favorable for this emission, and how do we account for it when we look at sort of higher redshift surveys where we might not have access to multi-band observations, where we're relying on an individual observation to essentially trace the star formation activity. So to that end, as part of the work that I did for my thesis, we undertook multiple surveys with the VLA in order to understand the sort of 3 to 33 gigahertz emission for both normal star forming galaxies like M51, as well as luminous infrared galaxies, which are generally major mergers and are often seen as sort of starburst galaxies that are sort of at star formation rates and star formation rate surface densities that are orders of magnitude larger than what you get in a typical Milky Way galaxy. So I'm not going to focus on any of the work we did for the VLA goals survey. You're curious, I published a paper in 2019 with the initial results. And there's going to be papers coming out by Yijing Song in the next 6 months with a sort of fuller account of the results of the survey. Today, I want to focus on the Star Formation in Radio survey, which initially began as a GBT campaign to study 100 individual regions within 50 galaxies in SING's Kingfish. We have since expanded that program to include VLA imaging at 3, 15, and 33 gigahertz to sample this sort of non-thermal to thermal sort of progression in terms of emission for 112 pointings in these galaxies. And the results of these work have been published in the last several years. In particular, I just want to point out the Linden 2020 paper actually presents the full SEDs for all of these regions. And so what actually some of this data look like, here's just 4 examples of galaxies in the survey where in gold, we're actually highlighting individual regions that are detected at 33 gigahertz. And you can see that we detect regions throughout the disks of these galaxies. And I just want to zoom in on one of the regions in M101, showing that we're actually able to make very detailed, high resolution, multi-band observations of all of these individual regions. And so based on the spectra, the 3 to 33 gigahertz spectra, having an 8 micron counterpart, and then cross-checking all of the identified regions with the known supernova catalogs and AGN catalogs, we're able to isolate this sample of sort of 300 regions that we detect down to about 200 or so, which look to be sort of normal H2 regions based on their radio spectra and the lack of any coincidence with known supernova or AGN. And I'm happy to talk more about that at the end. So one of the first things that we did is, as Eric was mentioning in the last talk, 33 gigahertz emission is, because it is in our survey, the band that is most heavily dominated potentially by free emission, we wanted to actually use this as our truth estimate for what the total star formation rate for each one of these regions is. And so because we are studying SING's Kingfish galaxies, all of the observations have accompanying H-alpha observations that we can then compare region by region what the 33 gigahertz to H-alpha ratios are. And what we find is an average extinction ratio in the H-alpha of about 1.2, which is typical for what you'd expect that the radio is sort of tracing these sort of dustier, more embedded H2 regions. But I want to point out these things that fall well above the correlation. And two of them, NGC 4594 and 4579, are actually Seyfert nuclei. And so their sort of jump off this correlation is due to excess radio emission from a central AGN. However, these two other regions that you can clearly see in the 24 micron, but one that clearly stands out is NGC 4725b. And the reason that we've actually plotted both the H alpha and the 24 micron is that we wanted a way to check to see if the excess 33 gigahertz emission was due to some sort of extreme extinction, or by going to 24 microns, we can actually look at a more dust-free tracer of the star formation activity. And so if you see excess in the 33 gigahertz emission from the H2 regions relative to 24 micron, then you truly have an excess of the radio emission relative to any sort of extrapolations for what the star formation rate would be. And so two regions in this parameter space stand out, and that's NGC 4725b and NGC 6946E4. And NGC 6946E4 has been classified as an extragalactic anomalous microwave emission region since 2010, when a detailed study published by Eric Murphy using the GVT found very conclusive evidence that this region was best fit, including this additional bump from the sort of the AME component. And so we've since obtained, using a VLA DDT and ALMA programs, matching VLA and sort of ALMA data to what was available for NGC 6946. And before I show the radio SCDs, I just want to point out what the actual regions look like. You can see that in contours in the middle panel here, these regions, the 33 gigahertz emission actually sits on top of regions with little to no optical emission. So these regions are very optically faint. However, as you go to near infrared, particularly in IRAC channel 2, you see that both of these regions that we detect actually have point source like emission in 4.5 microns and in 3.6 microns. And so this lends to the idea that if the AME is actually correlated with the PAH emission, then what actually is powering the AME is an abundance of small grains relative to larger grains. And how you might get into a situation like this is if you have potentially sort of lack of shocks due to supernova in these individual regions. And so what do the actual fits to the radio plus millimeter, submillimeter spectra look like? So for 6946 E4 and 4725B, both show clear bumps, peaks in the AME at around 30 gigahertz. The implied free fraction from each one of these regions is only about 30%. And so that's just to underscore the fact that if we had just assumed that all of the emission in this region was powered by free, we would have vastly overpredicted the amount of star formation rate coming from each one of these individual regions. The issue is that when we actually look to compare the strength of the AME, which is basically the width, the sort of the total integrated power of the purple model here in both curves, relative to the cold dust emission, the thermal dust emission, what we find is that that ratio for these two regions is very different than the AME that has been found in molecular clouds in the Milky Way. And I just want to highlight that for the panel all the way on the right, here we're showing the 8 micron in grayscale overlaid with the CO contour, CO2-1 contours from our ALMA imaging, showing that while there is an abundance of molecular gas detected in the vicinity of 4725b, we have very little to no molecular gas actually detected associated with the region itself. And so there's, in both of these cases, there's very little molecular gas, there's very little cold dust, but there's this sort of correlation with the sort of the PAH emission, and there's clearly this huge excess in radio emission. So what do AME in molecular clouds really look like, what we know from observations in the galaxy? And I'm not going to talk about comparisons with the diffuse component of AME, because likely that is powered in a slightly different physical mechanism. And these sort of observations are more directly applicable to the regions that we're looking at. So for two molecular clouds observed in the Plane Collaboration data release in 2011, you see there are two of the strongest known detections of galactic AME. And you can see that notably at 1.4 gigahertz and H alpha, the location of this very, very bright emission at 44 gigahertz and 28 gigahertz is not correlated with the typical tracers of star formation. And so we know, again, that these regions are optically faint. They are not necessarily correlated with synchrotron emission or H alpha emission. But actually what they find with these cases is that the AME is actually much more strongly correlated with the thermal dust emission.
You're into question time, Sean.
Oh, great. Great. So I will.
You can talk for another minute.
Yeah.
It's
So
okay.
I'll end by saying that with only 2 regions, we really don't have a good idea for how the AME actually changes in different environments. And so using the radio spectra from our initial 2020 paper, we've identified a sample of 31 additional regions that we have actually are now following up with the VLA. And all of the data for the VLA component of the survey has been delivered. And that includes observations at 22, 33, and 44 gigahertz to confirm these sort of rising SEDs. And so I'll just leave it at that and take any questions you have. Thanks.
All right, that was a very interesting talk. Do you have any questions while people are thinking? Sorry, I didn't mean to sort of interrupt you at the end there so abruptly.
Okay.
If you could take like 30 seconds or so and go over the connection to NGVLA. I saw you had that in your slides, but didn't have a chance to say it.
Yeah, so I mean, if this emission, and so one of the things that's worth pointing out is that these very, very strong cases are only about 2% of the total sample of regions observed in these galaxies. So these very, very strong outlier cases are not necessarily going to be a huge worry. However, we do see that these sort of rising SEDs from 15 to 33 gigahertz constitutes a much larger fraction of all the regions. And so something between 10 and 20%. So there is actually potentially non-insignificant component of H2 regions that have this AME signature. And this is just to highlight that what the VLA could do in 10 hours is on the right-hand side, and what the NGVLA could do in a comparable amount of time is essentially going to allow us to study not just the brightest H2 regions in these galaxies, which is what we've been limited to, but really all of the H2 regions. And so that's going to sort of completely transform our ability to study this in a statistical way.
All right, fantastic. And Dylan Dong has a question, maybe just a really, really brief answer on it. He asks, he says, hey, Sean, great talk. Are the other AME candidate regions in the SFRS better correlated with IR emission than NGC 4725b?
Well, so that is sort of the next thing to look at. We only have ALMA imaging for a small handful of the candidate regions, so we won't know how well the AME, the 44 gigahertz or the peak of the AME is correlated with the thermal dust for most of them. But that is definitely something that we're going to explore. In all likelihood, it's going to be a mixed, it's going to be a mess. But yeah, we'll see.
All right, well, thank you so much, Sean. And let's go ahead and move along. We've got a tight schedule to our last speaker of the session. So Judith. Oh, good, you're there. So Judith Irwin is going to be giving our final talk. This is an invited talk, and it is titled Changes at the VLA. And just as a reminder, please do stick around at the end because we will be taking a group photo.
Okay, thank you very much. And it was a pleasure to, it's a pleasure to be here and to hear all these wonderful talks. I have a bit of a long history now at the VLA. So since it's the last talk of the day, I thought I would start with a few remembrances of the VLA. So here, of course, is the standard picture of the VLA. And this is how I knew about the VLA before I first arrived. So I had to sort of ask myself, when was my first visit to the VLA? And as sad to say, it was April of 1984. As a graduate student from the University of Toronto at the time. And so I thought I would just share a little bit, a few impressions that I had the first time I went. First of all, this kind of picture was the only one I had seen of the VLA. What I hadn't realized was how beautiful the area was. The mountains around, the subtle colors. It was really a pleasure and a joy to drive out to the VLA site for the first time. Of course, when you first see the antennas, they appear like mushrooms coming out of the ground. You just pick up one and then another, and then they sort of bloom out into this great mushroom field. Quite amazing. At the time, of course, we all stayed on site in the visitors' quarters. That was because we had to do all our calibrations on site. There was no APES for calibrations, although we could do imaging at home after the fact. But it meant that you'd come down and set up your observations, do the observations, do all the calibrations, and write your tapes before you came home. And you've heard a bit about this from Rick Perley and Ron Eakers. Now, it may seem like an odd juxtaposition to show a coffee pot. However, what I was so utterly impressed with was that you could get into the central building at any time, day or night, and make yourself a coffee and talk to people. And there are people who like to work all night. And I really liked that exciting attitude where nothing was closed to you. It was all open, and the real goal here was science. So that was really appreciated. Another highlight was Halley's Comet in 1986. I was there at the time, standing out at the VLA site with the antennas all around and Halley's Comet right above. And that was kind of a magical moment. Now, here we have the Green Book. And you've seen a picture of this already. This is actually my Green Book that I took a photograph of. It was the sort of Bible that you could go to find out exactly how you should run things. I have something stuck across here. I'm not sure what the problem is, but at any rate, the Green Book told you everything you needed to know about setting up your observations and doing your calibrations. These were our tapes. If the yellow ring was in the back, you could write the tape, and if the yellow ring was out, it was read-only. You've heard also some information about the pipeline. I didn't actually try to use the pipeline, but there were sections of it that that you needed to look at to do your tapes, to write your tapes at the end of your visit. So I'll just read a couple of things here because you might find it amusing. Go to the Telex tape drive in the back part of the Deck 10 room near the pipeline terminals. Tape drive will have a label with system, subsystem gritter, and mount a tape with the ring in it. Make sure the unit is online, blah, blah, blah. Return to your gritter terminal and fill in the standard commands and run the program. I'll skip a bit. It is usually most convenient to select maps by record number range at 1600 BPI density. About 1024 by 1024 maps will fit on a 2400 foot reel. The execution time to fill a tape with maps at 1600 BPI is only about 10 minutes. So we've come a long way. I hope you agree. But this little pipeline user's guide was actually tucked into my Green Book. And I was kind of enjoying looking at this a bit and remembering a few things. It was inevitable that you had a 10 o'clock flight from Albuquerque, and at 8 o'clock at night, the night before, you were desperately trying to write your data onto tape. Now, onto the science. I want to go to an initial paper written by Hummel, Van Gorkum, and Kotani. And I don't know if Jacqueline is online right now, but this paper actually steered me in a direction that I kind of followed over my whole career. It was a paper about 5 edge-on galaxies that appeared to have radio lobes. And here's an example, a couple of radio lobes on either side. And because these galaxies were edge-on to the line of sight, it seemed pretty strong evidence that you had AGN-related radio lobes from spiral galaxies, which was something quite new. It had only, of course, been seen in ellipticals in the past, and a few anomalous features in Seyfert galaxies, but they weren't necessarily edge-on, so you couldn't see that these were out of the plane. So our job was to follow up on this, and I did this initially with NGC 3079. The major axis is where the arrows are. And I did a lot of H1 work and found that it was interesting that there were many features out of the plane of the galaxy in H1 that had nothing to do with the AGN, or at least if you looked at the velocity field, they appeared to have nothing to do with it. So suddenly you found all these loops, shells, expanding things out of the plane. And that was really, really interesting and worth following up even more. Apologies to the NRAO staff. I had to sneak in a GMRT picture here, but you can see the same galaxy here with radio continuum contours, and they extend a long ways out with these low frequencies. Now, following all this, we looked at various galaxies and found basically that in any component of the interstellar medium was represented in galaxy halos, which is called them halos, not dark matter halos, but gaseous halos, dust, X-ray gas, H-alpha emission, H1, CO, you name it, all of them are represented in halos to some extent or another, and there was a lot of structure. So that led to looking at really an initial limited survey of edge-on galaxies in the radio continuum. I just put one picture up here of NGC 3044. And that was kind of, actually, I'm sorry, there's something over top of my slide, so I can't actually read what I've got myself. I hope you can.
It looks okay to us. I can see subsequent years.
Okay, good. There's just one of these long, telling me screen sharing and so on across.
Okay, we don't see that.
Anyway, you can read it. I think I've given you an indication of somewhere what the, yes, there it is. The RMS, typical RMS at a 50 megahertz bandwidth that we got at the time, 43 to 230 microjanskis per beam, C array L band. Okay, jumping ahead, big changes with the expanded very large array. And that gave me an idea to do something much bigger with looking at more galaxies and more, different bands and different coverage from with spatial resolution. So this started the Changes project. And Changes, of course, stands for Continuum Halos in Nearby Galaxies, an EVLA survey. So it's an acronym within an acronym, but the acronym within the acronym is not quite right now because the expanded very large array is now the Jansky very large array. So never mind, just push along with it, hope for the best. But that was a big change with the wide arc correlator and the wide bands. And so I got a group of people together, actually an amazing group of people, to work on this project. You see some of them here at a Calgary meeting in 2018, but there are more than you see there. And we actually heard from Eric Murphy earlier, and I think you can see Eric Rosolowski in this picture as well. So two Erics. And the idea here was to take advantage of the L band and the C band wide bands, 2 gigahertz at C band, 500 megahertz at L band, use 3 arrays, 2 frequencies, but the key was all 4 Stokes. And so we could look at polarization and really get into the magnetic field information. At the lower left is GBT. We have some zero spacing flux data to add as well. Before I look at the science results, just want to let you know that you can actually download most of our data at queensu.ca/changes. It's very simple, simple to remember. And you see a page like this with all the galaxies, and you can click on them, and then you can download the FITS files. We also have H-alpha images, the polarization images, with and without primary beam correction, et cetera, et cetera. So there's lots of data there if you would like to make use of it. Okay, just briefly, I've picked out a few science results which I think are interesting, and particularly interesting. On the bottom left is that original paper from 1983 showing you NGC 4388. It's in the Virgo cluster. And on the right-hand side, one of our PhD students, Ankur Damas-Segovia, obtained this image that you see here, combined a couple of arrays at C-band. And I think you'll agree the detail is really quite exquisite, where there are many, many more features showing up. This is total intensity, and this is polarization here. So it's all been corrected for by RM synthesis for Faraday rotation, and evidence for a velocity of outflow, as I've written up at the top. Notice the RMS in Q and U, it's 2.3 microjanskis per beam, which I think is pretty good. And this is another image of the same galaxy. I just wanted to show all the magnetic field vectors and how they pull together in this particular case. Now, what else is interesting? Many things, but this one I really like. It's uncovering hidden AGN-related structure in radio polarization. So we see here NGC 2992. The color is just an optical DSS image. So we have a major axis sort of going roughly up and down in this picture. This is the total intensity radio continuum. And you can see there's some features a little bit right and left and so on. But you couldn't make any claim by looking at this for two lobes and an AGN sort of thing. But there's the polarization. And now it's, I think, quite clear that you have AGN-related double lobe source, just the way you saw for 4388 or for 3079. So polarization is a really great way to pick up things that you wouldn't normally see. Here, for example, is 3079 again. The top picture is total intensity and the bottom picture is polarization. So the contrast in brightness and polarization between the lobe and the center of the galaxy is much greater in the polarization than it is in total intensity. Another galaxy, NGC 5792, never before seen structure, but it looks like we have a double lobe source in this galaxy too. Now, what else have we found? This, in my opinion, is one of the most important results from changes. I'm looking here at NGC 4631. So on the top left, you can see where the major axis goes, and then there's a little companion here. Now, that major axis just goes along here, where I'm pointing on the bottom picture, and the colors indicate whether the rotation measure is positive or negative. And I want you, instead of looking right along the plane, which would be in the middle here, just go up, which would be maybe 2-3 kiloparsecs up, and draw a line across parallel to the major axis. And what you see is negative rotation measure, positive rotation measure, negative, positive, negative, positive. There is a regularity to the RM as you go across the galaxy. In other words, the magnetic field is pointing away from you, towards you, away from you, towards you, etc. The bottom doesn't look quite as clean, but still some evidence there. In case you think that's just something weird with NGC 4631, I'd like you to, I refer you to Marita Krause's paper in 2020, where all the galaxies are looked at as best as possible. Any galaxy where you have sufficient signal to noise, you can see these reversals in the rotation measure. Now, we actually have some models that discuss this. This is, I've got a few references here, mostly models led by Richard Henriksen. And you can see that depending on the modes that are in your magnetic fields, you can get different rotation measure structure as a result. So in other words, you would cut across, this is just one quadrant, and you'd see plus, minus, and that depends on how things are, what modes are showing up here. So regular magnetic field patterns on kiloparsec scales require a dynamo action. These models are all based on the dynamo. And what patterns you see depend on which modes are dominant. And the very third paper here has just come out on arXiv, where what we've done is tried to look at different inputs and compared them to changeless galaxies to see what might be the modes that are actually there compared to what you see. Okay, what are the dominant modes? For Marita's paper, what I did here was I took 28 galaxies, all scaled to the same angular size, rotated to the same major axis orientation, every point weighted by the RMS, averaged all the Qs, averaged all the Us, and recalculated the polarization and the magnetic field vectors. And this is what you see. And you can see it's a little messy, but not as messy as you would expect if everything was random. In fact, there is a kind of an X-type field this way, and a little bit more down this way and over to the right. Now, X-type fields have been seen before in individual galaxies, but this is the first time that 28 galaxies have been put together, and the X-type field, shaped field, still shows up. So what does this summary tell us? Well, first of all, in order to have a dynamo, you need star formation related activity to create subscale turbulence. And that's an ingredient in dynamo action. You have to have cosmic rays, so you need star formation in order to illuminate the magnetic fields. But actually, what you really have is a fundamental structure globally to the field itself. Individual star formation regions would not explain a global field pattern like this. And so you can imagine different star forming regions like popcorn in the disk going off, but the field itself is generated with something deeper, something more fundamental, something powerful. So I think it's quite robust is what I'm trying to say. Now, that doesn't mean there's no winds at all. If there are global winds, that can be part of the magnetic dynamo. So I think this is really something new and worth following up on even more in the future.
2-minute warning.
Okay, there was a talk on TDEs earlier. This galaxy is particularly interesting. We found the radio outburst serendipitously about a year after a gamma ray TDE event. I think I probably don't have time to go into any details, but again, the most recent archive paper here discusses how even central outflows can result as a part of the dynamo. What next? Right now, as we speak, S-band data are being acquired. So here's what we had for changes. 1, C-band, L-band, and now we're filling in S-band, which is absolutely great. This program is being led by Volker Hiesen, Elena Stein, and Teresa Wiegert. And that really allows us to get into the structure of the spectral index, try and understand the cosmic ray propagation and so on, position by position. And you can see this is actually normally Faraday thin in C-band, and L-band, there's not much polarization seen at all. It's Faraday thick. So S-band is crucial for seeing what happens with the polarization structure going from C through to L. What could we do with another factor of 10 sensitivity? So much, it's hard to know what to say here, but I could mention a couple of things. Here is a stacked 35 galaxy image from changes. Where does it keep going? What about the magnetic fields? If there are magnetic field lines, you would expect the field lines to close somewhere. Are they connected to the intergalactic medium? Another factor of 10 sensitivity could really start getting at these kinds of questions. We know that halos have lags, velocity lags. As you go up, the velocity changes. And well, we have one model which explains this in terms of a connection of the galaxy itself to the intergalactic medium. Much more, of course, but I think that that's where I should stop. Thank you.
All right. Thank you very much, Judith. And we had some lively discussion on memories of the VLA going on in the Zoom chat window. Do we have any science questions? Remember, you can also you can enter them here or also in the Slack channel. I'll start out with a quick science question. Could you go into a little bit more detail on the variable TDE source?
Yeah, I was kind of skipping that because of my time constraints, but
I was curious if the polarization properties are varying with time in that case, for instance.
Yeah, for some reason I can't quite get out of this. Okay, there we are. Okay, back. Why can't I go back? Right. Yeah, there's a long story about this particular source. It's right in the Virgo cluster. We caught variability even during we had like 2 frequencies and 3 arrays. And those 5 observations spanned at about 6 months. And in that 6 months, you could actually chart out the change in the brightness and in the spectral index. And at L band, the source was turning over and becoming a synchrotron self-absorbed. And at the higher frequency, it was optically thin. And here you can see the question here is, surely there's more emission from the disk. Where is it? And in fact, you know, we should have seen a decent we should have seen a decent amount of signal to noise given our data, but we see nothing out here. All we see is this unresolved core, and it's circularly polarized. And that's hard work, to tease that out of the VLA because of the circular feeds. But nevertheless, it's quite a strong source. So if you look at L band, for example, there's nothing at all in linear polarization, but it is circularly polarized. And so I think it's another, although it's a difficult project, I think, but it could be very illuminating as to what's going on deep inside the cores of these AGNs.
Very cool, thank you. I see Rick Perley has a question. Rick, do you want to just ask your question?
Okay. Judith, the image you showed with the alternating RMs, you know, positive, negative, positive, negative.
Yeah.
The dashed lines, I presume, are the intrinsic magnetic field structures orientation.
Sorry, I got to find it again.
Yeah,
this one here?
The little dashed lines, I presume that's the.
This is like, this is the red lines, do you mean?
Yeah.
Those would be magnetic field direction. Those are the B field vectors.
I'm trying to understand how you get an alternating RM in constant fields. Is the RM medium in front of some background, or is it more complicated?
No, there's nothing significant in the background. So this is intrinsic to the halo itself. It's tricky, right? Because you've got a 3-dimensional thing that you're seeing edge on here, but I don't think there's any way around it. You have to have a magnetic field pointing away from you and then towards you and away from you. Like this is what the data shows. And it's not just this galaxy. So it seems to be a regular pattern seen in any galaxy in which you have sufficient data. I don't think there's any that don't if you have a high signal to noise. You'd have to look at the details of the modes and the magnetic field patterns from these models to sort of dig out, separate what's going on in the various quadrants and so on. But we managed to do it. Actually, mostly Richard managed to do it. Yeah, it's. I'm not sure if I answered your question properly.
Well, it is, of course, complicated because there's a lot of things going on and it's all in projection. So it's very difficult to try and understand. I guess I was just drawn to the regularity of the fields despite the alternations of the RM. I'm not disputing the towards and away from you. I suppose with the 10 times increased sensitivity and resolution, we mustn't forget that beam depolarization is a significant problem in these things. So more resolution is going to help.
Yes.
We have one more question, maybe just a super quick, just a little bit of time here because we want to make sure we have time for the photograph, but I'm curious about this too. Does the source exhibit interstellar scintillation?
Oh, we don't have that. We don't have that information. You know, this is a full galaxy. I think for interstellar scintillation, you would need a point source in the background, right? If you're going to be studying that from our own ISM, is that what you mean? Because we just don't have the data for this extended source.
No, that's not the extended source. That's the galaxy in Virgo.
This one is not in Virgo. This is 4631.
No, not 4631. The galaxy in Virgo
Oh, okay.
showed up as a point source.
Yes. We never even thought of that, to tell you the truth. It's not quite a point source. There's a bit of a disk that you can see at, you know, B array, C-band, and higher frequencies. But it is true that it's a strong point-like source, and perhaps you could design an experiment to use it as a probe. I don't know.
So there's no VLBI observations of this source, 4845?
VLBI?
Yeah.
Yes, yes, there is. There are some papers by ourselves and Eric Perlman, another Eric. And there is one VLBI observation. There were two structures. There's another very close to the nucleus. There's another paper on its way with follow-up radio data. And in fact, I think I was mentioning that there was an X-ray outburst, right? The hard X-ray outburst to identify the TDE. A year later was all of our data showing spectral evolution and so on. And then there were some more observations after that. And it turns out that we have another outburst in the radio. So there's two, we've actually found two radio outbursts now. And as I speak, the almost final draft of the paper is ready and will be sent in, submitted for publication probably within the next couple of weeks. You know, if you want to know more about that light curve, you could maybe email me and I could show you the light curve provided Eric Perlman agrees.
All right, well, thank you, David Jauncey, for clarifying that question. And it's a very exciting time domain result. So we are at the end of this session. If everyone could just, well, thank you, Judith, for a wonderful talk and for all the memories and the cool science. But if at this point, I think we're going to do a photograph.
Yes, we're doing a set of photographs throughout the days just to make sure that we get everyone on, especially that different time zones connect at different times. So actually, I'm going to stop my video because I already am on the camera, and yeah, I'll try to do it quickly, and then we're going to collate them all together. Okay. And as everyone is waiting, when I'm finishing taking screenshots, also if there's anyone here who has not yet heard about our celebratory gifts, I will mention about this in a second. I just have a suspicion that those of our colleagues who probably connected from far east, especially Australia or something, might have not heard that yet. Thank you. I have took the screenshots. And so I'll do it super quickly. Oh, that's my desktop number one. 1 second, I'm sorry. So I'll start saying before I even share. So we are going to send everyone who would like from the participants that joined us during these celebrations, we will send a celebratory gift back. And but we do need a number of answers from you. So to claim your gift back, you do need to navigate to the website, the conference website, that you're probably not completely familiar with. And then log in there as the participant. So you need to go to the overview first. That's the very first page that you're going to see. Scroll down the page. You will then, oh my goodness. And then you will see grayed out button, register now. The button does not work because the registration is closed, but underneath you'll see already registered ? Click on that one. Once you do that, you will see a pop-up window where you will need to add the email address with which you registered and the confirmation number. And once you're there, you will see a post-registration web sites, additional sites. If you open that drop-down menu, you'll see survey, and that will take you to the subsite that explains what it is and takes you to the questionnaire. I do apologize, it's so complicated, but this is how this platform works. If anyone has any problems with that, just shoot me an email at vla40@nru.edu, and I will be happy to help you out. So that's it. Thank you. And we are returning tomorrow at 9 a.m. Mountain Time, which is, I think, 16 hours or something like that. Thank you all.